Genshin Impact, a game that most of you likely have heard by now or even played. In this game, there are around 4 to 5 main ways of roaming around the map. We'll be focusing on the first 3 of these systems: moving, gliding, and swimming. Of course, we'll start with their base, the movement system. Because it is a base, it also means it will take the longest. Now, I planned on splitting the tutorial in one video per system, but as I was writing the first tutorial, I noticed it will take quite longer than I expected. So I made a poll in the community tab, and while not by a long shot, most people voted to split it into smaller videos, much like my dialogue system. So I rewrote it to make more sense that way. However, because it was quite close in votes, I attempted to rewrite it in a way that made sense when put together. So whenever I release the last video of the first part, I'll also release one video with all of those videos together as soon as possible, for those that prefer it that way. Of course, because the video will be quite long, it will likely take hours to render it, and will take quite a while to rewatch it as well. So I'll just hope that it renders with no audio artifacts. If there happens to be any, I apologize for it now. Before we head into our tutorial, let's first take a look at what are we going to be using. We'll be using Scene Machine, which is an Unity package that easily allows us to add a camera system with pre-made algorithms. The new input system, also a Unity package, is a new way of creating and reading input. The animator controllers and animations allow us to add animations to our character. We'll be taking a look at reusable substate machines, but won't be taking a look at planned trees. Physics-based movement simply means movement using a rigid body. We'll not be using the built-in character controller. A floating capsule is a technique that easily allows our player to move up or down slopes as well as steps without any weird jumps or problems. And finally, state machines are an easy way of adding, removing and changing states. In our case, they will be our player states. All of these will be introduced in the base movement system part of the series, which is the main reason why it will take the longest. I'll try to explain as much as I can for what we need, but if you are interested in knowing more about these topics in whatever areas I don't cover, I'll be leaving a few links in the description. Regarding state machines, it is very likely that you'll see different ways of using them throughout other tutorials, so don't worry if mine is somewhat different from theirs, as that's normal. If you have already finished the series, if you did enjoy it, leaving a like and subscribing would help me out a lot, as it allows me to reach more people. Feel free to also leave any feedback whatsoever so that I can improve my future videos. With that out of the way, I really hope you enjoy this series. Let's then start by creating our project. All we need for this system is a 3D project. Unless there's any current problem with using HDRP or URP with Scene Machine or the new input system, we should be able to choose any 3D template we want. I'll go with a simple normal 3D template. For the Unity version I'm currently using 2020.3, but you should be able to use any you want. I do recommend at least 2020 as we'll be using serialized properties, but if you are using 2019 that should be fine as well. Simply swap the properties with public variables instead, or use non-automatic properties. For the name and folder of the project, choose the one you desire. We'll start by setting up a base namespace to make sure no name conflicts happen. To do that, we go to Edit, Project Settings, Editor, and scroll down to Root Namespace. I'll name mine Genshin Impact Movement System. Of course, give it a name you like. For simplicity, this will be the only namespace we'll be adding in this tutorial. I also went ahead to Kenny's website and downloaded his prototype textures. You can use normal materials if you prefer, in case you don't feel like downloading them. I'll have mine be inside of a folder named Materials. Next, let's download Scene Machine. To do that, we go to Window, Package Manager, and choose Packages from Unity Registry, and search for Scene Machine. Make sure you select the latest version here, which by the time of this video is 2.8.4. This is simply because there are some bugs happening in the older versions, so we are just making sure we've got a working one. If by the time you watch this video the default version is at least 2.8.4, then you should be fine. When that's done, press Install. When Scene Machine is done installing and importing, go ahead and search for Input System. Select it and feel free to install it with the default version. A warning should show up asking you if you want to disable the old input system. While it's not necessary, we don't need the old input system for this tutorial, so I'll go ahead and press Yes. To note that this will restart your project. If you chose No, make sure that in Edit, Project Settings, Player, and Other Settings, your active input handling is set to both or Input System Package New. Your project will also restart when you change this option. That's all for our packages, so we'll now go ahead and start downloading our character model and its animations. We'll of course be using a free model and free animations, so do not expect them to look as good as Genshin Impact animations. To do that, we'll be using a website owned by a dev named Mixamo. So go ahead and open up mixamo.com. You'll need to log in with an Adobe account to download the assets, but you can create an account using Google or Facebook if you do have them. When you are logged in, go ahead and open the Characters tab. This is the list of character models we can choose from. You can choose any character you want, but I'll go ahead and search for Ybot and select it. Once you have your character model selected, press download at the top right. For the format, make sure you choose FBX for Unity. I'll leave the pose as T-pose. When that's done, press download again. I'll be renaming the file to character model. Then, in Unity, I'll create a new folder named Models, followed by Characters, and Player inside. And then drag our character model here. With our character model in Unity, we of course need its animations. So back into Mixamo, go on to the Animations tab. We now have a list of animations we can download. For now, we'll only be downloading animations for our base movement system. Note that the only important setting in the Download tab is the Format option, which shall be set to FBX in Unity. I'll also be renaming the files, but I'll leave the new names in the screen. Here is a list of animations I'll be downloading. Idle, Walking, with an overdrive of 15 and the in-place option enabled, running, around the bottom, with the in-place option enabled, running above a bit, with the in-place option enabled, idle to sprint, run to stop, at the right, stop walking, with a starting trim of around 45, stop walking again, but with an overdrive of 25, character arm space of 55, and starting trim of 50. Jumping on the second tab at the right, with a starting trim of around 37. And falling to landing, with a starting trim of around 22. We have all of the animations we need, so it's time to add their files into Unity. Before we do that, make sure you have the following names in your animation files. Back into Unity, select all of our animation files and drag them into our models folder. Now these are models that come with an animation. We already have our base model, so we of course only want the animation clips, so we'll have to extract them out of the assets we have just imported. If we go ahead and open up one of the assets by clicking on the arrow icon, we can see a bunch of other assets inside. The one we want is the last asset, which is an animation clip. Now if you kept the ybot at part of the file name, your animation clip should have the same name as the text that follows it. This is why I've asked you to rename the files. If you did rename the files to not contain the ybot at part or whatever name your character model has, then the animation clip will come named as mixamu.com and you'll have to rename them through Unity instead. So I recommend just renaming and redragging the assets with the correct names. To get these animations out of our assets, we simply open up every asset, Control-click each of the animation clips, and then press Ctrl-D to duplicate them. When that's done, we won't be needing the downloaded assets anymore, so feel free to remove them. Do not remove the character model asset though. We now have our animations, so let's add them to a new folder. In the Assets folder, create a new folder named Animations, followed by Characters, Player, Clips, and States. I'll drag every single animation to the States folder. Then inside of this States folder, I'll create a few more folders. Moving, Stopping, Landing, Grounded, and Airborne. I'll add the walk, run and sprint animations to the moving folder. Then I'll add the light, medium and hard stop animations to the stopping folder. The light landing animation will go to the landing folder. When that's done, drag the jump animation to the airborne folder. Whatever remains here except the airborne folder will be moved onto the grounded folder. It's alright if you have no idea what these folder names mean, as it will become clear later on. We are just adding them now for organization purposes and do not need to do it later. Before we keep going, there were some animations that we have downloaded that didn't really have the in place option. This means that they will move the player forward without our input, which is something we do not want. We will change that in the following animations. Start by right-clicking in the Project tab and add a new animation tab. I'll dock it to the right for a bit and resize it. Then double-click on the dash animation on the grounded folder. The animation window shall now have all the keyframes of this specific animation. Open up the Ip's Position tab and select all X and Z keyframes. Then press the delete key to delete them. Repeat these steps for the light stop, medium stop and hard stop animations in the stopping folder as well. Next, we'll need to change some of the animations to keep looping after they run once. We can do that by enabling the loop time option in the animation clip. We'll do it for the idle animation and the walk, run and sprint animations. Our animations are now set up properly. We have our packages, character model and animations imported into Unity. But to be able to try out our game later on, it's best for us to have a small test map. We'll go ahead and create one now, but don't worry as it's easy and fast. If you do not feel it's worth it though, I'll leave a link down below where you can download the final map. We'll be using ProBuilder to easily build it, so go to Window, Package Manager, and choose the Unity Registry packages. In here, search for ProBuilder with no space in between. When it shows up, select the default version and install it. When it's done installing, go to Tools, ProBuilder window and dock it to the same tab as the Animator tab. We'll start by creating the ground by pressing on the new shape square with the plus icon. This will open a shape tool to select our object shape and its size. To note that for this to show up, you need to press directly on the plus icon square. You can also open this window by pressing Ctrl-Shift-K. We now have a preview of our shape in blue. Leave it as a cube and set its size to be 2000 by 100 by 2000. Press Build when you are done and close the window. Then I'll go to the Canis prototype texture folder and open up the dark PNG folder and drag the texture 05 to the ground. This will create a material, so now press on the ProBuilder Material Editor window and assign this new material to the Alt-2 shortcut. If we now select an object and press Alt-2, our material will be applied to it. I'll add this ground to a new parent game object named Environment and also rename it to Ground. I'll set the environment transform position to -1000, -100 and 1000 to center it. I'll also drag our character model into the scene. When that's done, add a parent game object to the character model and name it Player. Reset both game objects' transforms. This will make it so that our player has a different object for its main component and its graphics. It doesn't matter too much, but you can also set the camera to 0, 1.5 and -1. Next, we'll add one small ramp and one big ramp with a small area to walk on. To do so, press Ctrl-Shift-K and choose the cube shape. I'll have the size of the small ramp be 5 by 1 by 15 and build it. Close the window and select the Edge selection icon. Select the top and edge and also the Move tool. Then hold Ctrl and pull the arrow upwards until you got around 6 squares. Then select the top start edge without holding Ctrl and then move it down until it's on the same level or close to the same level as the bottom edge. We now have a ramp, but let's add our base to walk on by going to its back, select the face selection option and select the back face. Then press Ctrl E to extrude and move it with the Ctrl key held around 5 squares. When that's done, add this object to the environment game object and rename it Small Ramp. Then choose the object selection icon and move the whole object somewhere else you'd like. I'll also press Alt-2 to give it the dark texture. I would like for the top of the ramp to have another color though, so go to the orange folder and drag the texture 02 into the ramp and then press Ctrl-C to undo it. This created a new material, so open up the material editor window and add this new material to the Alt-3 shortcut. Then select the face selection icon and then select the top face and press Alt-3. Let's also expand this small ramp to have a big center by extracting each side faces. Make it as large as you want. I'll have each side be 5 squares. Although we won't use it in the first part of the tutorial, our water will stay here. When you are done, let's add a ramp that goes down to the water. I'll select the bottom edge of the side I want to add a ramp on, and press Alt-U. This creates an edge on the opposite orientation, so now drag the newly created edge to be 5 squares from the wall. Then select the new face and extrude it with Ctrl-E and drag it a bunch of squares. Now select the top edge and drag it down. Then select the top face and give it the orange material with Alt-3. Let's build another ramp by pressing Ctrl-Shift-K and make the set be 50 and build it. Make it a child of the environment game object and rename it to Big Ramp. Move it to a place you desire. I'll place it to the left of our small ramp. Then select its top and edge and drag it up as many squares as you want. When that's done, drag the top start edge down until there is a small step, which will serve as a test for our step climb. I'll also extrude the back face around 5 squares. Select the wall object now and give it the Alt 2 material. And then select the rump face and give it the Alt 3 material. With that done, we'll now add a new cube with a size that fits our water area. Make it a child of the environment game object and rename it to water. Then go to our materials folder and create a new folder named environment. Inside, right-click the project window and go to create material. I'll name it water. Change the rendering mode to transparent and make its albedo color a blue with a lower alpha. Then drag the material into the water game object. Next, remove its mesh collider and add a new box collider and set it to trigger. We'll also add 2 small rectangles to test something later on, so press Ctrl-Shift-K and build 2 cubes with a size of 4, 0.9 and 10. Name them obstacle and add them as child objects of the environment game object. Then move them somewhere close to our player and separate them, leaving just a small gap in between them. I'll give this tool the red folder texture 04 material. And that's our base map created. Feel free to close or dock the tab somewhere else if you want to. If you don't want to close the Pro Builder window, make sure the Object Selection option is selected. We are all set, but before we go ahead and start coding, I think it's best for you to learn about states and state machines first. When opening up and loading a game, the first thing you might notice is that our player is idling. This is what we call a state. In this example, the current player state is the idling state. If we were to move, let's say by pressing W, our player will start running. Running is yet another player state. We've simply changed or transitioned from the idling state to the running state by pressing a movement key. This gives us 2 states, idling and running. Both of these states are implemented as their own classes with their own logic. This means that the idling state doesn't care about what the running state does, but only that it shall transition to it whenever we press a movement key, like W. The running state is the one that takes care of giving the player some desired speed. However, that transition needs to somehow happen, and the current state logic needs to somehow run as well. That's what state machines are for. They hold the current state, a method to change that current state, and if the state isn't public, one or more methods to run its logic. This brings us to one of the state machine system advantages. Each state has its own logic. An example on why this is a good thing is a typical jumping and being grounded. Let's have an imaginary situation where our player is idling. Whenever we press on the space key, our player should jump. One common problem when doing this without state machines is that if we keep on pressing the space key, our player will keep on jumping. The common way of fixing this problem is by adding an isGrounded check. If when the player presses space there is ground right underneath the player, then the player can jump. Otherwise, our player shouldn't be able to jump. While this is alright, not only are the idling logic and the jumping logic in the same script, the jump is also caring about whether we are grounded or not, while it should only care about adding an upwards force. However, let's take a look at the same example using states and state machines. In our idling state, we have the logic of transitioning to the jumping state whenever we press the space key. When we do so, the state machine changes the current state to the jumping state. In the jumping state, the only logic we have is to jump upwards. There is no logic telling us that we should jump whenever we press space. This simply means that our player won't keep jumping if we keep on pressing space. Of course, if we did want to double or triple jump, we will simply add a count of used jumps and add a new upwards force whenever we pressed space. Something to note as well is that we do not need to check whether the player is grounded or not. The reason for that is quite simple. Our player can only be idling when it is in the ground, as otherwise our player will be in another state like falling. One other big advantage is that it's quite easy to add, remove or change a state. With one or a few scripts, we will have multiple states tangled within each other, and it can be a bit of a mess to add or remove an existing state, at least if you end up having quite a lot of them. With state machines, we add a new one by creating a new class and add its own logic to that class, and we can change the state implementation by updating that isolated logic. To remove one, we simply remove the file, the state transitions and whatever code was necessary for that transition. This does, however, bring us to a disadvantage. Each state is its own file. If we end up having 200 states, we'll end up having 200 files. This can easily add up a lot of files, which makes it harder to keep things organized. However, it does sound better to me than having those 200 states in just a few files. Another disadvantage is that the player can only be in one state at a time. If we are moving, then we can't be shooting, for example. Or if we are shooting, then we can't be moving. The first fix you might think is to have the movement logic in the shooting state, so that you can shoot and move at the same time. This works, but shooting shouldn't really be related to moving as they are two complete different systems, although it's fine if you decide it to be that way. The actual fix though is quite simple. Simply create two state machines. This means that you'll have a state machine for movement and a state machine for combat, which allows you to be in two states at the same time in case that's what you desire. As far as I know, we can't move while attacking in Genshin, so they either do it in the same state machine or disable the other one. One last disadvantage is that state classes do not inherit from the monoBehavior class. This means that we cannot add them as components in our inspector, which also means that any variable we want to set in the inspector needs to be done through another script. An example of this would be having a player script that holds all of that data and then passes that data to the state machines and their states. Furthermore, because we need access to those variables, We'll either need to make them public or somehow reference them by passing in every single variable. To keep things as simple as possible, we'll be making each variable a public property, and alternate between private, omitted and public setters. Now that we have an idea on what states and state machines are, let's take a look at what states our player will end up having for our base movement system. Our very first state will of course be the idling state. As we've seen before, it's a simple state where the player stands still. From the idling state we can start moving. In Genshin Impact, this is the equivalent of 3 states: walking, running, and sprinting. The main difference between these states is the speed at what the player moves at. In Genshin Impact, however, we can't directly go from idling to sprinting, but instead need to go to dashing first. Dashing is a low time but faster movement speed state. When we stop movement in any of these 4 states, they will transition to 3 other states: light, medium, and hard stopping. These simply decelerate the player until it comes to a stop, then transitioning to the idling state. We have 2 last states, which are the jumping and light landing. Jumping is a simple upward force, while light landing happens when the player falls from a small height. There are 2 other landing states that will be introduced with the gliding system, as we'll also introduce falling there, but for now this one suffices. These are all of the states we'll be needing for our base movement system. We, however, can go a bit further. Each one of these states can be part of a group, and by group I basically mean inherit from a base class that groups common logic. This is what's called hierarchical state machines. Much like state machines though, there are several ways you can use them, so if you ever watch another video, it's quite possible that they will have a different implementation than mine. But we'll go with the simplest of them all, which is state inheritance. To make things easier, we'll start grouping states from the bottom to the top. The first states we want to consider are walking, running, and sprinting. These states can be considered moving states, as they are states the player will be when moving. With that same logic, our light, medium, and hard stopping states can be considered stopping states. While there's only one of them right now, our light landing state can also be considered a landing state. All of our current states, besides the jumping state, are states that the player will be when he is on the ground. This means that we can group all of them into a grounded state. Following the same logic, our jumping state can be grouped into a state for when the player is in the air, which we'll be calling an airborne state. As we already know, the movement system is the base of the other 3 systems. The reason why is because gliding and swimming all use the same movement but with different settings. This means that we can group every existing state into a base state, to which we'll call movement state. This will simply take care of moving our player around. And this is how our state hierarchy will look like. As I've said before, each of these states will have to run their own logic. This means that every single one of them needs to have common methods that run that logic. Because of that, we'll be defining an interface that defines those methods and implement that interface into our base state. Because every other state will end up inheriting from our base state, they will be able to use those methods and also override them with their own logic. To create that interface, we'll go into Unity and create a new folder named Scripts in the Assets folder. Inside of this new folder, we'll create yet another one named State Machine. Here we can now create a new C# script by right-clicking in the project window and going to Create C# script. I'll name mine High State. Open it up and start by removing the default methods and the mono behavior inheritance as well. To make it an interface, simply swap the class keyword with interface instead. There are a few methods in state machines that people commonly use. The first two are a simple enter and exit methods. The logic in these methods is supposed to run whenever we transition from a state to another. Enter will run whenever this state becomes the current player state. Exit is the opposite and will run whenever this state becomes the previous player state. This is good for setting and resetting data whenever we enter or exit a state. Let's then define a method for each of these. To do that, simply type in public void enter and public void exit. Remember, we are only defining the methods here and not implementing them. If you did want an implementation, you will likely use an abstract class instead. It does seem that Unity 2021 does support C#8, which supports default interface methods. But I'm not entirely sure what's the line between abstract classes and interfaces in that case. Regardless, we now have two method definitions. Of course, we can't really run any constantly ongoing logic with these two methods. For that logic, we often have three other methods. Handle input, which will allow us to run any logic regarding reading input. Update, which will allow us to run any non-physics related logic. And physics update, which will allow us to run our physics related logic. You are likely familiar with the update and physics update methods, which are the equivalent of the monobehavior update and fixed update methods. The only new one here is the handle input method, which is us simply separating it from the update method. We'll be adding a few more methods here as we need them, but these will work fine for now. That's our state interface done, so now we'll be creating our base state machine. We'll be using an abstract class. So back into Unity, in the exact same folder, create a new C# script. I'll name it state machine. Open it up and remove the default methods and the monobehavior inheritance. To make this an abstract class, we simply need to type in abstract before the class keyword. We'll start by creating the variable that will hold the current state. To do that, type in protected iState current state. Note that this is the class that every state machine we create will inherit from, so we don't want the current player state, but the current state of the context we are getting it from. Protected is here to make it accessible in classes that inherit from this one. We now need a few things. The first one is a method that allows us to change the state machine current state for another state. The second one, because our current state variable isn't public, are methods that access the current state logic methods. If you don't understand why, don't worry, you'll do later. Simply put though, we'll need them so that we can call them from the monobehavior methods. Let's start with the first one by typing in public void change state. We'll pass in iState new state as a parameter. What we need to do here is quite simple. We'll start by calling in currentState.exit. This resets any data that needs to be reset before changing states. Then we set the current state to be the new state. When that's done, we call in currentState.enter. This will set any data that needs to be set on the new state. That's really all we need to change states. However, we currently have a problem. Because this will need to be called once to set the initial state, our current state variable will be null. This of course means that our exit method won't be called as it will throw an error, as null does not contain an exit method. The simplest fix for that is to add an if statement checking if the current state is null, and if it isn't, we can then call in the exit method. C# however has an AND operator, which is a null conditional operator. Its use is quite simple. Simply add a question mark right after the code that can return null. In this case, we add it right after the current state. Now, if current state returns null, C# will not call the exit method. Our enter method doesn't need it as our current state is set to the new state right before we call it. It will throw an error if you were to pass in a null new state, but you probably want to know if that is the case. That finishes up our changeState method. We shall now create a method for each of our stateLogic methods. To do that, start by typing in public void handle input, and inside call in currentState dot handle input. That's all we need to do, so duplicate this method twice and swap the name with update and physics update. We now have a way to call the currentState from a monoBehavior class, so our base state machine is done. With our abstract class done, we can now create our player movement state machine. This state machine will of course take care of all of the player movement states. To create it, in Unity, go back to the scripts folder and create a new folder named characters. Then inside create another one named player. Inside of that player folder, we'll have yet another folder named state machines, followed by another folder named movement. In there, create a new C# script to which I'll name player movement state machine. Open it up and remove the default methods and swap the monoBehavior inheritance with state machine instead. This state machine can now be used to change between player movement states and run their logic. Of course, we don't really have any state yet as we still need to create them. Before we do that though, let's first take a look at the differences between caching states or instantiating new states. Whenever we call our changeState method, we need to pass in our new state. We can do this by either creating a new instance of the newState class every time we change states, or create it once and cache that instance in our state machine. Creating a new instance every time we change states ensures that if a state isn't being used, resources won't be wasted unnecessarily, as it will be removed. Caching the instance will always have resources like memory being used, as the instance is still needed and won't be automatically removed, but you won't need to instantiate new states every time. One thing to note here as well is that creating a new instance always creates the variables again, so their values will be reset to their initial default values, while caching the instance will always have them the way they were, although I don't think it will matter for us too much. Now, which we should use depends in our use case. When a state will be entered quite a lot, then caching it might be a good idea. Let's take the example of the player jumping. It's extremely common for someone to keep pressing the jump button while roaming around the map. This means that the player state will be changed to the jumping state quite a lot, which makes it a good reason to cache that state instead of instantiating it every time. Now let's take an example of an NPC which has 2 or 3 states that only get changed every 30 minutes. For example, one will be idling, another one will be walking around, and another one will be talking with another NPC. Because they only change every so often, there isn't much reason to keep them cached, and will probably be better for us to create a new instance at every state change, or every 30 minutes. This will also make it if there were 100 NPCs in the map, we wouldn't have 300 states cached in, although we would have 100 states being instantiated every 30 minutes. Of course, you can mix both usages if you prefer. For our player, however, we'll be caching in all of our states. Now that we know that, let's start by creating our first movement states. We'll start with the moving states without the group state, but including the idling state, and the movement state as well, as that will be our base state. So, back in Unity, in the same folder, create a new folder named states. Inside, we'll create a new C# script to which I'll name player movement state. When that's done, create another folder named grounded for our grounded states. Inside, create a new C# script named player idling state. When you are done doing that, create yet another folder named Moving for our moving states. Inside, we'll create 3 new C# scripts: player walking state, player running state, and player sprinting state. When you are done creating them, go back to folders and open up the player movement state script. Remove the default methods and swap the monobehavior inheritance with an iState interface implementation. If you are using an IDE, it should show an error that says that we should implement the interface methods. So I'll press Alt-Enter and implement them. To make it easier for us to know what state the player is currently in, we'll log the current state class name in the enter method. To do that, type in debug.log and pass in state concatenated with getType.name. This will show the name of the correct class type. Other options like typeof or nameof will always show the parent class name. When that's done, we want to make sure we can override these methods with their own logic in each state. So we'll need to add the virtual keyword to every single one of the methods. Then we'll open up all of the other 4 states we have created and remove their default methods, making sure we swap their inheritance from monobehavior to player movement state as well. We now have our initial states, so we can start caching them. To do that, head back to the player movement state machine script. Remember that we'll only need to cache in states that are not considered group states. This is because the player will never be in the player movement state, but instead on the idling state or running state, as the movement state simply exists to group common logic. So start by typing in public player idling state. I'll make it a property with an omita set. In case you are wondering, here are the differences between writing private set or simply omitting the set. If you don't want to think about it, simply make it private for all properties that don't use a public set. Duplicate this property 3 times and swap their names to be walking, running, and sprinting. We now of course need to instantiate each one of them, so create a constructor by typing in public player movement state machine, and inside simply type in idling state equals to new player idling state. Do the same thing for all of the other 3 states. Our states are now cached. That's great, but you have likely noticed we aren't yet calling any of the state methods in any monobehavior class, which means their logic will never run when we start playing the game. To do that, we need to first create that monobehavior class. So, back in Unity, go all the way back to the player folder and create a new C# script. I'll name it player. Opening it up, remove the default methods. All we need to do now is to create an instance of our state machine and call its methods. To do that, create a new private variable of type player movement state machine, to which I'll name movement state machine. We now have the constructor, change state, and the input, update, and physics update methods to call. We'll call them in the awake method, the start method, the update method, and the fixed update method. In the awake method, we'll need to create a new instance of our state machine. So type in movement state machine equals to new player movement state machine. In the start method, we need to define the player starting state. We'll start our player in the idling state. To do that, type in movement state machine dot change state and pass in movement state machine dot idling state. Our player shall now enter the idling state whenever the game starts. In the update method, we'll need to handle our input and run our non-physics related logic. So call in movement state machine dot handle input and movement state machine dot update. The order is important as we want to make sure we've got our input data updated before we do anything with it in the update method. In the fixed update method, we'll need to run our physics related logic, so call in movement state machine dot physics update. We are now running our current state logic through our player script. Of course, this will never happen unless we add this script as a component of the player. So head back into Unity, select the player game object, and add the player script as a new component. If we now go ahead and enter play mode, a debug.log shall be called saying that the player is in the idling state. We are now able to run our state logic, but of course we don't still have any. Before we go ahead and start adding some logic though, we first need to create our player input. The reason why is that we are using the new input system, so we'll need to create the player input ourselves. Thankfully, it's quite simple to do that. Let's start by creating a folder in our assets folder, which I'll name input actions. Inside, we'll create two new folders, one inside of the other. Characters, and then player. Inside the player folder, we'll create its input actions by right-clicking in the project window, going to create, and input actions at the very bottom. I'll name them player input actions. When you are done doing that, double-click on the asset file to open up the input actions window or press on the edit asset button. I'll dock the window right next to the game tab. Now, if you have never used a new input system, you likely have no idea what is what. While I won't do a deep dive into what each option does, I'll at least try to explain what we need to know for this tutorial. The first thing we want to create is what Unity calls an action map. This is nothing more than a group of inputs. You can divide your inputs in whatever way you desire, but we'll create a player action map that groups every player input. So let's go ahead and press on the plus icon, which has a new action map. I'll name it player. When we select an action map, Unity shows us the existing inputs known as actions of that action map at the right side. It should come with a default action already, but feel free to right click on it and press delete. Right now we'll only be needing two inputs. One is for our movement, which will be making it be our WASD keys. And the other one will be to toggle between our walk or run states, which will be bound to the left control key. To do that, press the plus icon and name the first one movement. Then press it again and name the second one walk toggle. Select the movement action again. At the right side, we now have a properties area for the currently selected action. This area allows us to choose a few things, such as the type of value that we want our input to return, what type of interaction is needed for the input to be called, and if we want to process that data, such as clump the returned value. For our movement input, we want it to be constantly reading for changes, so that we can get an updated value in our handle input method. The way we do that is by setting the action type to value. The value type is an action type that continuously tracks changes on that action. This is different from the button action type that only tracks changes whenever we press or unpress an input. Now we want our movement input to return something that we can use to move horizontally. If you have ever used the old input system, that would be the get axis or get axis raw of the horizontal and vertical axis, in which you will then set the vertical axis value to move on the Z axis, as X and Z are our player horizontal axis in 3D. So all we need here is a vector 2, as it holds the two values we need. We can choose that return value type in the control type dropdown. We now have the type of input and value we want to receive. However, we haven't really set any key to this action. To do that, we use bindings. When creating an action, Unity already has a default binding to it with no key attached. However, we want our movement input to be the WASD keys. Currently, our binding is just one key, so we can't do that. Thankfully, there are other binding types depending on the chosen action type. So go ahead and right-click in the current movement binding and delete it. Then press on the plus icon at the right side of the action and choose Add to the Vector Composite. I'll name it Keyboard. This now allows us to bind one key for each direction. To bind a key, we need to use the Path dropdown. This has quite a lot of keys to choose from, and you could go ahead and go to Keyboard and search for the key you want. However, we'll do something simpler and faster, and that's to listen for our own input. If we go ahead and press listen and then press W in our keyboard, an option saying W keyboard shall now appear. Go ahead and select that one. Our up direction is now bound to the W key. All we need now is to do the exact same thing for our other three directions, so go ahead and do just that. Just in case you didn't understand, binding a key to a direction here means that W, for example, will get the value of up, which is 1 in the Z axis, which of course in our vector 2 will be 1 in the Y variable. If we press, let's say, WD, then we'll get a value in the X and in the Y variables of the vector 2, and that value will already be normalized, as in our keyboard binding we have the digital normalized mode selected. That's it for our movement input, so let's now do our walk toggle. In Genshin, whenever we are walking or running, we can switch between both by pressing the Ctrl key. This input is reading like a button, waiting for us to press on it and nothing else. There is no reason for us to continuously track this input value, as we don't really need to use it anywhere else, besides when switching between these two states. Because of that, we'll choose the button action type. For our binding, we'll be listening for the left control key and choose it. We now have the necessary inputs to start moving, so all we need to do now is to save them and somehow read them. To save these input actions, simply press on the Save Asset button above. If you wanted every change you do to automatically save, then you would enable the autosave at the right. I will however not do that. We now have our inputs saved, but we still need a way to access them. If we select the Input Actions asset file, we can see in the inspector that we have an option to generate a C# class. This class is automatically generated by Unity and provides us a way to access these input actions we have just created, so feel free to enable it. Now, there are a few fields you can update, but we'll leave everything to their default values and instead just press Apply. This should create a new C# script in the same folder with the same name as our input actions asset file, as well as automatically generate code of our action maps and actions, including their bindings, properties, etc. That's great, but we of course still need an instance of this class to be able to use it. To do that, we'll create our own player input class. So go back to the player scripts folder. In here, create a new folder named Utilities, followed by Input. Inside, we'll create a new C# script to which I'll name Player Input. Open it up and start by removing the default methods. We'll leave the monobehavior inheritance as we'll need it later. We need a few things to start using our input actions. The first is of course an instance of our player input actions class. To do that, create a new public property of type player input actions, which I'll name input actions. I'll give it a private set. I'll also create a reference for our player action map so that we can access it right away. To do that, type in public player input actions, which is our generated C# class dot player actions. I'll name it player actions as our action map is named player. The dot player actions we've added is automatically generated by Unity and represents the struct type of our player action map. If you've named your action map something different, then it should be your action map name with actions attached to it at the end. With that done, we can start by creating a new instance of our input actions. We'll do that in the awake method. In here, simply type in input actions equals to new player input actions. Then set our player actions to be equal to input actions.player. Note that while player actions is the name of the action map struct type, player is the name of the variable of the struct type. We now have a reference for our inputs, but there is a mistake I see some people make quite often, which is trying to read their inputs now. While we indeed have an instance of our player actions, Unity requires us to first enable them. To do that, we'll use the monobehavior onEnable method and also the onDisable method to disable them, as we don't want them to be enabled if the player game object is no longer enabled. So add in the onEnable method and inside type in input actions.enable. Then add the onDisable method and call in input actions.disable. We are now able to read our inputs. Of course, we still need to add this class as a component of the player, but we'll also need to add a reference to it in our player script, so that we can access it in our states. So go back to our player script. In here, start by creating a new public property of type player input. I'll name it input. Make sure you type the same property set as I do, but I'll most of the time make it private unless we need to be able to set the value from other classes. Then in the awake method we'll get its reference by typing in input equals get component of type player input. We can now add this player input class as a component of our player, but let's first add the required component attribute. Above of our player class, type in required component type of player input. Now every time we add a player component to a game object, it will automatically add the player input component with it as well. Save and go back to Unity and select the player game object. If Unity didn't add the player input as a component automatically, add a new component of its type yourself. We are now able to read input through our player input class, which makes it almost possible for us to start moving our player. Almost, because we still need to set a few small things before we are able to do it. The first one is of course adding a rigid body. Without it, our physics-based movement won't work. That's quite simple to do. We just select our player game object and add a new component of type rigid body. You could of course use the required component here as well if you'd like. We now have a rigid body, which means our player can move using physics, but it also needs a collider. This is because if we go ahead and enter play mode, our player will start falling due to gravity but won't collide with the ground. To add one, exit play mode and add a new capsule collider component to the player. If we inspect the player, we can see that our capsule collider is more like a sphere. The reason why is that we are not adding it to the character model but to an empty game object, which doesn't really have a defined size. We'll have to get the character model height ourselves and then define the values of this capsule collider. The way we know our character model size is by using its mesh renderer bound size variable. I've already got it myself and I know that my character model has a height of 1.8. So we'll select the player game object again and give our capsule collider a height of 1.8. Of course, we do have a new problem here, which is the capsule collider being halfway into the ground. That's actually correct as it's centered in the origin, but because we need it to fit our character model, instead of moving the character model object down, we'll update the center of our capsule collider to go up. We simply need it to go up half of the height of the collider, which is 0.9. It should now be in the correct height, but it's still looking quite thick, so let's lower the radius to be around 0.2. If we now enter play mode, our player should no longer fall through the ground. Of course, if we were to rotate it a bit, which can also happen when we collide with another object, it will fall as we are not restricting any rotations. To fix that, exit play mode and in the rigid body component, open up the constraints area and freeze all rotations. We'll also set interpolate to interpolate and collision detection to continuous for our player. Interpolation removes some possible jittering, while collision detection makes it so our player detects other colliders better, which makes it less likely to go through those colliders. These are recommended to use on your player, but most often only there as they are less performant. That's basically it, but we'll need a reference of our rigid body to be able to use it. So go to the player script, and when you are here, add a new public property of type rigid body, to which I'll name rigid body. I'll give it a private set. Then in the awake method, type in rigid body equals to get component of type rigid body. We now have every required component to move our player, but we don't really have a way to access that player in our states. Thankfully, that's quite easy to do as we just need to pass in our player to the state machine constructor. We have two options here. Pass it in into the state machine and then into each state, which makes it so we can access a variable right away, or leave it in the state machine itself so that we can access to the state machine variable. I don't really see any worthy advantage in any of them besides in one not needing to type in state machine before the player variable, and in the other one not needing to pass in the player to the state's constructors. Other than that, it should really be the same. I'll leave the player reference in the state machine as I'm going to use a state machine to load reusable data. So, in the player script, go to the state machine initialization and pass in this, which represents the player class. Then, in Visual Studio, I'll press Alt-Enter and choose Add Parameter to Player Movement State Machine. Our Movement State Machine constructor shall now have a player parameter. Next, create a public property above of type player, to which I'll name player. I'll omit the set as well. When that's done, in the constructor, set this player to be the player parameter. Our state machine can now reference the player, but states don't yet have a reference to our state machine. To do that, let's first go to our movement state. In here, add a constructor for this class by typing in public player movement state and accept a parameter of type player movement state machine named player movement state machine. Then create a protected variable above of type player movement state machine named state machine. When that's done, simply set it in our constructor to be the parameter. We now need to generate a constructor for each of our states that inherit from this one. We'll actually do that by going back to our state machine and pass in this for each of the constructors. When you are done doing that, press Alt-Enter and choose Generate Constructor in State. Do it for all of the 4 states. With that done, we are finally ready to start moving our player. Our movement logic will stay at the player movement state base class. So start by opening it up. The first thing we want to do is to read the player movement input. We'll save the input value into a variable, so above create a new protected variable of type vector2, which is our input action control type, and I'll name it movement input. Then we'll set its value in our handleInput method, so in there call in a new method named readMovementInput. For organization purposes, I'll be adding this method to a new region named mainMethods. I'll go ahead and also add the other methods to a new region named iStateMethods. You don't need to do this if you don't want to, or if you are not using Visual Studio, it's possible that you can't do it. In this new method, we'll read our input by typing in movement input equals to statemachine.player.input.playerActions, which gets our action map. Through this action map, we can get our actions. Our movement input was named movement, so type in .movement. And to read its value, we use the .readValue method. This method accepts the type of the value we are trying to read, which in our case is the vector2 type. When that's done, let's go to our physicsUpdate method and call in a new method named move. I'll also add it to the mainMethods region. Inside, start by checking if movementInput equals vector2.0. If that's the case, we return as it means we aren't moving. We can now start moving our player in case there is any input. The way we'll do that is quite simple. Whenever there is input, we'll add a force to our player rigid body towards that direction, at a certain speed. We are already reading our input, so let's also create a variable that holds our speed value. So above, create two new variables. Protected float base speed, defaulted to 5f, and protected float speed modifier, defaulted to 1f. This second variable makes it so we can edit our speed without modifying the base speed. Back to our move method, add to the if statement or speed modifier equals 0. We can now add a force to our player. To make it more understandable, I'll be creating a new vector tree named movement direction and set it to be equal to a new method named getMovementInputDirection. We'll be returning a new vector tree which simply holds the value of our movement input y variable in the z axis. So type in return new vector tree movementinput.x 0f movementinput.y. I'll also be making this method protected and I'll add it to a new region named reusable methods. We now have our movement input in 3D coordinates, as x and z are our 3D horizontal axes. Back to our move method, we'll now get our movement speed by typing in float movement speed equals to get movement speed. Inside, we'll simply return base speed multiplied by speed modifier. I'll also make it protected and add it to the reusable methods region. All that's left to do now is to add a force for our player to move. Now, commonly what I see in other tutorials is people setting the rigid body velocity variable right away. However, when going into Unity's documentation, they do not recommend doing that and recommend using add force instead. From my experience while doing this system, I found that while that works, I did need to set the velocity variable sometimes. The reason why was because adding a force isn't instantaneous and will only happen in the next physics update, while setting the velocity right away will be an instant change of the force. We'll understand more on the reason why when we get there, but we'll be using the velocity when resetting our velocity or whenever we can have more than one add force running at the same time, and use add force for the remaining forces, as so far it seems to work fine. That of course means our movement will use the add force method. So in our move method, under our movement speed variable, type in statemachine.player.resheetBody.addForce. For the force, we'll pass in movement direction multiplied by movement speed. This adds a force, but right now by default, Unity is adding a force mode of force, which isn't really what we want. If we take a look at a nice image made by Nothkey that was posted on Reddit, we see that the force mode not only depends on time, but it's also dependent on our player mass. We don't really want that. Besides not caring about our player mass, we don't want it to be time dependent either. We need an instant force that moves our player at the same speed at the start or middle of the input, which leads us to the force mode known as velocity change. Just like it says in the formula, this is the same as velocity plus equals force, which is almost the same as using our velocity variable to add a force, but of course using the add force method, which gets called in the physics update. Note that this is a 3D force mode, and as far as I know, this one doesn't exist in 2D, so it's quite possible you'll need to use the velocity variable instead. To note that it's also apparently not recommended to use delta time while setting a velocity. Now that we know that, pass in force mode.velocityChange as the second parameter of the addForce method. It might seem that we are done, but remember that the addForce method adds a force to the already existing force. This means that if we move our player and don't stop pressing our input keys, our player will become Speedy Gonzales. To fix that problem, we simply need to remove the existing velocity from the force we are going to be adding. To do that, type in just before adding the force, vector3, current player horizontal velocity equals to get player horizontal velocity. Inside of this new method, create a new vector3 named player horizontal velocity and set it to be statemachine.player.resheetBody.velocity. Then set the player horizontal velocity.y to be 0f and return the variable at the end. I'll also make this method protected and add it to the reusable methods Recentering. Back to our move method, subtract this horizontal velocity from our force. If we save and go back to Unity, entering play mode should have our player moving at a constant speed. Remember that we don't need to normalize our input through code, as the input action already does that automatically for us. That's the base of our player movement done. But just as a small tip, let's say we were to add another float to our addForce multiplication. While this might seem normal at first glance, because our first variable in the multiplication is a vector, it means that it will multiply with movement speed and return another vector, and then multiply with this new variable, which also returns a vector. The problem here is that we are doing two vector multiplications, which are less performant than normal multiplications. If we were, for example, to swap the order and make our vector the last variable, we will now multiply the new float with movement speed, which will just be a normal float multiplication, and only then multiply by our vector, which will be a vector multiplication. We now have one vector multiplication only instead of two, which means it's more optimized. This can be a problem when you are calling the multiplication multiple times, like we are doing for our addForce. It will be even worse if it was in the update method, as it's called once per frame. Adding the vector as the last value of the multiplication basically ensures you only have one vector multiplication, unless of course you have more vectors in the formula. In our example, we will now have 10 vector multiplications instead of 20 in 10 calls just by swapping the order. This doesn't really matter for our system as we are only multiplying by one value, but it might be a nice thing for you to keep in mind in case you ever multiply vectors by multiple float values. In our case though, we can leave the current order. With that, we got the base of our movement done. But if we take a look at Genshin Impact, we quickly notice that this isn't how movement works there. Not only does the player rotate towards the movement direction, that movement direction is relative to the camera and not to the input. If we press W to move forwards, we'll always move forwards towards where we are looking at. That also means that if we press S, we'll move backwards or to the opposite of where we are looking at. To be able to do the same, we need to create a camera system. Thankfully for us, we are going to be using Cinemachine, which easily allows us to add one. This seems to be what Genshin Impact uses as well. We have already downloaded it when setting up the project, so we can now easily create our camera by right-clicking in the hierarchy window and going to Cinemachine Virtual Camera. I'll name it Player Camera. While I was able to somewhat replicate Genshin Camera with a free look camera, there was a missing option that we will need to add ourselves, and apparently virtual cameras are more performant as they only use one rig, while free look cameras use 3. To start off with our camera, we need a target for the follow and look at fields. Follow is the target that our camera will follow around. Look at is a target that our aim will be relative to. By relative here, I mean that the center of our aim will always be on the target. To add this, select our player game object and add a new child game object named Camera Look Point. I'll add an icon to this game object so that we can easily see where it is placed. Then I'll make its y-axis be at 1.4. When that's done, we'll set our camera targets to be this new object. So back into our player camera, drag this new game object to the follow and look at fields. Note that Cinemachine should add a Cinemachine brain to your main camera automatically, but if it didn't, make sure you do it yourself. This simply makes it so Cinemachine cameras can control your main camera. Our camera is now looking towards our camera look point, but is still using the old input system, so our current mouse input won't work. Thankfully, it's quite simple to swap it with a new input system, as all that we need to do is to add a new component named Cinemachine Input Provider. This component accepts an X-Y axis, which will represent the camera rotation, and a Z axis, which will represent the distance. Of course, to assign an input here we need to create it first. So go ahead and open up the Input Actions window. In here, let's first create a new action for our mouse movement by pressing on the plus icon and naming it Look. For our types, we'll have it to be a value of vector 2 as we want to constantly get our X and Y axis. In its binding, select Mouse Delta. Delta is apparently the change in pixels in vector 2 since the last rendered frame mouse position. For our zoom, we'll add another action named Zoom and set it to value as well. We simply want a float here to know whether we are scrolling up or down. The value type for float is called axis. Now we'll use the value this input returns to know how much we should scroll up or down, but it currently comes with high values such as 120, so we'll clamp it to a lower value. To do that, add a processor of type clamp and set it to be from -0.1 to 0.1. This input also comes inverted, which means scrolling up will return positive and scrolling down will return negative. We want the opposite of that, so add yet another processor, but this time of type invert. When that's done, set its binding to be mouse scroll Y. Then save the asset. Back in our player camera, in the input provider component, select the corresponding inputs. So look for the XY axis and then zoom for the Z axis. We are now using the new input system for our camera. We are only a few settings away of having our camera behaving like Genshin's camera. The first thing we'll be doing is set our FOV to 60. The next thing is setting both the camera body and aim. The body sets the algorithm that the camera uses to follow its target. The aim sets the algorithm that the camera uses to look at its target. If we take a look at Genshin Impact camera, we can see that we can rotate around the target. In the free look camera, this is known as an orbital transposer. However, in the virtual camera, the orbital transposer does not contain a vertical rotation, but only horizontal. Thankfully, we can imitate the free look camera setting using the framing transposer body together with the POV aim. The framing transposer tries to keep the camera center to the follow object at the provided distance. The POV aim moves the camera according to your input, which should translate to where you are looking at relative to the look at target. If we enter play mode, our camera should have the same orbital behavior that Genshin Impact camera offers. However, there are a few problems. Besides the camera movement being too fast, the faster you move your mouse around, the slower the movement gets. What we want here is for the camera sensitivity to be as close to the mouse speed as possible. To fix that problem, open up the aim area and swap both inputs from max speed to input value gain. Make sure your vertical axis also has the inverted option enabled, as otherwise we'll be rotating towards the opposite vertical direction. Next, we'll set the speed on the vertical axis to be 0.1 and on the horizontal axis to be 0.16, as Genshin camera has a faster horizontal movement. If we now move our camera around, it should be slower and also have a closer one-to-one sensitivity with our mouse. If you wanted a fully one-to-one sensitivity, then you will need to set the speed to 1. There still are some problems left to resolve. One example is our vertical axis, as we aren't able to rotate 90 degrees up or down. That's solvable by updating the value range field from the vertical axis. We'll set it to be from -90 to 90. For our horizontal axis, we'll go with 0 to 360. I'm not entirely sure if we actually need this one, but I'll leave it as is to make sure nothing breaks. I'll also enable wrap to allow the camera to keep rotating once we get to the 360 degree rotation, as otherwise it will stop there and we will need to move the camera back. The next thing is that if you start moving your camera around and stop it, you might notice something. The acceleration and deceleration of the camera are instantaneous. In Genshin Impact, however, there is a small acceleration and deceleration. We can easily set that up by updating the vertical and horizontal axis, axle time, and decel time fields. For the vertical axis, we'll go with 0.8 acceleration and 0.05 deceleration time. For the horizontal axis, we'll also go with 0.8 acceleration but 0.25 deceleration time. Our camera shall now start or stop a bit slower. I'm not really sure what the recenter target does here, but I have mine set to follow target forward, and it works fine, so I'll add it here as well. In this case, it seems to be the same as the look one because both have the same target, but I don't really know what these axis angles are relative to target means. I'm assuming it has something to do with the vertical and horizontal recentering, and that it recenters relative to that target, but I'm not completely sure. If you do know, please leave a comment below explaining it so that we know what it actually does. This horizontal recentering option is what free-look cameras don't provide us with, but we'll only need this quite a bit later, so leave it disabled for now. For our body, we'll be setting both the X dumping to be 0.2 and the Y dumping to be around 0.4. Damping is how fast or slow the camera tries to keep itself centered with a target, which in this case should be the follow target. While we won't be needing to set this here, I'll also go ahead and set the camera distance to 6. We now have a camera working quite nicely, but we still need 2 more things to take care of. The first one is that currently our camera goes through the ground instead of colliding with it. The second one is that we can't yet zoom in or zoom out. Thankfully, both are quite easy to do. Let's start by exiting play mode. For the camera collisions, go to the bottom of the Scene Machine component and open up the Add Extension dropdown. There should be an option named Scene Machine Collider. Feel free to press on it. This should add a new component to our camera object that allows us to set collisions with the camera. What we want here is to set the collide against layer to something to collide with. To do that, we'll create a layer for our environment so that the camera collides with every existing environment instead of just the ground. So add in a new layer named Environment. Then go to all of our environment cam objects besides the water and set their layer as environment. When that's done, go back to the camera and now set the collide against to environment and remove the default layer from there. For the ignore tag, we'll set it to player. Of course, we need to add this tag to the player, so select its game object and add the player tag. Next, back into our camera, we'll be changing the strategy of the camera collider. This is simply how the camera behaves when colliding with something. In our case, we want the camera to pull forward when we collide with the environment, which simply pulls the camera to the front of the collider. I'll leave the rest with its default values, but feel free to change them if you want to. If we enter play mode, our camera collisions should be working. That means that all that's left is our camera zoom. Unfortunately, I don't think there is a built-in functionality for this, so we'll have to do it ourselves. Thankfully, with the input provider, set axis and the body camera distance, this is quite simple to achieve. That's because the input provider set axis gives us a value of when we scroll our mouse wheel, while the camera distance is how far we are from the target. So go back to the scripts folder and create a new folder named camera. Inside we'll create a new C# script to which I'll name camera zoom. When you are done creating it, add it as a component of our player camera. Then open it up and remove the default methods. We'll start by creating 3 variables: the default distance that the camera will start at, and the minimum and maximum distance that the camera can go to. So type in serialize field, private, float, default distance, and default it to 6f. Then duplicate the variable line twice and swap default with minimum, and then default with maximum. I'll set their default values to 1f and 6f respectively. We'll also make it so we can update these variables with a slider. So to do that, simply add in after the serialized field attribute range from 0f to 10f, meaning we can choose a value from 0 to 10 through a slider. Next, we'll add two more variables, a value to smooth our distance lerp and a value to multiply our set axis value with. So duplicate one of the variables above twice and then change the first one to be named smoothing and the second one to be zoom sensitivity. I'll default the smoothing to 4f and the zoom sensitivity to 1f. That's all the data we need to be able to set in the inspector. So now we need two more things. A reference to the scene machine framing transposer, which represents our body, and a reference to the scene machine input provider, which contains our set access value. So create a new private variable of type scene machine framing transposer named framing transposer. Make sure you import the scene machine namespace. Then create another private variable of type scene machine input provider named input provider. To get their references, we'll use the getComponent method, so type in awake, and inside type in framing transposer equals to getComponent of type scene machine virtual camera, which gets our virtual camera. We'll now get our framing transposer by using the .getSceneMachineComponent method instead. For the type, we'll of course pass in scene machine framing transposer. We use the getSceneMachineComponent method here because the body is part of the scene machine component. For our provider, type in input provider equals to getComponent of type scene machine input provider. When that's done, call in the monoBehaviorUpdate method and call in a new method named zoom. We can now start zooming our camera. The way we'll do that is by retrieving the value of our scroll, which we can do from the input provider set axis. To do that, type in float zoom value equals to input provider dot get axis value. Here we need to pass in an axis index, which is the index of 2 for the set axis. Then we multiply this value by our zoom sensitivity. We now need to add this value to our current distance target, which we currently have no variable of. So above, create a new private float named current target distance. This will start with a default value of 0, but we want it to start with a default distance. So in the awake method, type in current target distance equals to default distance. Then back in our zoom method, type in current target distance equals to current target distance plus zoom value. We need to make sure we clamp this target distance to not pass our maximum distance, so add in matf.clamp surrounding our assignment, and then pass in minimum distance as a second parameter and maximum distance as a third one. We can now lerp the current distance towards the target distance so that we slowly get there instead of it being an instant change. To do that, create a float named current distance and assign to it framingtransposer.mCameraDistance. Then type in if current distance equals current target distance, we return. This makes it so that if we are already at the target distance, we won't do anything. To lerp our value, type in float lerped zoom value equals to mathf.lerp current distance, current target distance, smoothing multiplied by time.delta time. We pass in smoothing multiplied by time.delta time here because we don't really want it to be an amount of seconds for the whole lerp, but just keep it as consistent as possible at every change and get there whenever it gets there. Then finish it up by setting the framing transposer .m camera distance to be equal to the lerped zoom value. That's all we need to zoom our camera, so save it up and go back to Unity. If we now enter play mode, we should be able to zoom our camera. With our camera working like Genshin Impact camera, we can finally use it to rotate our character and move it towards the right direction. Because we'll need to know our camera rotation to do that, we'll need a reference to our camera. So open up the player script. In here, create a new public property of type transform, which shall name main camera transform. Then in the awake method, type in main camera transform equals to camera.main.transform. We are getting the main camera and not the scene machine camera because scene machine controls the main camera, so we are safe to get our data from there. Now, camera.main was something that wasn't very performant before, and that's the reason why we are caching it here. This is because it used to search for all objects with tags and add it to a temporary list, which will then be searched again for an object with the camera component enabled. However, seems like in Unity 2020.2 that was optimized, and now it stores a dedicated list of objects with the main camera tag instead, and then searches on that list only. And as it says there, they found a new way of doing things to be way more performant. However, we'll still cache it ourselves, not only because we are also getting the transform, but also caching it means we can assign any value to this variable whenever we want, and it's changed everywhere, and likely makes the code a bit cleaner and organized. With that done, let's head back to our movement state. We'll be adding our player rotation here. Just under our move method declaration, create another one by typing in private float rotate. We'll accept a parameter of type vector3 named direction, which is simply the direction that our player will rotate towards. Before we start coding it though, let's first take a look at how it works in Genshin Impact. Let's start by pressing W. As one might expect, this will move the player forwards. However, the moment we rotate the camera around, the player will start rotating with it and move forwards towards where the camera is looking at. If we instead start pressing S to move backwards, it will keep on doing the same but towards the opposite direction. The same happens when we move sideways. What's happening here is that our player is moving towards the sum of our input direction plus the rotation of the camera. So if we press W and move the camera 45 degrees, we want to go 0 degrees from our forward direction plus 45 degrees from our camera. If we instead press S, we want to go 180 degrees from our backwards direction plus 40 degrees from our camera. We'll understand more in a bit on why W and S are 0 and 180 degrees. Let's then start by getting that sum. The first thing we'll need will be our movement input angle, or its direction angle. We can get that through a math method named attan2. Attan2 receives two parameters, the y and x of a coordinate in that order. Let's say we were moving forward, which translates to the coordinate of 0, 1. Remember that our y-axis here is the equivalent of the 3D z-axis. If we pass in 1, 0 to the attentu method, it will be the same as having the 0, 1 coordinate. The angle this returns is 90 degrees, which should be correct. However, Unity forward axis is the z-axis. Contrary to the normal degree circle, it increments its angles clockwise, starting at the top. This means that our 0, 1 coordinate should have been 0 degrees instead of 90 degrees, as 90 degrees in Unity will be towards the right and not forwards. We can actually make it so that attentu returns relative to the z-axis by simply swapping the order of the parameter values. If we now pass in 0, 1 to our attentu method instead, which is the same order as the forward coordinate, the coordinate will now become 1, 0. If we take a look at the degree circle now, that coordinate is at 0 degrees, which is exactly what we need. Now, I don't completely understand the reason why this happens, but I guess it's just how math works. It's like we are saying, give us the angle relative to the z-axis instead, or relative to the second parameter axis. Let's also take a look at a few other coordinates. 0, -1 for backwards, -1, 0 for left, -0.7, 0.7 for left forward. With that in mind, let's get that angle by typing in float direction angle mathf.attentu direction.x direction.z. This method, however, returns the value in radians. To transform it into degrees, we just need to multiply it by a certain value, which is by mathf.rad2deg. This works because we know that 1 radian is the equivalent of an amount of degrees. That amount is stored in the mathf rad2deg variable, so by multiplying it with the amount of radians, we get the angle in degrees. We, however, have yet another problem. attentu can return negative values, as it ranges from -180 to 180. If I remember correctly, there were some problems with rotations that I needed to make sure that negative angles were converted into positive angles. I believe it was because a rotation wouldn't always follow the shortest path to a certain angle, so it could rotate wrongly. Thankfully, it's quite easy to turn negative angles into positive angles. To do that, simply type in if direction angle lesser than 0f, then we sum to the direction angle 360 degrees. This means that -90 will equal to 270, -180 will equal to 180, etc. With that, we have our input direction angle and simply need to add our camera angle to it. Now, if any of you is wondering why do we need to add our camera angle if we already have the input direction in degrees, that's because the movement input is always the same regardless of where the player is looking at. That's of course because that's how it is defined in the input actions. W is always up, S is always down, etc. Not only that, but no matter how much the player rotates, 90 degrees in Unity is always to the same direction, which is right, as it is in world space. That means that if we tell our player to go 90 degrees, it will always go to the right in world space, and not to the right relative to where the player is facing. And that's when our camera angle comes in. Let's say we move 90 degrees, or to the right by pressing D. Then we also move our camera 90 degrees to the right. Currently, our player will keep on moving towards the same direction as it's going to the world space 90 degrees direction. However, let's also add the 90 degrees of our camera to make a total of 180 degrees. Our player will now move 90 degrees to the right of the camera, which is considered down or backwards in world space, the equivalent of 180 degrees. which is exactly what we want. So to add our camera angle, simply type in direction angle plus equals state machine dot player dot main camera transform dot Euler angles dot y. Note that we need to use Euler angles and not rotation, as rotation returns a quaternion. The y-axis of a camera is the horizontal rotation. Of course, when adding the camera angle to our direction angle, it will be possible to go over 360 degrees. To fix that problem, we simply check if direction angle is greater than 360°. If that's the case, we subtract to the direction angle 360 degrees. So 600 degrees will lead to 240 degrees, or 380 degrees will lead to 20 degrees. With that done, we have our final direction angle. We can now return it by typing in return direction angle. To keep things organized, let's do two things. Select the first if statement and assignment and extract it to a new method named getDirectionAngle. Then select the second if statement and assignment and extract it to a new method named addCameraRotationToAngle. I'll rename the last method parameter to beAngle. We now have the direction angle we want to rotate our player towards. But if we take a look at Genshin Impact, whenever the player rotates, either by pressing one of the movement keys or by rotating the camera, it takes some time to get to the target rotation. You might not notice it too much when pressing the movement keys because that reach time is quite low, but you can see that it isn't null as it isn't snappy. If you do rotate the camera, then you can see that the player is a bit delayed on its rotation. We'll be smoothing our player rotation much like they do, using a method named smoothDampAngle. This method requires a few things from us: the current angle, which we'll be able to obtain from our player rotation, the target angle, which is our direction angle, a velocity, which the method takes care of updating its value, and the amount of time it should take to reach the target angle. We'll create one variable for each of these, including for our direction angle, as we'll need it somewhere else further into this series. So above, create a few new variables: protected, vector3, current target rotation, protected, vector3, time to reach target rotation, protected, vector3, damped target rotation, current velocity, and protected, vector3, damped target rotation, past time. We are creating vector trees because in our gliding system we'll need a value for the x and the z axis, so we might as well just make it a vector tree right away. We now need to initialize our reach time to a certain value, so in our constructor call in a new method named initializeData. Inside we'll type in time to reach target rotation.y equals to 0.14f. We'll later on understand how I got to this value, but just know that it is the time it takes for the rotation to happen in Genshin. When that's done, back to our rotate method, we'll call in a new method named rotate towards target rotation. I'll make this method protected and move it to the reusable methods region. We'll start by getting the current angle by typing in float current y angle equals to statemachine.player.rigidbody.rotation.eulerangles.y. We can now start smoothing our player rotation, but only if we aren't already at our target rotation. So type in if current y angle equals to current target rotation.y. If that's the case, we return. Otherwise, we'll smooth our angle by typing in float smooth y angle equals to mathf.smooth_damp_angle. When that's done, pass in current y angle and current target rotation.y. Then we'll need to pass in the velocity variable, but with the ref keyword, as Unity automatically updates and uses this variable as it wishes inside of the method. So pass in ref dumped target rotation current velocity.y. For the amount of time it should take to reach the target rotation, we'll pass in time to reach target rotation.y minus dumped target rotation past time.y. If we were to pass in time to reach target rotation alone here, it would always take 0.14 seconds for each smooth method call, instead of 0.14 seconds for the whole rotation. Of course, we need to increment something to the past time variable, as otherwise it will keep on being 0. So type in dumped target rotation past time.y plus equals time.delta time. Note that because this method is being called in the fixed update method, Unity will automatically return fixed delta time when we use the delta time variable. We now have our smoothed value, so we can rotate our player with it. To do that, we'll create a new quaternion which I'll name target rotation. Then we'll set it to be quaternion.Euler, which accepts Euler angles and transforms them into a quaternion, and pass in 0f for the x, smooth y angle for the y, and 0f for the z. When that's done, we'll set the player rotation by typing in statemachine.player.rigidbody.moveRotation and pass in target rotation. That takes care of rotating our player. However, we need to remember that the moment our direction angle changes to something else, we need to reset the past time and also set the target rotation to our new angle, as we are not yet doing that. So back in our rotate method, between the last two methods, type in if direction angle is different than current target rotation.y, we'll call in a new method named update target rotation data, with direction angle as an argument. I'll update the name of the parameter to be target angle instead. In here, we'll set the current target rotation.y to be the target angle. Then we'll reset the past time by typing in dumped target rotation past time.y equals to 0f. We don't really need to reset anything else. We don't need to reset our velocity either, as the smooth damp angle method automatically takes care of that for us. Back in our rotate method, I'll select the code of the if statement up until the getDirectionAngle method and extract it to another method named updateTargetRotation. Then I'll make it protected and add it to the reusable methods Recentering. I'll also add a new parameter of type pool named shouldConsiderCameraRotation defaulted to true. Then, before we add our camera angle, type in if shouldConsiderCameraRotation and put the line inside of this if statement. We'll need this later for our dashing state. We now have everything needed to rotate our player. Of course, we aren't yet calling the rotate method anywhere. If we take a look at Genshin Impact, if we move the camera around while idling or jumping, our player won't rotate with it. This simply means that our rotation only happens when we are moving. The idling and jumping are not considered moving because we set their speed modifiers to 0. So in our move method, right after we get the movement direction, type in float target rotation y angle equals to rotate and pass in movement direction. We now need to transform this angle into a direction that the player can move towards, as right now we are moving towards the input direction, which will always be the same regardless of the camera angle. To do that, type in vector3 target rotation direction equals to get target rotation direction, passing in target rotation y angle as an argument. I'll rename the method parameter name to be target angle instead. I'll also make it be protected and add it to the reusable methods region. In here, we'll return quaternion.Euler 0f target angle and 0f multiplied by vector3.forward. Now, if I'm being completely honest, I'm not too sure what actually happens here. If I understood something, it's that we have a point which is our forward direction. And then we want to know what point would we get if we rotated that forward direction by an amount of degrees, let's say 45 degrees. With this multiplication of a quaternion which represents our 45 degrees angle by a vector, some black magic happens and we get our normalized point, which is the direction we want to go to. We pass in vector3.forward here because we always want a rotation from the set axis, which is the player forward axis. Do note that it's apparently important for the multiplication to be a quaternion by a vector and not the opposite, so order matters here. With that done, let's go back to our move method. In the add force method, we now swap the movement direction with our new target rotation direction, which already comes normalized. If we save and go back to Unity, entering play mode should allow us to move and rotate our player around correctly. We even get a thumbs up from our shadow. Great, our player now rotates and moves properly. But while we are doing that, we're not really using any of our actual states. We are doing all of this while on the idling state, which of course shouldn't be happening, as idling means standing still doing nothing at all. To fix this problem, let's go to our idling state script. We have a few things to do here. The first thing is to set the speed modifier to 0f when we enter this state, so to not allow our player to move. We can do that by overriding the enter method, and set the speed modifier to 0f. We don't need to set this variable back to 1/2 when exiting, as every state will update this variable to a specific value. The second thing we need to do is to reset our player velocity. This is because we can come from a state that's still moving. If we did not reset the velocity, our player will continue to slide due to physics. We'll be creating a reusable method for this, so add back to the player movement state script. And in the reusable methods region, create a new protected method named resetVelocity. Here type in statemachine.player.rigidbody.velocity equals to vector3.0. As I've previously explained, we'll be setting this to the velocity variable to make sure it is an instantaneous change. Back to our idling state, we now call in resetVelocity. I'll also add this method to an iteration named iStateMethods. That's most of what we need in our idling state. Right now we'll only add the transitions to other states, and later on in the series we'll finish whatever is left to do here. Taking a look at our movement system states, the idling state can transition to the following states: walking, running, dashing, and jumping. Because we'll only do dashing and jumping later on, we'll only transition to the walking and running states. The way we'll be doing this is by using something from the new input system, which are callbacks. Every action should have three phases: started, performed, and cancelled. When these are called depend on the action type that we chose when creating the input actions. In our case, we need the movement input which is of type value. For the value action type, started means when we first press one of the keys. Performed means whenever we press a key after the first one without actually releasing it, like going from W to WD. And cancelled means releasing the input keys completely. We'll be using these actions for most of our transitions, but in some cases this leads us to a problem. Let's say we were idling and decided to jump. Whenever we are in the jump state, moving in the air is not possible, but we are still able to press the movement input keys if we don't disable them, which we won't. In that case, if we hold one of the movement keys while in the jumping state and then land, the expected outcome is for us to start moving. However, because the movement input has already started when we were jumping, the callback we'll add on the idling state won't be called anymore, which means we will stay in the idling state even though our movement keys are pressed. If we were to disable the input when we jump and then enable it when we land, then the started will be called again. But because we won't be doing that here, we need to find another solution. Thankfully, this is quite simple to solve. In our update method, we simply need to check if our movement input variable is not 0, and if it isn't, it means we should start moving. This works because our movement input is of value type, which continuously tracks changes, and if you remember, we are constantly reading for those changes in the player movement state update method. So let's do that by typing in override, update, and pressing enter. Here type in if movement input equals vector2.0. If that's the case, we can return. Otherwise, we'll call in a new method named onMove. Note that even though this is in our update method, it will only be called once, as we'll be transitioning states in this method, meaning our current state will change to another state on its first call. Now in Genshin Impact we can go from idling to walking or running. The transition depends on our walk toggle. If the walk is toggled, then we'll transition to the walking state, and if it isn't, we'll transition to the running state. Of course, we don't really have a way to know in what toggle state we are, so we'll start by creating a variable in our player movement state script. In here, create a new variable by typing in protected bool showed walk. To update it, we'll use the walk toggle input action started action. For the button type, started is called whenever we press on the input key. Performed is called whenever the input action is performed, which can change if you add an interaction like hold. An hold interaction of 1 second here will only call the performed action when the button is held for that 1 second. This will be useful for us later on. For an input action without interactions though, this will be called right after the started action. Cancelled is called whenever we release the input key. Start by going into our enter method and call in a new method named addInputActionsCallbacks. In our exit method, we'll also call in another new method named removeInputActionsCallbacks. Make both of these methods protected and virtual, and move them to the reusable methods region. The way we can add a callback to the input started action is by typing in stateMachine.player.playerActions.walkToggle.started plus equals onWalkToggleStarted. If we generate a method for this, it should also come with a parameter. We do not need to pass this parameter when we add this callback, as C# does that for us already. I'll rename it to context. I'll also make this method be protected and virtual and add it to a new region named input methods. What we'll do here is quite simple. Every time we press the walk toggle input key, we'll set the showedWalk variable to its opposite value, which we can do by typing in showedWalk equals to not showedWalk. This is how you add a callback to an input action. Now, we aren't really using the context variable here, so do we really need to pass it in? The answer is actually yes. Whenever we add a callback, we need to make sure we also remove it. The reason why is because we are adding a callback every time we enter a state, which means that if we were to enter it 10 times, we would have 10 of the same callback being called. However, Unity needs to know what's the callback we are trying to remove, and apparently it needs this context variable to know it. I've tried in a project before removing the context parameter, and it didn't really remove the callback, so we need to make sure it is there. Now, to actually remove the callback, we simply copy our line that has it and paste it in the remove input actions callbacks method. Then we swap the plus operator with the minus operator to subtract or remove this callback. And that's our walk toggle callback done. So go back to our player idling state, and in here we can now use a showedWalk variable for our transitions. To do that, type in if showedWalk. We shall then transition to the walking state by typing in statemachine.changeState and pass in statemachine.walkingState. We can of course return from the method right after that. Otherwise, if we aren't supposed to be walking, we shall go to the running state. So type in statemachine.changeState and pass in statemachine.runningstate. We are now able to transition to another state from the idling state. Of course, we haven't yet done the other state's logic, so if we were to change states now, our player will stand still due to the speed modifier still being 0. Let's start by adding our logic to the walking state. To do that, open up the player walking state script. We'll start by overriding our enter method, and then set our speed modifier to be around 0.225f. This will make it so our player moves slowly, much like he was walking. I'll add our enter method to a new region named iStateMethods. Note that every value that I'll write are values that I found to be somewhat close to Genshin Impact. And that's really it for our walking state logic. We simply needed to make it move slowly. Of course, we also need to add transitions to other states, so let's take a look at our movement system states. From the walking state, we can transition to running, light stopping, dashing, and jumping. Again, we'll add dashing and jumping later on in the series. For our light stopping, we'll also add it later, so we'll instead transition to the idling state for now. We'll use callbacks for these transitions. The first one is to the running state. This happens when we are walking and untoggle the showedWalk variable. Thankfully, we can do that very easily by overriding the onWalkToggleStarted method. I'll add this method to a new region named inputMethods. We need to call our base method logic here as it takes care of setting the showedWalk variable for us, and all we need to do here is to transition to the running state by typing in statemachine.changeState statemachine.runningstate. That's it for our running transition, so for the other we'll be adding a new callback. We'll be using the movement cancelled action for this. So start by overriding the add and remove input actions callbacks methods. I'll add them to a new region named reusable methods. then call in statemachine.player.input.playerActions.movement.cancelled plus equals onMovementCancelled. I'll make this new method protected, rename the parameter to context, and add it to the input method's region. Make sure you also remove the callback we've just added in the remove method. In the callback, we'll simply type in statemachine.changeState, statemachine.idlingState. That's all we need for our walking state, so let's next do the logic of our running state. So open up the player running state script. Start by overriding the enter method and set the speed modifier to be 1f. I'll add this method to an region named iStateMethods. Again, that's all the logic we need, so all that's left are the transitions to other states. Looking at our movement system states, our running state can transition to walking, medium stopping, dashing, and jumping. This is much like the situation of our walking state. So let's head back to the player walking state and copy the whole input method's region. Then back into the player running state, paste the code we've just copied. Our onMovementCancelled callback is as it should be for now. For our onWalk toggle started, we'll swap running state with walking state instead. And that's all we need to do in our running state. Go ahead and save all the files and then go back to Unity. Entering play mode, our player shall now be working fine, and our debug.log shall show the correct state. If we start running and toggle our walk by pressing the left control key, we shall start moving slowly. Of course, toggling it again shall now make the player go back to its running speed. However, we currently have two problems. The first one is that we are starting to unnecessarily repeat some code in our states, like our onMovementCancelled callback. We are also hardcoding our values, such as for our speed modifier. The second one is regarding our showedWalk variable and how we are currently reusing data between states. Let's exit and enter play mode again to make sure everything is reset to its default values. Right now, our showedWalk variable should be set to false. That means that if we start moving, we should enter the running state, which is what's happening. But let's now toggle our walking state. With this, not only are we moving slowly, our showedWalk variable shall now be true. Let's now stop moving to enter the idling state. What do you think will happen if we start moving again? From what we've done so far, because the showedWalk variable is now true, we shall start walking. However, we can see that's not the case and are instead running. The reason why that's happening is quite simple. The showedWalk variable is not static, which means each state has its own showedWalk variable. So, while in our running state the showedWalk variable became true, it remained as false in our idling state, hence why we started running instead. We can further see this if we stop running, press left control, and start moving again. We shall now be walking. One way of possibly fixing this is by setting the showedWalk variable to be a static variable, meaning it will be shared across all instances of the player movement state class. However, that isn't a great solution when we can have more than one player, like in co-op games, as it will make it so every player will share the showedWalk variable with each other. What we'll end up doing instead is to create a class that holds data that can be reused between all of the states. Before we do that though, we'll start by fixing our first problem, which also involves removing the hard-coded values of our code. We don't really have a lot of code that can be reused in our moving states right now, but we can still update a few things. In our case, we'll be moving our onMove, onMovementCancelled and the inputActionCallbacks methods to a new state, which will be our grounded state. Of course, we still need to create a state, so go to the player states folder in the grounded folder. In here, create a new C# script, which I'll name player grounded state. Open it up and remove the default methods. We'll also swap the monoBehavior inheritance with player movement state instead, and generate the constructor it needs. When we are done doing that, we'll go ahead and swap our moving and idling states to inherit from this state instead. So go to the player idling state and swap the inheritance. When that's done, do the same for our walking, running and sprinting states. Then go to the player walking state script and copy or cut the inputActionCallbacks methods. Next, paste that code into the player grounded state script. Then we'll go get the onMovementCancelled method from the player walking state script as well, and paste it here with its region. Make it a virtual method as well. When that's done, remove them from the player running state script. Next, we'll go to the player idling state script and copy or cut the onMove method and paste it in the reusable methods region of the grounded state script. We'll also make it a protected virtual method. That's all we need to reuse for now. All that's left is to create a way for us to set our current hard-coded values through the inspector, and also create a reusable data class for us to reuse data between states. So go back to Unity and move back to the player scripts folder. In here, we'll create another folder named data. Inside, create two other folders: scriptable objects and states. Inside of the scriptable objects folder, create a new C# script. I'll name it player SO. Inside of the states folder, create two new C# scripts: player state reusable data and player rotation data. Then create a new folder named grounded. Inside of the grounded folder, create a new C# script: player grounded data. Then create yet another folder named moving, and inside of that folder, two new C# scripts: player walk data and player run data. The player SO or player scriptable object will hold most of the values we'll be using throughout our system, such as the speed modifiers or rotation reach times. The player state reusable data will hold the data that needs to be reused through multiple states, much like our showed walk variable or our movement input variable. Start by going back to the scriptable objects folder and open up the player SO script. Remove the default methods and swap the monoBehavior inheritance with scriptable object instead. Then create a new public property of type player grounded data. Name it grounded data. I'll give it a private set. Because we'll need to set this in the inspector, add the field serialized field attribute to it. The field serialized field attribute should work in Unity 2020 or above, but if it doesn't work for you, use public variables instead. I believe you can also use it with non-automatic properties as well. That's all the data we need here. So now we need a way to create this scriptable object. We can do that by adding, just above the class name, Create Asset Menu. I'll pass in the file name of player and the menu name of Custom Characters Player. When that's done, open up the player grounded data script. In here, remove the default methods and inheritance. We'll hold the base speed of the player here, so type in public float base speed and give it a private set and a default value of 5f. Then give it the field serialized field attribute together with the field range attribute from 0f to 25f. Then we'll add our rotation data by typing in field serialized field public player rotation data base rotation data with a private set. Next, we'll add our walk data and run data, so type in field serialized field public player walk data with a private set. And duplicate this line, swapping the walk with run instead. To make this class show up in the inspector, we need to make it serializable by typing in just above the class name serializable, which requires the system namespace. We'll now set our player walk data, so open it up and remove the default methods and inheritance. Then type in field serialized field range from 0f to 1/2 public float speed modifier with a private set and a default value of 0.225f. Make this class serializable as well. That's all for our walk data, and our run data will be the same, so copy the speed modifier variable and open up the run data script. In here, remove the default methods and inheritance and then paste the variable line and swap the range to be from 1f to 2f and default the value to be 1f. Don't forget to make this class serializable as well. All that's left for our SO data is the rotation data, so open up the player rotation data script. Start by removing the default methods and inheritance. When that's done, add a new public vector tree named target rotation reach time, giving it the field serialized field attribute. Make this class serializable as well. That's it for our scriptable object data. So for our reusable data, open up the player state reusable data script. In here, remove the default methods and the mono behavior inheritance. I'll be showing on the screen the necessary data to be reused. Let's start with our movement input by typing in public vector2 movement input with a public set. We'll be giving a public set to all of the properties here, as we need to be able to set their values. Then add a speed modifier by typing in public float movement speed modifier and default it to 1f. For our showed walk, type in public bool showed walk. With that done, we now need a property for all of our vector trees. However, we have a problem when doing that. Whenever we have a vector tree property, we cannot set its variable from another class. So creating a vector tree here wouldn't allow us to change its x, y and z variables from our states. This only happens when it is a property, because properties return a copy of the private variable they create when its type is of value type. which means changing its x, y, or z won't do anything in the original vector tree. We could fix this by making it a public variable instead of a property, but we'll actually fix it by making it so that the property returns a reference of our private variable. This means that we can change its variables as it's not a copy anymore, but a reference to the actual vector tree. To do that, first create the private variable by typing in private vector tree current target rotation. Then under it type in public ref vector tree current target rotation. We'll have to set the get ourselves and return a reference of our current target rotation. We don't nor can give it a set because it is by reference, which basically means do what you want with it already. Now, the reason why we also need the ref in our property and not just in the return is because properties are methods. So our ref vector tree is basically our property or method return type, which requires the ref keyword if we are returning a value by reference. All that's left to do is to do the same for the other 3 variables. So duplicate the existing one 3 more times and change the variables and properties name to time to reach target rotation, dumped target rotation current velocity, and dumped target rotation past time. Make sure you make all the properties public. We now have our reusable data. Of course, we do still need to create our player scriptable object in Unity and also swap the current data usage with our data classes. For our player scriptable object, head back to Unity and go to the Assets folder. In here, create 3 folders, each inside of the other: Scriptable Objects, Characters, and Player. Then we'll create the scriptable objects by going to Create, Custom, Characters, Player. I'll name it Player. You can also access this menu through the Assets top menu. We already have most of our default values set to the correct values, but because our base rotation reach time is a vector tree, we weren't able to set a default value. So, change the y value to be 0.14. That's all we need, but I'll also add a new inspector tab by right-clicking in Inspector tab and going Add tab, Inspector. Then I'll lock this tab so that if we ever need to access a scriptable object, we can come here without needing to go through all of the folders. When that's done, go back to the other Inspector tab. Our scriptable object is now created, so we need a reference to it in our player. To do that, open up the player script. In here, create a new public property of type player.so, to which I'll name data. Add the field serialized field attribute to it as well. I'll also add a field header for references. When that's done, go to Unity, select the player game object, and add the player.so to the respective field. That's it for our scriptable object. We now need to add our reusable data, and we'll do that in our state machine. We could add it for every single state, but it's unnecessary. So open up the player movement state machine script. In here, type in public player state reusable data. I'll omit the set. Then in the constructor, type in reusable data equals to new player state reusable data. We can now start swapping our values with our data variables. Start by opening up the player movement state script. We'll be using the rename function of Visual Studio for this, which other IDEs should also have. However, it doesn't really let us add a dot ourselves, but we can cheat that by typing in state machine dot reusable data dot select it and then copy or cut it. Then we'll go to our variables and we'll select the movement input variable and right click on it and press rename, or just use the F2 shortcut. When that's done, put the cursor on beginning of the variable name and paste our state machine reusable data text. Of course, change the M to be uppercase as well and press enter. This renamed our movement input variable usages to what we needed, so feel free to delete the variable now. When that's done, do the exact same thing for the other existing variables except the base speed. Rename the speed modifier to movement speed modifier as well. Once we are doing that, we need to swap our hard-coded values with our SO data. For our base speed, we'll remove the current variable and create a new protected variable of type player-grounded-data named movement data. Then in the constructor, we'll set the movement data to be equal to the state machine .player.data.grounded-data. When that's done, go to the getMovementSpeed method and swap the old base speed with movementData.baseSpeed. Now in our initializeData method, we'll swap the hard-coded 0.14f with movementData.baseRotationData.targetRotationReachTime. We'll also remove the .y from the time to reach target rotation. All that's left now is to do the same thing for our hard-coded speed modifier values. So go to the walking state and swap the value with movementData.walkData.speedModifier. And then go to the running state and swap the value with movementData.runData.speedModifier. We don't need to set our idling state modifier because it is always 0. We don't need to make the movement data reusable either because it's always referencing to the same scriptable object data. We are now reusing our data and not hard-coding any values besides the speed modifiers of 0. If we go into Unity and enter play mode, you might have noticed when going against a wall that we kinda get stuck in there. We'll be fixing that by giving our player a physics material with no friction so that we don't get stuck anymore. So exit play mode and in our materials folder, create another folder named physics. Inside, create a new physics material. I'll name it player physics. Then set every field to be 0. When that's done, drag it into our Capsule Collider material field. If we enter play mode again, going against a wall shall no longer get us stuck. As a last thing, while we won't really be reusing any data or logic with it, we'll create our player moving state. This is because we'll need it when animating, so we might as well just create it now. So go to the player grounded state scripts folder and in the moving folder, create a new C# script named player moving state. Open it up and remove the default methods and swap the inheritance with player grounded state. Then go to the walking, running and sprinting states, and swap their inheritance to inherit from player moving state. That's all we'll need for now. Saving it all and going back to Unity, entering play mode shall now have our showed walk variable working fine. If we start running and press left Ctrl, our walking will be toggled and will start moving slowly. If we now stop and then start moving again, we shall start walking instead of running, which means that our variables are indeed being reused between the different states. That's great. Our data can now be reused throughout all of the states. Before we start adding the remaining states though, we'll take a look at how are we going to allow our player to move up and down slopes and also climb steps up until a certain height. For the reason why, let's enter play mode and move up and down in our small ramp. Even though for the most part it works, when going down or going up our ramps, we sometimes jump. If we head to the other ramp, we can't climb it either as there is a small step. The first one happens because Unity gravity isn't fast enough to keep with our horizontal movement speed, so it will look like we have jumped. The second one happens because we are colliding our player capsule collider with the ramp collider, which in this case is like colliding with a wall. It would work if the step was a bit smaller as it would hit the rounded part of the capsule collider, but it will be best for us to decide the maximum height we want our player to climb instead. From what I found when doing this system, there are two common ways of solving the slope problem: floating capsules and normals. Floating capsules, which is the solution we'll be using, consists in adding a force to the player in a way that the capsule constantly floats, or more specifically, the center of the capsule stays at a certain distance from the ground. We can mix this with a resizable capsule collider to allow our player to climb steps up until a certain height. Normals, however, involve getting the normal of the ground that's underneath the player and set our player direction relative to that normal. Normal is simply the direction that the object is facing. However, I don't think normals solve the step climb problem, so we'll go with the floating capsule technique. With that in mind, we now have two things to do. Allow our capsule collider height to be changed through a slider, removing the height from the bottom only, and apply a force to our player to keep him from falling due to gravity. Let's start with the collider height. To do that, go to the scripts folder and create a new folder named Utilities. Inside, create another folder named Colliders. In here, we'll create a new C# script to which I'll name Capsule Collider Utility. Open it up and remove the default methods and inheritance. Because we'll need it to show in the inspector, we'll make this class serializable. In this script, we'll basically be recalculating our collider height every time a slider that goes from 0 to 1 is updated in the inspector, 0 being 0% and 1 being 100% of the original collider height. To do that, we'll need a few things: a reference to our capsule collider, the default collider data, and the slope data, like our percentage slider. We'll be creating a data class for each of these, including our capsule collider reference, as we'll need to cache some data from it as well. So, back into Unity, go to the scripts folder and create a new folder named Data. Inside, create yet another folder named Colliders. In here, we'll create 3 new C# scripts: Capsule Collider Data, default collider data, and slope data. Start by opening up the Capsule Collider data script. Remove the default methods and inheritance. We'll be storing not only our Capsule Collider reference, but also its local space center. So type in public Capsule Collider, and make it a private set. And then public vector3 collider center in local space with a private set as well. To initialize this data, we'll create a new method by typing in public void initialize and pass in GameObject as a parameter. This is because we won't be setting our reference through the inspector, but instead through a GameObject we pass in. If you do want to set it from the inspector instead, then the next 3 lines won't be required, but you'll need to add the field serialized field attribute to the collider variable, as well as a serializable attribute to the class. Making it a GameObject instead of a player makes this script reusable. Inside, type in if collider is different than null, we return, as it means it's already initialized. Otherwise, we'll get it by typing in collider equals to GameObject.getComponent of type Capsule Collider. For our capsule center in local space, we have 2 ways of doing it. One is by using the transform inverse transform point method to transform a world space position to a local space position. However, the Capsule Collider already contains a center variable in local space. We'll be setting it to our own property though, as that makes it so that if we ever need to update this center to be something else, we only need to change it here and it applies everywhere. Or if we ever need to remove it, errors will be thrown wherever we were using the property, which makes it easier for us to know where we need to remove it from. So type in collider center in local space equals to collider.center. We'll extract this last line to a new method named updateColliderData and make it public. That's it for our Capsule Collider data for now, so open up the default Collider data script. We'll need this data when recalculating the Capsule Collider new dimensions. Remove the default methods together with the monobehavior inheritance. We'll be making this class serializable to be able to set the default data through the inspector. We'll be needing 3 things: its height, its center, and its radius. So type in field serialized field public float named height with a private set. Then duplicate this line twice and swap the names to be center y and radius. I'll give the height a default value of 1.8f, the center y a default value of 0.9f, and the radius a value of 0.2f. The height of our character model is known through its mesh renderer bounds size variable. The center y is simply half of that height, and our radius is something we've defined ourselves before. That's it for our default data, so next, open up the slope data script. Remove the default methods and the inheritance and make the class serializable. We'll only need one variable for now, which is our step height. So type in field serialized field range from 0f to 1f public float step height percentage with a private set. I'll default it to 0.25f. We'll add the rest of our variables whenever we need them. That's it for now, so go back to the Capsule Collider utility script. we'll create a variable for each of our data classes. To do that, start by typing in public Capsule Collider data with a private set. Again, if you are setting this one through the inspector, add the field serialized field attribute to it. Then duplicate this line and swap Capsule Collider with Default Collider. When that's done, add the field serialized field attribute to this property. Duplicate this new line and swap the Default Collider with Slope instead. We now have our data variables, so we can start creating the methods needed to recalculate our collider dimensions. To do that, create a new public method named Calculate Capsule Collider Dimensions. We'll be calling this method every time our inspector values are updated, so we'll need to recalculate the height, center, and radius. We'll start with our radius by typing in set Capsule Collider Radius and pass in default collider data.radius. Then I'll make the method public just in case we ever want to reuse it. Inside, type in Capsule Collider data.collider.radius equals to radius. This is needed because we'll need to update the radius to something else later on under a certain condition. Once that's done, we'll need to set our collider height depending on our step height percentage. So duplicate this method and swap the radius with height instead. Then in our calculate method, call in set Capsule Collider height and pass in default collider data.height. Of course, we need to multiply this with our step height percentage, which goes from 0 to 1, where 1 is 100%. So multiply the height by, between parentheses, 1f minus slope data dot step height percentage. We add the 1f minus here because the step height percentage is the percentage we want to remove. So removing 0.25 or 25% means that our new height should be 75% of its default height, which we can get by multiplying the default height with 0.75. With that done, we now need to recalculate our center. While our center is half of our height when the height is at 100%, this isn't true when we start lowering the height. The reason why is because we'll only remove height from the bottom to represent the step height, which means we want the Capsule Collider to center itself at the top and not in the middle of the character. Thankfully, it's quite easy to do that. We simply need to get the difference between the default height and the current height, and then add half of that difference to the center. Half here is the same as the bottom or the top part, and this basically makes it so that our top difference will add itself to the bottom instead. So call in a new method named Recalculate Capsule Collider Center. I'll make this method public as well. Inside, type in float collider height difference equals to default collider data dot height minus capsule collider data dot collider dot height. We get the default height first because our current height will never be bigger than our default height. When that's done, create a new vector tree named new collider center and set it to be equal to new vector tree 0f default collider data dot center y plus between parentheses collider height difference divided by 2f, and for the z axis pass in 0f. Again, we are making it go up off of our height, which is the same as adding our top height difference to the bottom. Then we set the center by typing in capsule collider data dot collider dot center equals to new collider center. Note that this collider.center is measured in local space, so we can assign our new center without transforming it into world space, which, if you ever need, you can do it by using the transform point method. That's mostly it when recalculating the dimensions of our capsule collider, but we currently have a problem. Whenever we update our step height, it will come to a certain point where our capsule collider becomes a sphere from how small it is, and will start moving up when we keep removing height from it. This seems to happen whenever our height is less than double of our radius. It's really simply because a capsule collider top and bottom are half spherical, which makes it become a sphere when there is no more middle ground to remove. So it starts going up instead, likely because it starts becoming a negative-like middle ground. What we'll do to fix it is simply set our radius to half of our height whenever the height gets to that point we've mentioned earlier. This makes it so that instead of going up, it will keep being where it was, but will instead become smaller. It isn't a perfect solution, but in my opinion it's better. So, to do that, type in if capsule collider data.collider.height divided by 2f is lesser than capsule collider data.collider.radius. If this is confusing, we basically need to know if our height is double or less of our radius. So if we divide our height by 2, we get half of it. If half of our height is equal to the radius, then it means that the full height is double of the radius. If half of our height is less than the radius, then it means that the full height is less than double of the radius. In the last case, we need to update the radius to that half height, which keeps our height at least double of our radius at any given time. To do that, type in set capsule collider radius and pass in capsule collider data.collider.height divided by 2f. I'll also extract this half height into its own variable named half collider height, and swap it in the method call as well. That fixes our problem, but we also can't forget that when we recalculate our center, we also need to cache our center in local space again. So call in capsule collider data.update collider data. With that done, we now only need an initialization method, so above type in public void initialize and accept a game object named GameObject. Then call in capsule collider data.initialize and pass in GameObject. Of course, in case this class isn't serializable, which in my case isn't, we'll also need to instantiate it. So above, type in capsule collider data equals to new capsule collider data. And above that, type in if capsule collider data is different from null, we return, as to not keep calling this once it's already initialized. That's it for our collider utility, so let's now add it to our player. To do that, open up the player script. In here, create a new field serialized field public property of type capsule collider utility named collider utility with a private set. I'll give it a field header with the text of collisions. When that's done, in the awake method, call in collider utility.initialize and pass in GameObject. Then, to make sure our collider dimensions are updated, call in collider utility.calculate capsule collider dimensions. This takes care of setting our collider data whenever we enter play mode, but doesn't take care of setting it in the editor whenever we update a slider value. To do that, we'll call in the monoBehaviorOnValidate method. We'll copy the two lines we just added in the awake method and paste them here. Saving and going back to Unity, every value update we do in the inspector shall now recalculate our capsule data. Our capsule collider height is indeed updating fine. Of course, if we go ahead and enter play mode, our player will fall and have his legs be stuck in the ground, as our capsule collider is no longer the size of our character model. That's where the floating capsule technique comes to the rescue. Simply put, we'll add a force to counter the gravity pulling us down. The way we'll be doing that is somewhat simple. Let's take a look at our player model with its capsule. In the editor mode, we are able to update the capsule collider height by only taking away height from the bottom. Of course, because we are in the editor mode, there is no gravity and that's why it stays up. What we want is to keep this place even when we enter play mode. However, as we have seen just now, if we do enter play mode, our player will fall until it collides with the ground. This is simply because our character model is just plain graphics, and doesn't take care of any collisions, as we've left that for our capsule collider. The capsule collider then sees nothing underneath, so it will start falling down due to gravity until it collides with something. So how do we make it so that the player doesn't fall down due to gravity and stays at the distance it was in the beginning? We have our capsule collider center in local space, which currently, for our values, should be around 1.125. We'll then cast a ray down from the capsule collider world space center, as the ray cast requires a world space origin up until a certain distance. If this ray hits something, which shall be our ground, it will give us the distance between the origin and the ground hit point. We then shall simply remove that distance from our capsule collider local space center. There are three possible outcomes here: a positive value, a null value, and a negative value. A positive value happens when our capsule collider isn't yet where it should be and shall still go up. For example, let's say that in this position, the distance from our ray to the ground is 1. 1.125 minus 1 results in 0.125. This means that our player still needs to go up 0.125 units for it to be at our desired point, which can be done by adding a positive vertical force. A negative value is quite the opposite. It means that our capsule collider is above where it should be and should go down. For example, let's say that in this position, the distance from our ray to the ground is 1.5. 1.125 minus 1.5 results in negative 0.375. This means that our player went 0.375 units above its desired point, and needs to go down 0.375 units to be where it should be. This can be done by adding a negative vertical force. A null value happens when our capsule collider is at its desired point. For example, let's say that in this position, the distance from our ray to the ground is 1.125. 1.125 minus 1.125 results in a 0. This means that our player is at the desired point, as it's both up or down 0 units, which is perfect. Of course, we need to keep a few things in mind here. The first one is that we need to use our local space center for this subtraction. If we were to pass in the world space center, then the y could be 0, 1, 1000, minus 250, etc. depending on the player position at that time. The second thing is that we need to add a negative vertical force ourselves, because if we let Unity Gravity take care of it, it will be too slow and we will still have our slope jump problem. The third thing is that these values that we'll receive will be smaller than that 1.125 value, meaning that they will be extremely small. Adding a force with such a small number will not be strong enough to overpower Unity gravity. Because of that, we'll need to multiply that value with a force multiplier to make sure it has enough force to go up or down as fast as it can, instantaneously to the human high if possible. Also, we need to remember that add force keeps on adding a force, so we need to make sure we remove the current vertical velocity, as otherwise our player will start bouncing. It doesn't end up flying because we'll also be adding a negative force for when we pass through the desired point, so it will keep coming back and start bouncing instead. The fourth and last thing is that it is very unlikely that our value will be null or zero. The reason why is because we are using physics, so by the time we call another add force, Unity's gravity will have added a tiny bit of negative velocity. But we'll still check if it is zero, so that we can return and do nothing if that's ever the case. We'll do all of this in our grounded state, so open up the player grounded state script. The reason why we'll do it here is because we really only want our capsule to float whenever we are on the ground, as the rest of the states, airborne and aquatic, won't really need it and would probably not work very well if we hadn't it there. With that in mind, start by overriding the physics update. I'll add this method to a new region named iStateMethods. Then call in a new method named float. You can name it float capsule or anything else if you prefer. I'll add this float method to a new region named main-methods. We'll start this off by casting our ray downwards towards the ground. To do that, we have the physics raycast method. This method requires us to send the origin of the ray in world space, so create a new vector tree named Capsule Collider Center in world space and set it to be statemachine.player.colliderutility.capsulecolliderdata.collider.bounds.center, which returns the center in world space. Then we'll create a new variable of type ray named downwards ray from capsule center and assign it to a new ray. For the first parameter, pass in capsule collider center in world space, and for the second one, pass in vector3.down. As far as I understood, the difference between vector3.down and -transform.up is that vector3.down will always be in world space, while -transform.up will be relative to the transform rotation. When that's done, type in if physics.raycast. The first argument is our ray, so pass in downwards ray from capsule center. For the second argument, we need a raycast heat variable, which we can pass in out raycast heat named heat, which allows us to use the heat variable inside of the if statement. This variable is what we'll use to know our distance. Of course, we now need a distance for the ray, so let's go to our slope data script, and when you are here, add in a new field, serialized field range from 0f to 5f, public float property named float ray distance. I'll give it a private set. I'll also default it to 2f. You don't really need it to be 2f here, but just a bit above half of the capsule height. Giving it a higher number ensures it works and will also be used for something we'll see later on. Back into the grounded state, we'll need the slope data, so let's go to our variables and type in private slope data. This is so we don't need to type in a long line as we'll use it more than once. Then, in our constructor, set the slope data to be equal to statemachine.player.colliderutility.slopedata. Back to our float method, we can now pass in slope data.float ray distance. For our fourth argument, we need the layer or layers that this array will collide with. We'll only be colliding with our environment layer, but we don't yet have a way to get it. We could pass in its layer number or string, but that isn't a great way of doing it. We'll instead create a new script to hold this data, so head back to Unity. In here, open up the player data scripts folder and create a new folder named layers. Inside, create a new C# script named player layer data. Open it up and remove the default methods and inheritance. We'll make this class serializable. When that's done, create a new field, serialize field, public property of type layer mask, named ground layer. I'll give it a private set. Then go to the player script and add a new property under our collider utility by typing in field, serialize field, public, player layer data, layer data. I'll give it a private set. Save and head back to Unity. Selecting the player object, go to the layer data area and set the ground layer to be environment. Back to our ground state, pass in state machine .player .layer data .ground layer. For our fifth argument, we'll pass in query trigger interaction .ignore, which ignores objects that have the environment layer but are trigger colliders, as we don't want to consider triggers a ground we walk on. That's it for our if statement, so we can now start floating our capsule. To do that, create a new variable to hold our remaining distance by typing in float distance to floating point equals to state machine .player .collider utility .capsule collider data .collider center in local space .y, as we want the vertical axis. Now, this isn't extremely important for us, but if we ever scale our player game object, our capsule won't stay afloat at the point that we want. To fix this, we can multiply this collider center y with a player y local scale. So multiply it by state machine .player .transform .local scale .y. Of course, if the scale becomes too big, the distance will be more than 2, so the raycast won't find anything, and our player will enter the ground, which is solvable by increasing the distance value. We now simply need to subtract the distance from our ray hit, so type in -it.distance. This is, of course, the distance from the center of the capsule collider to the ground. We can now float if this value isn't 0, so first type in if distance to floating point equals 0f. We return. Then we'll need our lift force, which means we need a vector tree. Start by typing in float amount to lift equals to distance to floating point. We now need to multiply this value with that extra force we've talked about previously, and also remove the current vertical velocity. For the force, head back to the slope data script. In here, duplicate the ray distance variable and set the range to be from 0f to 50f, and name it step reach force. I'll default this value to 25f. When that's done, go back to the ground state script and multiply our distance with slope data.step reach force. We'll need to subtract it with the player vertical velocity now, so let's create a method to get us that. Go to the player movement state script and under the get player horizontal velocity, type in protected vector tree get player vertical velocity, and inside type in return new vector tree 0f state machine .player .rigidbody .velocity .y and 0f. You could also just return the y value if you'd prefer, which will return a float instead of a vector tree. Back into the grounded state script, subtract the amount to lift with getPlayerVerticalVelocity.y. We now need to convert this float force into a vector 3 force, so type in vector 3 lift force equals to new vector 3 0f amount to lift 0f. Then to add this force, we call in stateMachine.player.rigidBody.addForce and pass in lift force and force mode of velocity change. Add force here is fine even though we have another add force when moving, because this one is a vertical force while the other one is an horizontal force. We will likely need to use the velocity variable if both add forces were for the same axis. If we now save everything and go back to Unity and enter play mode, our player should be floating, meaning that our capsule collider won't be touching the ground. We can also go up and down slopes without any jumps. Furthermore, it's now possible for our player to climb the other ramp step without a problem. Of course, we can see our feet entering the ground when going up the ramp, but Genshin Impact likely fixes this using IK or inverse kinematics, which we won't be covering. Regarding what I previously said about our float ray distance, which is 2f, this ray distance is also used when the player needs to go down. This means that if we jump or fall down something, let's say we fall off the ramp, if the distance from the center of the capsule collider to the ground is enough to be caught in the raycast, we'll instantaneously teleport to our desired floating point, as we've added a negative force to move down. This, however, won't be too noticeable once we had falling in our gliding system. With that, we are now able to correctly move on slopes, so we'll add something else as well. If we take a look at Genshin Impact, the speed of the player is reduced when we enter a slope. This happens both when going up or down the slope. So back into our grounded state, in the raycast if statement, we need to get the angle of the ground. That's easily obtainable by using the vector3.angle method, which returns the angle in degrees between two vectors. So type in float ground angle equals to vector3.angle. For our first vector, we'll pass in the ground facing direction, which we can get through the it.normal variable. For our second vector, we'll pass in our downwards ray from capsule center.direction. However, this direction is going down, which is the opposite of the ground direction. So we'll instead do its opposite direction by adding a minus at the beginning. With this value, we can now set our speed modifier to something else depending on the given angle. So call in a new method named setSlopeSpeed modifier on angle and pass in ground angle. I'll rename the parameter to be named angle instead. We'll now need to create a new property for our speed modifier when on slopes, as we want to make it be relative to the current state speed. To do that, go to the player state reusable data script, and when you are here, duplicate the movement speed modifier property and name it movement on slopes speed modifier. This will act as a percentage from 0 to 1. Back to our grounded state, we need to check if this angle is at a certain angle and only update our slope speed modifier when that's true. However, while adding an if statement is fine, we'll learn something a bit cooler: animation curves. This easily allows us to add different speeds for different angle ranges through the inspector. To get our animation curve, go ahead and open up the player grounded data script. In here, under our base speed, create a new field, serialized field, public property of type animation curve, named slope speed angles. I'll give it a private set. Save it up and go to Unity. Then, open up the second Inspector tab to see our player's scriptable object. If we open up the animation curve, we can see an empty graph-like window, with a value from 0 to 1 on the left and 0 to 1 on the bottom. The bottom value is considered the time, while the left value is considered the value. We can read it as it having a certain value at a given time. What we'll do is convert this time into our angle and the value into our slope speed modifier. So it will end up having a certain slope speed modifier at a given angle. We could leave the time or angle to be from 0 to 1 for it to be normalized, but that will make it harder to understand angle ranges. So instead we'll change our time to be from 0 to 90. To do that, select the first curve preset at the bottom. Then right-click on the last key and choose Edit Key. In here, press Tab to go to the time field and set it to be 90 instead. Press Enter when you are done. Then press F to recenter the graph. This made it so that our time or angle will now go from 0 up to 90 degrees. Right now though, our slope speed modifier is always 1 at any given angle. Let's make it so that our slope speed modifier is 0.75 when the ground angle is within 15 and 55 degrees. To do that, right-click in the curve and press Add Key. Then right-click on the key and add it to be 0.75 on the value and 15 on the time. When that's done, press Enter and F to recenter the graph. Make sure the graph itself is selected or you will recenter on the selected key instead. Now add yet another key and edit it to be at 0.75 for the value and 55 for the time. Press F again to recenter. Right now our curve is looking like an actual curve, which makes it so that the slope speed modifier is actually descending from 1 to 0.75 as the angle increases instead of being either 1 or 0.75. This can be what you desire and is what makes animation curves quite powerful, but we want it to only be one of the two values. To do that is thankfully quite simple. We right-click on a key and open up the Both Tensions drop-down. We then set it to be constant. Do the same for the other key. Our values are now either 1 or 0.75 and not something in between. We do however have another problem. From our angle 55 upwards, it keeps being 0.75 instead of 1. To fix this, we'll edit the second key and set the value to be 1. The problem with this outcome though is that now our angle 55 is also 1. So edit again and make the time 55.1 instead. This now translates to the following. If the angle is on the range of 0 to 14.9, the speed modifier is 1. If the angle is on the range of 15 to 55, the speed modifier is 0.75. If the angle is on the range of 55.1 to 90, the speed modifier is 1. In Genshin, however, we can actually very slowly climb high-angled grounds up until a certain angle. After that angle, we'll fall or slide instead. So swap the 55.1 key value to be 0.4 and then add another key for 65.1 and make its value be 0. Make the 90 degrees key have a value of 0 as well. That's done for our slope modifier, so feel free to close the animation curve window and add back to the ground state script. In here, we need a way to get the slope speed modifier at the given ground angle. That translates to get the value of the curve at the given time. Thankfully, we can easily do that by using the animation curve evaluate method. So type in float slope speed modifier equals to movement data dot slope speed angles dot evaluate and pass in angle. We now have our curve value or slope speed modifier, so we need to set it up by typing in state machine dot reusable data dot movement on slopes speed modifier equals to slope speed modifier. We are now setting our slope speed modifier using an animation curve. We'll also return this value, so type in return slope speed modifier and update the return type to be float. In our float method, get its returned value by assigning it to a new float variable named slope speed modifier. Then, under that, we'll check if slope speed modifier equals 0f, we return. This makes it so we don't float on grounds that have an angle that's too high, which makes it so that we can't walk on them and will fall or slide instead. Of course, we still need to multiply our movement speed with this new variable, so open up the player movement state script and go to the get movement speed method. In here, simply add to the multiplication state machine dot reusable data dot movement on slopes speed modifier. When that's done, save everything and go back to Unity. Entering play mode and going to a slope should now update the speed that our player is moving at depending on the ground angle. We now have our slopes working, so it's time to start adding the remaining states. We'll be starting with our dashing state. To do that, we'll need to first add an input action for our dash. So open up the docked input actions window. In here, add a new action and name it dash. I'll leave the action type as button. Make sure you remove the clamp and invert processors Unity automatically added from our previous input. I assume it's a bug. For our binding, I'll bind it to the Shift key. We'll also add another binding and set it to be the mouse right click. This is simply because you can dash with any of these two keys in Genshin. When you are done setting the bindings, feel free to save the asset. Still in Unity, open up the grounded states folder in the player scripts folder. In here, we'll create a new C# script, which I'll name player dashing state. Open it up and remove the default methods. Swap the inheritance with player grounded state instead, and generate the constructor. We'll need to cache this state, so open up our player movement state machine script. In here, duplicate one of the properties and swap it with the dashing state. Don't forget to initialize it as well. When that's done, go back to the dashing state script. When entering this state, we'll have two possible outcomes. When we dash while moving, which is the equivalent of transitioning from a moving state to the dashing state, we'll dash towards our movement direction. When we dash while standing still, which is the equivalent of transitioning from the idling or the stopping states to the dashing state, we'll dash towards the direction that our player is facing. To do that, start by overriding the enter method. If our dash comes from a moving state, we'll simply update the speed modifier to be a bit higher. If it comes from a stopping state, we'll add a force instead, as our player isn't able to move without pressing a movement input key. Of course, that means that we need a speed modifier value, which also means that we'll need to create a dash data script. So, back in Unity, go to the states data folder and in the grounded folder create a new C# script to which I'll name player-data. Open it up, remove the default methods and the inheritance, and make the class serializable. Then add a speed modifier by typing in field, serialize field, field, range, from 1f to 3f, public float, speed modifier. I'll give it a private set. I'll also default it to 2f. Then go to our player grounded data script. In here, create a new field, serialize field, public player-data property named -data. I'll give it a private set. We can now return to our player-state script and set the state machine.reusabledata.movement speed modifier to be equal to movement data.data.speed modifier. We'll be needing more data from this class later on, so above create a new variable by typing in private player-data-data. In the constructor, set the -data to be equal to movement data.data. Then swap it in our enter method. This does it for when we are transitioning from a moving state, so for the from a stopping state case, we'll call in a new method named addForceOnTransition from stationary state. I'll add this method to an iteration named main-methods. I'll also add the enter method to an iteration named iStateMethods. In our new method, we only want to add a force if there was no input by the time we got into the dashing state. So type in if stateMachine.reusabledata.movementInput is different than vector2.0. If that's the case, then we can return. For the force, we'll add it towards the player facing direction multiplied by the movement speed. To do that, start by typing in vector3 character rotation direction equals to statemachine.player.transform.forward. We only need our horizontal rotation direction, so now type in character rotation direction.y equals to 0f. Here we'll actually set the force to the velocity variable of the rigid body. The reason why we'll be doing that is because we can move while dashing. That means that it is possible that our move add force will be called before dashing. Even if we were to reset the velocity before we add this force, it's possible that it will reset, add movement force, and only then add the dash force. Which again, because we are adding, it will become double the velocity. For some reason, doing the same as in the move add force of getting the player horizontal velocity and subtracting it from the add force only removed half of the velocity it needed to remove. I couldn't really understand why, which is why I decided to set the velocity variable right away, which seems to fix our problems, as it completely overrides the current velocity. So type in statemachine.player.rigidbody.velocity equals to character rotation direction multiplied by get movement speed. This should be enough to get the base of our dash working. However, in Genshin, if we dash twice in a small amount of time, we'll get into a cooldown where we can't dash for a second or two. We'll be calling this limit our consecutive dashes limit. The way they will work is as follows. When we enter our dashing state, we'll save the current time into a variable. Before we save that time, we'll check if the current time is less than our saved time plus a time we have defined, which is a time to be considered a consecutive dash. If the current time is less than that sum, then it is a consecutive dash, so we add 1 to the consecutive dashes count. Whenever that count is equal to the limit of consecutive dashes we have defined, we'll disable the dashing input for a few seconds. We'll be setting this data in our player-data script, so open it up again. We'll need 3 new properties, so duplicate the existing one 3 times. We'll name the first one time to be considered consecutive and default it to 1f. We'll also set its range to be from 0f to 2f. We'll name the second one consecutive dashes limit amount and make it an integer. We'll default it to 2 and make the range be from 1 to 10 without the f, as it's no longer a float. For the third one, we'll name it dash limit reached cooldown and default it to 1.75f. We'll also change the range to be from 0f to 5f. When that's done, add back to the player dashing state script. We'll start by creating our saved time variable, so type in private float start time. Then we'll create one to count how many consecutive dashes we have done, so type in private int consecutive dashes used. In our enter method, call in a new method we'll create named update consecutive dashes. I'll add this method to the main method's region. Inside, we'll start by checking if the dash we are in is a consecutive dash, so type in if is consecutive and generate the method. Inside, we'll return time.time, which is the current game time, lesser than start time, which is the time of when we have entered the previous dash, plus dash data dot time to be considered consecutive. So if we enter the current dashing state not too long after our previous dashing state, we'll consider the current dash a consecutive dash. That's done, so in our update consecutive dashes method, we'll add the not operator to the if statement and reset our dash count if it's not a consecutive dash. We do that by typing in consecutive dashes used equals to 0. After that, outside of the if statement, we'll add 1 to the used dashes count by typing in ++ consecutive dashes used. We now need to check if our used dashes count is equal to our dash limit amount, so type in if consecutive dashes used equals to dash data dot consecutive dashes limit amount. If that's true, we'll need to reset our used dashes count. To do that, type in consecutive dashes used equals to 0. This is likely not necessary if our cooldown is higher than the time to be considered consecutive, but this makes it a safe reset. We'll also need to disable our dash input for a few seconds. Unfortunately, it doesn't seem like the new input system has a built-in way of disabling an input for an amount of seconds, so we'll need to do it ourselves. We'll do that in the player input script. In here, we'll create a new public void method named disableAction4 and pass in an input action named action and a float named seconds. Don't forget to import the necessary namespace for the input action type, which is the type of our movement input, dash input, etc. Simply put, in this method we'll disable an action for an amount of seconds. We could add a list of inputs that we wanted to disable and then iterate through that list in the update method to see if we should enable any again, but will instead use a coroutine. This is simply because in this use case, it seems better for me to use a coroutine than to loop a list of disabled actions every update call. So, under our method, create a new coroutine by typing in private IEnumerator disable action and pass in the same parameters as above. Import any necessary namespace for the IEnumerator type. Inside, we'll disable the action, wait a few seconds, and then enable it again. To do that, simply type in action.disable. Then type in yield, return, new, wait 4 seconds, and pass in seconds. And then we enable the action again by typing in action.enable. That's all we need to do, so in our public method, we'll call this coroutine by typing in start coroutine, disable action, and pass in action and seconds. In case you didn't know, coroutines can only be called in a monobehavior class, which is why we are doing it here. With that done, go back to the player dashing state script. We can now call in statemachine.player.input.disableAction4 and pass in the action of statemachine.player.input.playerActions.dash and the seconds of dashdata.dashLimitReachCooldown. All that's left to finish this up is to set our start time variable value. We'll do this after we update consecutive dashes because we need to know the start time of the last dash and not the current one. If we did set it before we check if it's a consecutive dash, then we will be comparing the current pass time with itself, which will always lead to the same result. So in our enter method, right after we call the update consecutive dashes method, type in start time equals to time.time. We are now finished adding consecutive dashes, but we of course still need to add the transitions to and from this state. We'll start by adding the transitions to the dashing state. If we take a look at our movement system states, the states that transition to the dashing state are idling, all moving states, all stopping states, and the light landing state. In other words, every grounded state besides the dashing state. The reason why the dashing state doesn't transition to itself is that in Genshin, if we try to dash, we can actually only transition when we enter the sprinting state or the hard stopping state. It's a bit hard to understand it as the dashing state only happens for quite a small period of time. But if you keep pressing shift on that period of time, it will not dash again. So, knowing that, let's go to our player grounded state. Then in the add input actions callbacks method, call in statemachine.player.input.playerActions.dash.started plus equals on dash started. I'll also remove the callback in the remove input actions callbacks method. When that's done, I'll make the method be protected virtual and add it to the input method's region. I'll also rename the parameter to context. Inside, we'll simply update the state to be our dashing state. So type in statemachine.changeState and pass in statemachine.dashingState. Of course, right now this also adds a callback to the dashing state, which is why we've made this a virtual method. So open up the dashing state again and add a new region named input methods. In here, override the onDashStart method and leave it empty. Regarding the dashing state transitions to other states, if we take a look at our movement system states, at the end of the dashing animation, we can transition to the sprinting state if we keep holding the movement input key, or to the R stopping state if there was no movement input key pressed. We can also transition to the jumping state. Of course, we still don't have our stopping states, so we'll instead transition to the idling state, and won't yet transition to the jumping state either, as we haven't done it yet. However, as I've just said, these transitions will happen at the end of the animation. The way we'll be doing that is by using something called animation events. Simply put, we can add an event at a certain frame of the animation in the Animator tab, and call a specific method for when our animation enters that frame. That means that we won't actually be able to test our transitions to those states until we add animations, but we can at least start creating the methods that we'll need to call in our animation events. To do that, we'll add 3 new methods to our states, so open up the iState interface. The methods we'll be adding are public void onAnimationEnterEvent, which we can use for things like make the player immune to damage when the animation enters its first frame, and public void onAnimationExitEvent, which we can use for things like make the player vulnerable to damage again when the animation enters its last frame. In Genshin, an example of this will be the character's ultimate ability, which makes the character immune to damage when the animation is playing. For our last one, we have the public void onAnimationTransitionEvent, which we can use for transitioning to other states when the animation enters a certain frame. An example of this will be our dashing state, which is the reason why we are adding these events right now. When that's done, open up the player movement state script. In here, implement the 3 new methods we have added. I'll add them at the end of the iState methods region and also make them virtual. While we'll only be using them when we add animations, I'll also open up the player state machine script. In here, I'll create a new method by typing in public void onAnimationEnterEvent and call in current state dot onAnimationEnterEvent. Then I'll duplicate this method twice and swap enter with exit for the first one, and then enter with transition for the second one. When that's done, we can add a transition to our dashing state. To do that, open up the player dashing state script. In the iStates methods region, start by overriding the onAnimationTransitionEvent method. Inside, we'll check if stateMachine.ReusableData.MovementInput equals to vector2.0. We'll then transition to our R stopping state. Of course, we don't yet have it, so let's transition to the idling state instead by typing in stateMachine.ChangeState and pass in stateMachine.idlingState. We can then return. If that isn't the case and we have something in our movement input variable, which means we are pressing a movement key, we need to change to the sprinting state instead. So copy the line above and paste it under the if statement. Then swap the idling state with sprinting state. There is one last thing we need to do, and that's to override the onMovementCancel callback method and leave it empty. This makes it so we don't go to the idling state if we press and release a movement input key. Our dashing state shall now be finalized. Do note though that it will only completely work whenever we add animations to our system. But if we enter play mode, we should at least be able to dash once. Of course, it will never leave the dashing state, which has an higher speed modifier as well. With our dashing state done, we can now do our next state, which will be the sprinting state. This state has a few things to consider, but before we go ahead and talk about them, let's first see how can we enter this state. We enter the dashing state by pressing Shift or right click, and then at a certain frame of its animation, we transition to the sprinting state. The sprinting state will make the player go faster for a while, but only keep sprinting if we didn't stop holding the Shift or right click keys for a while. Let's look at an example in Genshin where we are running. While we are doing that, we press on the Shift key to dash and then unpress it right away. The dashing state will still enter the sprinting state, and the player will run faster for a second or two before the sprinting state transitions back to the running state. This is because we haven't held the Shift key long enough for our player to keep sprinting. Let's take a look at the same example, but we now don't let go of the Shift key for a while. Our player will now keep on sprinting. This stays true even if we let go of the Shift key, as we've held the key long enough already. Thankfully, the new input system has an old interaction that only calls a performed action once we've held the key for a desired amount of time, which makes this system quite simple to achieve. Of course, we should start by creating our sprint input. To do that, open up the docked input actions window. We'll add a new action named sprint. I'll leave it with the button action type as we don't need to continuously read its value. In the properties area, we'll add the hold interaction. We shall now get a press point and a hold time. I don't really know what the press point is, but I assume it's how much force we need to apply to a key or button for it to be considered pressed. We'll leave it with the default value. The hold time is what we need, which is how long we need to press the key for it to be considered pressed, which translates to how long does it need to be pressed to call the performed action. We'll untick the default from this one and set the amount of time to be 1 second. For our binding, we'll listen for the left Shift key and then add another binding for the mouse right click. When that's done, feel free to save the asset. Then open up the player sprinting state script in the moving states folder. We'll start by setting the speed modifier for this state, so override the enter method. I'll add it to a new region named iStateMethods. We need a value for our speed modifier, so back in Unity, go to the grounded moving state data folder and create a new C# script named player sprint data. Open it up and remove the default methods and the mono behavior inheritance. We'll also make it serializable. Then create a new field, serialize field, field range from 1F to 3F, public float property named speed modifier. I'll give it a private set. I'll also default it to 1.7F. Next, open up the player grounded data script. Duplicate the run data property and swap the run with sprint instead. When that's done, go back to the sprinting state script. Let's start by creating a variable to hold our data by typing in private player sprint data. Then in the constructor, type in sprint data equals to movement data dot sprint data. Next, in our enter method, we set the speed modifier by typing in statemachine.reusabledata.movementSpeedModifier equals to sprintData.speedModifier. Now, this is basically it for our sprinting logic, and the rest is mainly transition logic. Like we've seen before, if our sprint key isn't held enough time, our sprint state will go to the running state. To know if our key was held enough time, let's go to our variables and create a new private variable of type bool named keepSprinting. This variable will start as false, but if our sprint performed action is ever called, it will become true, as it means that the key was held long enough, so we need to keep sprinting. So add a new issue named reusable methods. In here, start by overriding the add and remove input actions callbacks methods. Then add a new callback by typing in statemachine.player.input.playerActions.sprint.performed plus equals on sprint performed. Don't forget to remove the callback as well. I'll add this method to an issue named input methods. I'll also update parameter name to be context. Inside, we'll simply set the keep sprinting variable to true. The way we'll transition to the running state in case this variable keeps on being false is by checking if this variable is false and if a certain amount of time has passed on the update method. The certain amount of time passed is that 1 or 2 seconds we've seen in our example before it transitions into the running state. So in our iStates methods region, override the update method. In here, type in if keep sprinting, we return, as that means we don't want to transition to another state. For our time we need 2 variables, one for whenever we enter the sprinting state, and the other one for how long can we stay here before transitioning. So above in our variables, create a new private float named start time. Then in the enter method, type in start time equals to time.time. For the other one, we'll do it in our data class, so open up the player sprint data script. In here, duplicate the speed modifier property and name it sprint to runtime, and default it to 1f. We'll also make the range be from 0f to 5f. When that's done, go back to our player sprinting state script. In the update method under our current if statement, we'll check if time.time lesser than start time plus print data.sprint to runtime. If this is the case, it means not enough time has passed for us to transition to the running state, so we need to return. Otherwise, we'll call in a new method named stopSprinting. I'll add this method to a new issue named mainMethods. In here, we'll either transition to the running state or the stopping state, just in case we have entered this method at the same time that we have stopped any movement input, which will be extremely rare but can still happen. Of course, we don't have our stopping states yet, so we'll transition to the idling state instead. To do that, type in if statemachine.reusabledata.movementInput equals to vector2.0. Then we transition to the idling state by typing in statemachine.changeState and pass in statemachine.idlingState. We of course return right after. Otherwise, we'll need to transition to the running state, so copy the line above and swap idling state with running state. That's it for our transition from sprinting to running. However, there is yet another use case. We have seen us going from running to sprinting to running, but we haven't yet seen what happens when we go from walking to sprinting to walking. What happens is a bit weird, but likely the way they've decided to smooth the transition. If we take a look at the Genshin Impact example, we can see that our sprinting still changes to the running state, but then our running state changes to the walking state after a small amount of time. We'll add this logic of swapping to our walking state in the running state, so open up the player running state script. The logic will be quite simple. If we enter the running state while the showedWalk property was true, then it means we entered the state through the sprinting state. This is because if that was not the case, we should have entered the walking state instead, as our showedWalk property is set to true. So start by overriding the update method. In here, type in if not statemachine.reusabledata.showedWalk we can return, as it means we should be running, as the should walk property is set to false. Otherwise, after an amount of time passes, we'll need to change the state to the walking state. The logic is much like our sprinting to running logic. So above, we'll create a new variable for the start time by typing in private float start time. Then in the enter method, set the start time to be time.time. We now need the time it takes to transition. We'll do that in the player sprint data, as that's the reason why we need this logic here. So open it up. In here, duplicate the sprint to runtime property and change its name to run to walk time. I'll default it to 0.5f and update the range to be from 0f to 2f. Feel free to do this in the player run data if you prefer it that way. We can now go back to the running state. In here, we'll create a variable for our sprint data, so type in private player sprint data. And then in the constructor, type in sprint data equals to movement data dot sprint data. Then in the update method, we'll type in if time.time lesser than start time plus sprint data dot run to walk time, we return. Otherwise, we can call in a new method named stop running. I'll add this method to an iteration named main methods. We'll do the exact same as we did in our sprinting state here, but transition to the medium stopping state instead, which will need to be our idling state for now. So type in if statemachine.reusabledata.movementInput equals to vector2.0. If that's the case, we change the state to be the idling state. We should also return right after. Otherwise, we copy this line and swap the idling state with walking state instead. When that's done, go back to the player sprinting state. We'll still need to do one thing here, and that's setting our keep sprinting variable to false whenever we exit the sprinting state, as otherwise it will always keep on sprinting when we come back to this state, because we are caching in our states and not initializing new ones, meaning our variable data will remain intact. So in the iState methods region, start by overriding the exit method. In here, simply type in keep sprinting equals false. And that's all we need for our sprinting state. We can also transition to the jumping state from the sprinting state, but we haven't done it yet, so we can do it for now. We can't really test it either, as we don't have animation events, but it should be working. If you wanted to try it out, you could always change from the dashing state to the sprinting state after a certain amount of time has passed, instead of it being on the animation event. With our dashing state and sprinting state done, we can now step ahead into our stopping states. These are the states that will be used whenever we stop pressing our movement input keys, and will represent the different stopping motions. Thankfully, these won't need any input action themselves, as all we need to know is if the movement input action was cancelled. Of course, we still need to create their state scripts. So head over to the player scripts grounded states folder. In here, create a new folder named stopping. Inside of this new folder, create 4 new C# scripts. Player stopping state, player light stopping state, player medium stopping state, and player hard stopping state. Start by opening up the player stopping state script. Remove its default methods and swap the inheritance with player grounded state instead. generating the necessary constructor. When that's done, go to the other 3 stopping states and do the same, but inherit from the player's stopping state instead. Then, open up the player movement state machine script and cache the 3 new stopping states. Light stopping state, medium stopping state, and hard stopping state. Initialize them as well. Add back to the player stopping state script when you are done. The way stopping works in Genshin is by slowly coming to an halt and not by instantaneously stopping. In other words, the player starts decelerating the moment we stop pressing a movement key, or at the end of the dashing state animation if we didn't press the movement key in the first place. Now all that changes between the stopping state's logic is at what force the player will decelerate. Because of that, we can add the deceleration logic in our player stopping state script and individually set the force in each state. We'll start by actually setting the speed modifier by overriding the enter method and typing in stateMachine.ReusableData.MovementSpeedModifier equals to 0f. Although likely not necessary due to a few transitions we'll be adding, this makes it so that we can't move while in our stopping states. I'll add this method to a new region named iStateMethods. For our deceleration, we'll be creating a method in our player movement state script, as we'll later on need to decelerate the player in our swimming system, so feel free to open it up. We'll add it in our reusable methods region, so when you are there, type in protected void decelerate horizontally. Remember that we only need to decelerate our player in the horizontal axis. We'll be doing that by using the add force method. Also remember that because our speed modifier is 0, the move method add force won't be called, which means we can call this add force here without any problems, even if it is a force in the same axis. However, we want our player to slowly decelerate and not for it to have an instant change on its velocity, so we can't or shouldn't use the velocity change force mode here. If we take a look at the same image we've seen previously made by NodeKey, we can get our desired force mode by knowing 2 things. We want our player to slow down over time, which means we want our force to depend on how much time has passed, or in other words, to be time dependent. Not only that, we don't want our player mass to have any matter on the deceleration, so we know that our force is mass independent. This leads us to the force mode known as acceleration. Of course, we don't want to accelerate our player, but to decelerate. The way we do that is simple. We'll simply slowly accelerate our player towards its opposite direction, which we can get from its current velocity. Of course, we'll only add this force while the player velocity is over 0 or over a close enough value to 0. This is because if we didn't check for our velocity, we would keep decelerating the player even if we had already stopped. Of course, this means that we will start moving backwards. Not only that, but because we are using physics, we can't expect our velocity to reach exactly 0 when we are adding forces. so we'll instead check for a bit of an higher value than 0. Of course, even if we do stop adding more deceleration forces, the forces we've added before will still be there. Physics of course takes care of slowing it down, but it does so slowly if there are no collisions, so our player will slide for a while. We could reset to player velocity once we've come to the point where we are almost at 0, but because these states will transition to the idling state at the end of their animations, we'll actually not need to reset to player velocity here, as we already reset to player velocity when we enter the idling state. With that in mind, in our decelerate method, start by typing in vector3 player horizontal velocity equals to get player horizontal velocity. Then we'll add a force by typing in statemachine.player.rigidbody.addForce and pass in minus player horizontal velocity, which gets the opposite direction of our velocity, and pass in force mode.acceleration for our force mode. Note that this force mode is multiplied by delta time, as it's a time-dependent force mode. Of course, we want to set how fast we want to decelerate our player, so we'll need to multiply our horizontal velocity with some other value that we'll set in each state individually. To do that, start by opening up the player state reusable data script. In here, duplicate the last speed modifier property and rename it to movement deceleration force. Then go back to the player movement state script and multiply the horizontal velocity with statemachine.reusabledata.movement deceleration force. With that done, we now need to create the necessary data property to be able to set this force through the inspector. Before we do that though, we'll first create another method. This method will simply tell us if the player is moving horizontally, because again we'll only decelerate our player if it isn't moving. So under our decelerate horizontally method, type in protected bool is moving horizontally and pass in float minimum magnitude defaulted to 0.1f as a parameter. The parameter is required because we'll know if the player is moving by checking the magnitude of its horizontal velocity. The magnitude of a vector is simply the distance between the vector origin and the vector point. In this case, it will be the distance between the origin and our velocity. If the distance is 0 or close to 0, then it means we aren't moving or are almost completely stopping. This is mostly so that we don't check if the x or the z is over 0, and can instead check one variable only. So type in vector3 player horizontal velocity equals to get player horizontal velocity. However, this velocity comes with an y value. Even when this y is 0, it changes our magnitude results. This is because we are checking for a point, so 0 is part of its coordinate. To fix that, create a new vector2 named player horizontal movement and set it to be equal to new vector2 player horizontal velocity.x and player horizontal velocity.z. Then return player horizontal movement dot magnitude is greater than minimum magnitude. These are all the methods we'll need, so now go back to the player stopping state script. In here, we'll do both the isMoving check and the deceleration in the physics update method, so override it in the iState method's region. Then start by checking if not is moving. In case this is true, meaning that we aren't moving, we can return. Otherwise, we can call in our decelerate horizontally method. This takes care of decelerating our player. However, we still aren't setting the force we want to decelerate with. To do that, let's head back into Unity and go to the player grounded states data folder. In here, create a new folder named Stopping. Inside, create a new C# script named Player Stop Data. Open it up and remove the default methods and inheritance. We'll make it a serializable class. We'll be creating 3 forces, one for each stopping state. So start by typing in field, serialize field, field range, from 0f to 15f, public float, light deceleration force, and give it a private set. Then duplicate this line twice and swap light with medium and then with hard. I'll default the light force to 5f, the medium force to 6.5f, and the hard force to 5f as well. When that's done, open up the player grounded data script. In here, add a new property by typing in field, serialize field, public player stop data with a private set. That's all the data we'll need, so let's now set the deceleration force property to its corresponding values. Start by opening up the light stopping state. Here override the enter method and set the state machine .reusable data .movement deceleration force to be movement data .stop data .light deceleration force. I'll add this method into a new region named iStateMethods. When that's done, copy this whole region and open up the player medium stopping state script. In here, paste the region and swap the light force with the medium deceleration force. Then do the same in the player hard stopping state script. That's all we need for our deceleration logic, so we'll now take care of the transitions to and from these states. We'll start with our transitions to these states by taking a look at our movement system states. As we've seen before, we had multiple states that transition to a stopping state, but that we have decided to transition to the idle state instead while we didn't have them. Those states are walking, running, sprinting, and dashing. The walking state will transition to the light stopping state. The running state will transition to the medium stopping state. The sprinting and dashing states will transition to the hard stopping state. Start by opening up the player walking state script. In here, we'll override our onMovementConsole method in the input methods region. Remove the base method call and transition to the light stopping state by typing in statemachine.changeState and pass in statemachine.lightStoppingState. Then copy this method and go to the player running state script. Paste the copied method into the input methods region and swap the light stopping state with medium stopping state instead. When that's done, go to the player sprinting state script. Paste the copied method into the input methods region again and swap it to the hard stopping state instead. The dashing state will also transition to the hard stopping state, so open it up and in our onAnimationTransition event method, swap the idling state with hard stopping state instead. That's it for the states that transition to the stopping states. So we now need to set the state transitions from the stopping states. Taking a look at our movement system states again, our stopping states can transition to idling, walking, running, dashing, and jumping. Whenever any stopping state animation reaches its last frame, we'll transition to the idling state. Whenever we press a movement key again, we'll transition to the walking or running state, depending on the walk toggle value. We'll also be able to transition to the dashing and jumping states as usual, although we won't be able to add the transition to the jumping state yet, as we don't really have it. With that in mind, start by opening up the player stopping state script. In here, in the iState methods region, we'll override the onAnimationTransition event method. Inside, we'll transition to the idling state by typing in statemachine.changeState and pass in statemachine.idlingState. This method override makes our onMovementCancelled method useless, and although it shall never be called because not only will we only enter a stopping state when we have already stopped input, but also add transitions to the moving states, let's override it and leave it empty. I'll also add it to an region named input methods. Now, previously we've talked about going to moving states through the callback and the update method for situations where we could press the movement input in a state like jumping, where the callback won't be called as the input had already been pressed. In our stopping states case, we'll never enter them from the jumping state. We'll also never enter our stopping states until we release our movement input keys. This simply means that we'll never be able to enter a stopping state with our movement input keys already pressed. For that reason, we can add a callback to our movement started action instead of using the update method. To do that, add a new region named reusable methods. In here, override the add and remove input actions callbacks methods. Inside, type in statemachine.player.input.playeractions.movement.started plus equals on movement started. Don't forget to remove the callback as well. When that's done, I'll add the new method to the input methods region. I'll also rename the parameter to context. Inside, we can simply call the grounded state onMove method, which takes care of transitioning to the moving states. For our dash transition, it's already set up in the grounded state, so we don't need to add it here. That means that we are now transitioning to the idling state, the moving states, and the dashing state. Of course, the jumping state will be added whenever we add jumping to our system. However, there is one more thing to keep in mind. In Genshin, in the light and medium stopping states, we are able to transition to the walking state at any given moment. However, that doesn't seem to be the case for the hard stopping state. Whenever we try to do it, the player doesn't start walking or moving at all, meaning that we can only transition to the running state. To copy this situation, open up the player hard stopping state script. In here, we'll simply override the onMove method, which we've made virtual in our grounded state. I'll add it to a new region named reusable methods. In here, remove the base method call and then check if statemachine.reusabledata.showedWalk, and if that's true, we return, as we can transition to the walking state. Otherwise, we should transition to the running state by typing in statemachine.change_state statemachine.running_state. That's all we need for our stopping states, so save it all and go back to Unity. Entering play mode, we shall now be able to stop after walking, running or sprinting, by slowly decelerating instead of instantaneously stopping. Of course, because we haven't yet added animations, our animation event is never going to be called, which means we'll never enter the idling state. Because of that, our player will very slowly slide for a while. We also won't be able to test our dashing transition yet. With our stopping states added into our system, the only remaining states are the jumping and light landing states. Before we take a look at those states though, we need to add something else first: automatic rotations. If we take a look at Genshin Impact, if we press a movement key like S when looking forward, and then press it right after, the player will still finish rotating itself, even though we are not pressing on the key anymore. Genshin offers this automatic rotation in multiple places: when dashing, when stopping, and when jumping. In the dashing state, if we ever tap a movement key to change its direction in the middle of the dashing or even before dashing, the player will still finish rotating. In the stopping state, the player simply finishes rotating towards the direction that the player was going to move. This means that it actually automatically rotates when stopping and not when moving, which makes sense as we already rotate while moving. In the jumping state, we have two possible outcomes. If by the time that we enter the jumping state, we are pressing on a movement key, then the player will rotate and jump towards the movement direction even if we were looking somewhere else. This happens either we leave the key pressed or unpress it, as long as it's after we enter the jumping state. If by the time that we enter the jumping state we are not pressing any movement key, then the player will jump towards its facing or forward direction, which doesn't really need any extra rotation. We'll be adding the first two cases here and then add the jumping case whenever we add jumping into our system, which should be right after this. Thankfully, when we've added movement to our player, we already created reusable methods that allow us to rotate our player, so it will be quite simple to add this feature. We'll start with our stopping states, so open up the player stopping state script in the stopping states folder. What we'll do here is quite simple. In the physics update method, we'll simply make sure our player keeps rotating until it reaches the target rotation. We'll use the physics update method as our reusable methods use the rigid body move rotation method, which involves physics. So in the physics update method, above the rest of the code, call in rotate towards target rotation. We don't need to check if it reached the target rotation already, because we already do that inside of the rotation method. And that's really all we need to do. Whenever we enter a stopping state now, it will finish rotating even though we are not pressing on a movement key. When that's done, open up the player dashing state script. When dashing, we want to keep rotating in two occasions. When we enter the dashing state with a movement key already pressed, and when we press a movement key while already in the dashing state. Now, in the first case, because we'll be calling our move method, we'll already be rotating our player. However, it's possible that we release a key right after, which means that our player will stop rotating. Because of that, we need to make sure we somehow keep rotating. For the second case, let's say we enter the dashing state without any movement key pressed at all, and then pressed and unpressed a movement key mid-dash. For example, we could go from idle to dash and then press and unpress S quite fast. Because we aren't reading for that change in input anywhere, our player won't keep rotating towards where it showed when we released the key. With that in mind, let's start by creating a new variable by typing in private bool should keep rotating. Then in our enter method, after we add the force, we'll type in should keep rotating equals to stateMachine.reusableData.movementInput different than vector2.0. This will become true if we are pressing any movement key or false if we are pressing none. This is just in case we release the key right after to make sure it keeps rotating regardless. For our second case, we'll need to make this variable true whenever we press a movement key, which we can know through the performed action. So add a new region named reusable methods. In here, override the add and remove input actions callbacks methods. Then add a new callback by typing in stateMachine.player.input.playerActions.movement.performed plus equals on movement performed. Don't forget to remove it as well. Remember that performed for the value action type will be called right after started and every time a new key is pressed, even if we didn't release the old one, which is what we want. I'll add this method to the input methods region and also rename the parameter to context. Inside, all we need to do is to set the should keep rotating variable to true. When that's done, we need to make our player rotate, so head over to the iStateMethods region and override the physicsUpdate method. In here, first check if not should keep rotating, and if we shouldn't, we can then return. Otherwise, we call in rotate towards target rotation. That's mostly it, but we currently have a problem. Let's say we are facing forwards and tap S. This updates our target rotation to be backwards. In the middle of this rotation, however, we press Shift to enter the dashing state. Because by the time we have entered the dashing state, there was no movement key pressed, our player will dash towards its facing direction. However, at the end of our dash, we'll transition to the hard stopping state, simply because we were not pressing any movement key. What happens next is that our stopping state will rotate towards its target rotation, which is still backwards from when we have pressed our S key. This happens because we are only updating our target rotation when we move, and we haven't pressed any movement key since the first S key press. Thankfully, this problem is quite simple to solve. Whenever we dash, we simply need to update our target rotation to be our player forward direction. So in our add force on transition from stationary state method, type in right after we get our character rotation direction, update target rotation. For the direction, pass in character rotation direction. For the second argument, we'll pass in false, as we don't want to consider the camera rotation, but only the player forward direction or our movement input direction. There is one more thing regarding our dash rotation, which is at what speed our player rotates. If we take a look at Genshin, our movement and stopping rotation should be around 0.14 seconds. This is how I obtained the 0.14 from our existing target reach time. However, in both the dashing and jumping rotations, the rotation takes only about 0.02 seconds. Let's update this rotation reach time by opening up our player dash data script. In here, after our speed modifier, add a new field serialized field public property of type player rotation data named rotation data. I'll give it a private set. When that's done, go back to the player-state script. In the enter method, we now simply type in statemachine.reusabledata.rotation_data equals to -data.rotation_data. Of course, we don't still have this property, so generate it by pressing Alt-Enter and choose Generate Property. Then go to that property and make it set public. We of course need to set its default value, so open up the player movement state script and in the initializeData method, just before setting our reach time, type in statemachine.reusabledata.rotation_data equals to movementData.baseRotationData. Then swap the movementData.baseRotationData from our reach timeline with statemachine.reusabledata.rotation_data. When that's done, select these two lines and extract them to a new method named setBaseRotationData. I'll make this method protected and add it to the reusable methods region. The reason why we have made this a new method is because we need to make sure we set our rotation data back when we exit the dashing state, as otherwise our rotation will keep on being 0.02 seconds. To do that, open up the player-state script. Then, in the iState methods region, override the exit method. In here, call in setBaseRotationData. When that's done, save it up and add back to Unity. In the second inspector tab, update the -data rotation Y value to be 0.02 seconds. If we enter play mode now, our player should rotate correctly even when we unpress our movement keys.
The next state we'll be taking care of is the jumping state, as we now have everything we need to add it to our system. Before we start doing that though, we of course need to know how jumping works in Genshin. There are several outcomes when it comes to jumping, depending on the current player input or state. The most basic jump is when idling. This will add an upwards force and make the player jump in the same place, without moving horizontally. The outcome that follows it is jumping while moving. This will still add a normal upward force, but also jump towards our movement direction. One thing to note is that Genshin seems to have a different force for each moving state. This force doesn't seem to have anything to do with the speed modifier or with the velocity that our player is moving at. Another outcome is when rotating. We have already seen this previously, but if we press space when we have a movement input key pressed, then the player will jump towards the movement input direction. If we jump to the opposite side, then we'll rotate our player and jump towards that side. We also know from our automatic rotation part that it takes 0.02 seconds for this rotation to happen. If we pressed a movement key and unpressed it right after, if we end up pressing space while the player is still rotating, then the player will stop rotating and jump towards its facing direction. This is because the stopping states will have their own forces. Of course, if we were back to the idling state already, we will jump in the same place. And last but not least, we can jump while on a slope. In Genshin, when on a slope, we jump with a lower force. This is because if we were to jump with our normal force when we are facing a slope, it will be too much of a force and we wouldn't really jump but instead slide on the slope. This of course happens when moving. as we are adding an horizontal velocity towards the slope. Now that we know the possible outcomes of the jumping state, we'll start by creating its input. To do that, head over to the docked Input Actions window. In here, we'll add a new action named Jump. If Unity added the old interaction to it, feel free to remove it. We can leave the action type as button. For our binding, we'll listen for the spacebar key. When that's done, feel free to save the asset. Next, we'll create our jumping state script. To do that, head back to the Player States Scripts folder. In here, create a new folder named Airborne. Inside of the Airborne folder, we'll create two new C# scripts, Player Airborne State and Player Jumping State. Start by opening up the Player Airborne State script. In here, remove the default methods and swap the inheritance from monoBehavior to Player Movement State. Generate the necessary constructor as well. When that's done, open up the Player Jumping State script. Remove the default methods and swap the monoBehavior inheritance with Player Airborne State instead. Make sure you generate the necessary constructor. We now need to cache the jumping state, so open up the Player Movement State Machine script. In here, create a new property for our jumping state. Make sure you initialize it as well. With that done, go back to the Player Jumping State script. When jumping in Genshin, we aren't able to move, simply meaning there's no air movement like there is when gliding. We can easily not allow movement in our jumping state by setting our speed modifier to 0, so override the enter method. Then, inside, type in stateMachine.reusableData.movementSpeedModifier equals to 0f. I'll add this method when we reach the named iStateMethods. We can now start thinking on how to add the jump force. The first thing we need is the force that we'll want to add when jumping, which changes depending on the current player state. To create it, head over to the Player State Reusable Data script. In here, under our author vector trees properties, type in public vector tree current jump force and give it a public set. Now, because we'll be assigning this property value to a temporary variable, we don't really need to do the same thing we did in our other vector tree properties. This is of course because we'll not actually update the x, y and z of this vector tree, but only the one of our temporary variable. With that done, go back to the Player Jumping State script. In our enter method, we'll now call in a new method named jump. I'll add this method to an iteration named main-methods. We'll start by assigning our current force into a temporary variable. So type in vector3 jump force equals to stateMachine.reusableData.current jump force. The reason why we are adding a temporary variable here is because the jump force will need to be changed depending on the slope angle as well as the jump direction. For example, let's say we want to add a force of 3 in the horizontal axis. 3 will always be a positive force, which will always jump towards the same side, even if we intended to jump in the opposite direction. We'll need to update it to be relative to our desired direction, which we might need to make it become -3 instead. We'll also need to reduce it when on slopes to be a certain percentage of the original force, which requires us to hold that original force somewhere. By creating a temporary variable, we can update it as we desire without updating the original property value. With that in mind, we'll now add our force by typing in statemachine.player.rigidbody.addForce and pass in jump force. We'll also be setting the force mode to be forceMode.velocityChange, as it shall be both time and mass independent. Of course, we need to update our jump force to be able to jump in the direction that our player is moving and not towards the positive force direction only. Not only that, but currently if we set a force of 3 while we are only moving in one of the horizontal axes, we'll still jump towards both horizontal axes, as we are adding a force of 3 to both axes. To solve these two problems, we can simply multiply our jump force with the player forward vector 3. The player forward is basically our player normalized direction, which is the equivalent of where our player is facing. This means that if we are only moving in one horizontal axis, the force of the other axis will be multiplied by 0, which means we won't jump towards that direction. To be able to do that, just before adding our force, type in vector3 player forward equals to statemachine.player.transform.forward. Then we multiply our jump force.x with player forward.x and our jump force.z with the player forward.z. We don't want to multiply our y-axis as our player forward direction has no effect whatsoever in our upwards velocity. That's the very base of our jump done, and we can now jump with a given force. However, before we jump, we shall reset any velocity we have, as we don't want our current player velocity to impact our jump force. To do that, above our addForce method, call in reset velocity. This situation is one of the reasons why our reset velocity method sets the velocity variable right away for an instantaneous change. If we didn't do that, jumping multiple times in a row could make the player jump more than it should. Again, I'm not entirely sure why that happens, but I assume the order of the add forces is being swapped, or the force we were trying to add was now more than the player force at the time that the addForce method was actually called. Of course, we still need to create the data classes to be able to set the corresponding jump forces. To do that, save everything and head back to Unity. When you are there, go to the player states data folder. In here, create a new folder named Airborne. Inside, we'll create two new C# scripts, player airborne data and player jump data. Start by opening up the player jump data script. In here, remove the default methods and inheritance and make this class serializable. We'll be adding one property for each force strength. To do that, start by typing in field serialize field public vector3 stationary force with a private set. Then duplicate this property 3 times. Swap their names to weak force, medium force, and strong force. When that's done, open up the player airborne data script. Remove the default methods and inheritance and make this class serializable. We'll add a jump data property here by typing in field serialize field public player jump data. I'll give it a private set. When that's done, open up the player SO script. Duplicate the existing grounded data property and swap the grounded with airborne instead. Once you are done doing that, save it all up and head back to Unity. We'll be setting our forces values, so open up the second Inspector tab. In the Airborne Jump Data area, we'll set the following forces. For the stationary force, we'll set y to a value of 5. For the weak force, we'll set the vector to 1, 5, 1. For our medium force, we'll set the vector to 3.5, 5, 3.5. For the strong force, we'll set the vector to 5, 5, 5. With that done, we now need to assign these values in the corresponding states. If we take a look at Genshin, we can see our forces being applied to the following states. Idling, which gets set to the stationary force. Walking and light stopping, which gets set to the weak force. Running and medium stopping, which gets set to the medium force. Sprinting, dashing and hard stopping, which gets set to the hard force. Regarding the forces, they also seem to depend on the size of the selected character. For example, smaller characters seem to have the same medium and strong jumping force, while taller characters seem to have a stronger strong force. Thankfully, if you ever need to differentiate their forces like that, you can simply create another scriptable object for smaller or taller characters. We will however not do that and just use our existing player scriptable object. Now, sometimes the stopping states use the stationary force at any given frame, and sometimes they use the weak, medium and hard forces at any given frame as well. I couldn't really understand what was the factor that decided which force to use, as it didn't seem to be at a certain frame. To make it easier for us, we leave the same force for the whole animation duration. If you did want to set a stationary force in a certain frame, you could do it by overriding one of the animation event methods and set the current jump force to the stationary force there. Upon further inspection after recording everything, I notice it will depend on the last jump we have made. So if we have jumped while idling, the stopping state will jump with that force. It wasn't the case for every single stopping state, as the lighter stopping states, for example, wouldn't transition to the stronger force. It seems to cause a bug sometimes where something like dashing and jumping would cause the jump to use a stationary force as well. So because I don't find this way of doing it to be correct, and mainly because I've already recorded everything, I'll go with my current implementation. If you do want to try to be as close as possible to the actual implementation, you will likely not set the forces in the stopping states. With that in mind, we'll now assign the forces in the corresponding states. We'll start with the idling state, but because we'll need to reference the airborne data a few times, start by opening up the player movement state script first. In here, we'll create a new variable by typing in protected player airborne data. Then, in the constructor, we type in airborne data equals to statemachine.player.data.airborne data. When that's done, open up the player idling state script. In the enter method, we'll set the jump force by typing in statemachine.reusabledata.currentJumpForce equals to airborne data.jumpdata.stationary force. When you are done doing that, copy this line and open up the player walking state script. Paste the line we just copied in the enter method and swap the stationary force with weak force instead. Copy the line again and open up the player light stopping state script. Paste the line in its enter method. Next, open up the player running state script. Paste the line in the enter method and swap it with medium force instead. Copy the line again and open up the player medium stopping state script. In here, paste the line in the enter method as well. When you are done doing that, do the same for the sprinting, dashing and hard stopping states, but swap the medium force with strong force instead. That's it for our forces, so before we add the remaining features, we'll actually make it so that we can transition to and from the champion state. This will allow us to test what we have done so far. Taking a look at our movement system states, we can transition to the champion state through the following states. Every grounded state. This basically means that we can add a transition to the champion state in our player grounded state script. So, knowing that, open it up. In here, in the Add Input Actions Callbacks method, found in the Reusable Methods region, we'll add a new callback by typing in statemachine.player.input.playerActions.jump.started plus equals on jump started. Don't forget to remove the callback as well. I'll make this method protected virtual and add it to the input methods region. I'll also rename the parameter to context. To transition to the champion state, we simply type in statemachine.changeState and pass in statemachine.championState. That's it for the transitions to the champion state, so we'll now add a transition from the champion state. For now, because we don't have the falling and the landing systems in our system, we'll simply transition to the idling state whenever we jump and touch the ground again. The way this transition works is by having a trigger collider at the feet of the player, waiting for the onTriggerEnter call whenever the collider enters the ground after jumping. Knowing that, we need two things: a trigger collider and a way to call the onTriggerEnter method. Let's start with our trigger collider by going back into Unity. Selecting our player game object, create a new child game object and name it Trigger Checks, or any other name you'd like for colliders that will check for something. Inside of this Trigger Checks game object, create yet another child game object named Ground Check. Adding a collider in a different game object allows us to add a specific layer to it, which means we can control what a specific collider collides with. In the Ground Check game object, add a new component of type Box Collider. A sphere will likely be fine as well, but I'll go with a box. When that's done, make the collider a trigger by ticking the isTrigger checkbox. Right now though, its center and size aren't the most correct. So edit the center to be 0, 0.1, 0, and the size to be 0.25, 0.2, 0.25. It shall now be positioned around our feet and just slightly touching the ground. If your capsule collider height is still at 100%, make sure this collider is able to touch the ground by updating its center or Y size if necessary. When that's done, we'll add a layer to this collider game object, so add in a new layer named Ground Check. When you are done adding it, go to Edit, Project Settings, and Physics, and in the layers at the bottom, make sure you disable every collision for the Ground Check layer, besides collisions with the environment layer. This ensures that our trigger collider can only collide with the environment, meaning that other game objects, such as other players or enemies, won't call the onTriggerEnter method when being collided with. With our trigger collider added, we can now add the onTriggerEnter method. To do that, open up the iState script. In here, add in a new public void method named onTriggerEnter. Unity monobehavior onTriggerEnter method requires a collider parameter, so pass in collider as a method parameter. Make sure you import any necessary namespace. When that's done, open up the player movement state script and implement the onTriggerEnter method, making sure you add it to the iState methods region and remove whatever code is inside. make it a virtual method as well. With that done, open up the state machine script and create a new method to call the onTriggerEnter method by typing in public void onTriggerEnter collider collider. Make sure you import the necessary namespace. Inside, call in current state .onTriggerEnter and pass in collider. Then open up the player script. In here, under the start method, call in the monoBehavior onTriggerEnter method. I'll rename the parameter to collider instead. Inside, we can simply call in movementStateMachine.onTriggerEnter and pass in collider. All that's left now is to check if we collided with the ground and transition to the idling state if that's the case. To check for that collision, we can either use tags or layers. To be honest, I couldn't find which one is the best for these comparisons. So I'll go with layers by using a layer mask to compare them, simply because layers seem to be the most related to collisions. Unfortunately, we can't or shouldn't really compare a layer mask with a collider layer right away, and it's a bit bothersome to compare them when you don't understand how it works. But I'll try to explain it as best as I can. Before I explain it though, open up the player layer data script. This is where our ground layer reference is in, and we'll now add a new method that allows us to compare layers, or more specifically check if a layer mask contains a certain layer. To do that, create a new method by typing in public bool contains layer and pass in layer mask, and int layer. Inside, we simply return, between parentheses, 1 lesser than layer ampersand layer mask, and outside of the parentheses, different than 0. Now, if you have never seen this before or never compared layers before, you are likely completely lost on the meaning of this return statement. To be honest, I was too and had no idea what this meant. To be able to fully understand it, let's go bit by bit. We have layer masks and we have layers. If you remember the layer inspector, you know that we can have up to 32 layers, some already used by Unity. This is basically a 32-bit bit mask. In human readable numbers, these layers will be represented from 0 to 31, which is what people often use in their code. However, let's take a look at our environment layer in computer numbers. Using the inspector 32-bit bit mask, it will be represented by a bit mask with a 1 at its 7th position. This is because our environment layer is the layer 6 in the inspector, and because layers in the inspector start from 0, the actual position is that number plus 1. Of course, our ground check layer would have a 1 in the 8th position instead, and so on. So that's how our layers are represented in the 32-bit bit mask. A layer mask is also a 32-bit bit mask. If you remember from our inspector, a layer mask can be used to select multiple layers. So while it starts with zeros for the whole bit mask, the moment we select one or more layers in the inspector, the 32-bit bit mask will start turning zeros to ones in the respective layer position. For example, selecting the environment layer will have a 1 at the 7th position. Now, if our layer mask bit mask is looking the same as our layers bit mask with our environment layer selected, why can't we compare our layer with our layer mask? The reason why is that while layer masks are represented with computer numbers, layers are represented with human numbers, simply to make it easier for us to understand them. So, when we compare the environment layer with a layer mask, we are comparing a human number with a computer number, which won't work out very well. For raycast cases, because we are passing in the human number to the layer mask argument, that human number will be converted to a computer number represented by the layer number. For example, if we passed in 6, as that's our environment layer number, it will be transformed into binary and will be represented by a 32-bit bitmask with a 1 at its second and third positions. This is because 6 in binary is represented by 110. That 110 will then be transformed into a 32-bit bitmask, as the raycast requires a layer mask. Of course, this will simply add the remaining bits or zeros to its left side. If we now compare it with a layer mask bitmask, we can see that they do not look the same at all, even though we've passed in the correct layer number. The fix to all of this is quite simple. We simply need to convert our human number to a computer number, which is what our weird formula does. Starting from the beginning, our 1 represents the first position of the bitmask. The lesser than sign is called bitwise shifting. Simply put, we tell our bitmask to shift an amount of times to the left. So our 1 that was in our first position will now shift itself layer amounts to the left. If our layer is the environment layer, then it will shift itself 6 times to the left, which means it will now be in the 7th position. With this, our human number is now a computer number, and represents the same bitmask that our layer mask represents. This means that comparing them will give us the desired result. However, remember that a layer mask can contain multiple layers. If we were to also add in the ground check layer, it will now have a 1 in the 7th and 8th position, which will now be different than our environment layer bitmask. That's where the ampersand layer mask comes in play. The ampersand sign is a bitwise operator and represents the AND operator. This operator will compare all bits in both of our bit masks and return 0 when one of the same position bits is 0, or 1 when both bits are 1. Simply put, it keeps the common ones between both bit masks. If the returned bit mask has any 1 in it, then it means that if we convert this bitmask computer number into a human number, it will return a value over 0. For example, in this case it will be 64 as it's a 1 in the 7th position. This means that our layer mask contains the passed-in layer. If the final bitmask were to return a bitmask with only zeros, then it would mean that the layer wasn't part of the layer mask. That's what our different than 0 is for. Again, if the final human number is 0, then it means the layer mask didn't contain the passed-in layer, as there was no 1 in the same bit in both bit masks. If the final human number is different than 0, then it means the layer mask contains the passed-in layer, as there was a 1 in the same bit in both bit masks. I'll leave a few links in the description if you want to dive deeper into it, but this should be enough for you to understand our use case. With that in mind, we'll also create another method to check if it's a ground layer. So type in public bool is ground layer and pass in int layer as a parameter. Inside, return contains layer and pass in ground layer and layer. That's all we need here, so now open up the player movement state script. In our onTriggerEnter method, we'll check if the object we have collided with is part of the environment by typing in if statemachine.player.layerData.isGroundLayer and pass in collider.GameObject.layer. Inside of this if statement, call in a new method named onContactWithGround and pass in collider as an argument. Return right after to make sure nothing else gets called. I'll make the method protected virtual and add it to the reusable methods region. We'll override this method wherever we need something to happen when we enter in contact with the ground. which we don't need in our movement state. We can use this method to transition to the idling state in our jumping state, but because I know we'll need to transition more times to the idling state, or more specifically to the light landing state whenever we add it, we'll actually add it to the player airborne state script, so open it up. In here, create a new region named reusable methods. Inside, override the onContactWithGround method. Then transition to the idling state by typing in statemachine.changeState and pass in statemachine.idlingState. Feel free to remove the base method call as well. This should be enough to test our current jump, so save it all up and go back to Unity. If we enter play mode, our jump should now work and its force should depend on the current player state. We also cannot move mid-air. However, we still need to finish up a few features from the jumping state: automatic rotation, force modifier when on a slope, fixing the floaty jump feeling, and keep sprinting after jumping. We'll start with the automatic rotation, so go back to the player jumping state script. We need to automatically rotate our player if we have entered the jumping state with a movement input key pressed. Not only that, but currently we are always jumping to the player facing direction. This is not what should happen when we press a movement key, and should instead jump towards our movement input direction if that's the case. We'll start by creating a variable to know if we should rotate, so above type in private bool should keep rotating. Then, in the enter method, set the should keep rotating to be equal to statemachine.reusabledata.movementInput different than vector2.0. This makes it so we keep rotating if we have input. With that, we can now override the physics update method, and inside type in if should keep rotating. If that's the case, we can call in rotate towards target rotation. We are adding it inside of the if statement, as we'll have another if statement in this method later on. We shall now make it so that the player jumps towards the movement input direction instead of the player forward direction if we enter the jumping state with a movement key pressed. To do that, go to the jump method. The way we'll do this is by updating our player forward variable value to be the movement input direction instead when we have a movement key pressed. We can use the should keep rotating variable to know if our movement input key was pressed, as that's the condition we gave it in our enter method. So after our player forward variable, type in if should keep rotating. If that's the case, we'll update our player forward to be the movement input direction. However, we actually want the direction to be relative to the camera, as the movement input will be in world space. We can do this by getting the direction of our target rotation, which was updated when we moved before jumping. We also have already created a method before that guesses a direction given a rotation. So, simply type in player forward equals to get target rotation direction, and pass in statemachine.reusabledata.currentTargetRotation.y. This is a method that transforms a quaternion with a certain angle into a vector direction. Remember that even if we come here from a stopping state, we enter them with an updated target rotation already, so we don't need to update it here. Our player forward variable name no longer makes much sense, so we'll select it and rename it by pressing F2 or right-clicking on it and choosing rename, and set its name to jump direction. Of course, like we've seen before, both dashing and jumping have a different reach time, so we need to set that up. To set it up, open up the player jump data script. In here, create a new property by typing in field, serialize field, public, player rotation data, rotation data. I'll give it a private set. When that's done, save it up and go back to Unity. In the second inspector tab, set the jump data Y rotation value to be 0.02 seconds. Then go back to the player jumping state script and create a new variable above by typing in private player jump data. Then in the constructor, set it to be jump data equals to airborne data.jump data. In our enter method, we can now type in statemachine.reusabledata.rotation equals to jump data.rotation data. We should also not forget to reset this rotation data when exiting, so override the exit method and call in setBaseRotationData. If we save it all and head over to Unity, entering play mode should now have our jump working fine. That's great, but we shall now make sure we have a lower jump force when on slopes to make sure we don't get into the slopes when jumping, which will make the player look like he's sliding. This mostly happens on steeper slopes. To do that, head back to the player jumping state script. We'll do this by casting a ray in our jump method to know if we are on a slope and then update the forces if that's the case. To do that, before resetting the velocity, type in vector3 capsule collider center in world space equals to statemachine.player.collider.capsule collider data.collider.bounce.center. Then create the ray by typing in ray downwards ray from capsule center equals to new ray and pass in capsule collider center in world space and vector3.on for the direction. We can now cast our ray by typing in if physics.raycast and pass in downwards ray from capsule center and out raycast it. We need the distance of our ray now, so open up the player jump data script. In here, type in field serialize field range from 0f to 5f public float jump to ground ray distance with a private set. I'll default it to 2f. When that's done, go back to the player jumping state script. Pass into the raycast jump data.jump to ground ray distance. For our layer mask, we'll pass in statemachine.player.layerData.groundLayer. Then pass in query trigger interaction.ignore to ignore trigger colliders. If we hit something with this ray, we then need to know if we are on a slope. We'll of course be using the vector3.angle method again. To do that, type in float ground angle equals to vector3.angle and pass in it.normal and minus downwards ray from capsule center.direction. We now need a way to check for the angles and set the force accordingly, which we'll be doing by using animation curves. However, we'll need to create an animation curve for both going up and down slopes. This is because that's how it works in Genshin. When going up, we update the horizontal forces to make sure we don't slide in the slope. When going down, we don't really need that as there is no ramp in front of us, but it seems that they update the vertical force to be a bit lower. To know whether we are going up or down, we simply need to check the player vertical velocity. Going up means it's positive, while going down means it's negative. We'll create two methods for that, so open up the player movement state script. In the reusable methods region, head over to the isMoving method. Then create a new method by typing in protected bool isMovingUp and pass in float minimum velocity
defaulted to 0.1f as a parameter. Inside, we can simply return getPlayerVerticalVelocity .y greater than minimum velocity. That's all we need, so now duplicate this method and rename it to isMovingDown instead. Then we'll swap the greater than with lesser than and add a minus sign before the minimum velocity. This makes it so that we can pass in a positive velocity as an argument, while the method takes care of it being checked as negative, which is what should happen. When that's done, go back to the player jumping state script. In the raycast if statement, now check if isMoving up and also if isMoving down. We can now start creating and setting the animation curves for each situation. To do that, open up the player jump data script. In here, create a new field, serialized field, public animation curve, jump force modifier, on slope upwards, and give it a private set. You can give it any other name if you find something better. Then duplicate the property and swap upwards with downwards. When you are done, save everything and head back to Unity. In here, open up the second Inspector tab. In the jump data area, start by opening up the upwards force animation curve. Select the first curve preset. Then right-click on the last key, press Edit key and set its time to be 90. We'll have two different ranges. From 20 to 35, the force modifier will be 0.75, or 75% of the original jump force. From 35.1 to 75, the force modifier will be 0.5, or 50% of the original jump force. This is because the steeper the slope, the easier it is to look like we are sliding. So we need to make sure we have a lower horizontal force. Knowing that, add in 3 keys. "20" with a value of 0.75, 35.1 with a value of 0.5, and 75.1 with a value of 1. Of course, we don't want this to look like an actual curve, so select all keys and set both tensions to constant for all keys. If all has been done correctly, 20 to 35 should be at 0.75, 35.1 to 75 should be 0.5, and the rest should be 1. With that done, close the current animation curve and open up the downwards animation curve. Choose the first curve preset and change the last key time to be 90. We'll only have one range here. From 20 to 70, the force modifier will be 0.85 or 85% of the original jump force. Make sure the 70 key is actually 70.1 and set to 1, for the reason as all the other animation curves. Set both keys' tensions to be constant. We should be left with one single area from 30 to 70 set to 0.85, and the rest set to 1. That's all we need for our animation curves, so feel free to close it and head back to the player jumping state script. In our isMovingUp if statement, we'll need to apply the forces only on the horizontal axis. To do that, start by typing in float force modifier equals to jump data dot jump force modifier on slope upwards dot evaluate and pass in ground angle. Then apply the modifier by typing in jumpforce.x multiplied with force modifier and jumpforce.z multiplied with force modifier. That's all we need when moving up, so in our isMovingDown if statement we'll need to apply the forces only for the vertical axis. To do that, copy the first two lines of the isMovingUp if statement and paste them in the isMovingDown if statement. Then swap upwards with downwards and x with y. This should be all that's necessary to correctly jump on a slope, so save it all and go back to Unity. Entering play mode, we shall now be able to jump correctly in both of our ramps. We should also be jumping differently when going up or down the ramps. Do note that animations also play a part on how good this looks, so you might need to update the values once you add animations into the system. If it isn't working in your own game objects, make sure that ramp angles are within the ranges we have added, as if they aren't, they will jump normally. I think you could ramp up the 20 to 30 if you'd like, but I made it 20 so that we could test it out in our current ramp, as 20 shouldn't be steep enough to need a jump force modifier. With that done, you might have also noticed that our jump looks kinda floaty. If we take a look at Genshin, if we jump, we see that it gets to the top quite fast, not really having much of a floating feeling. And yes, I'm still talking about the jump. The reason why the jump feels floaty is because it's taking its time to get to the top, and then gravity also takes its time to create a strong enough negative velocity. The way we'll make it less floaty is by adding a small negative force while the player is going up. This makes it so that we get to the top faster, which makes it look less floaty. You could also add a small negative force when going down, which will make the player fall faster, but I'll just add one when going up. To do this, go back to the player jumping state script. In here, in our physics update method, type in if isMovingUp. If that's the case, we need to add a force to our player vertical axis. We'll do that using the acceleration force mode, as we want to slowly decelerate our player over time. Of course, we currently only have an horizontal deceleration method, so we'll need to create one for a vertical deceleration. To do that, open up the player movement state script. In the reusable methods region, go to our decelerate horizontally method and duplicate it. Then rename it to decelerate vertically. Inside, swap the getPlayer horizontal velocity with getPlayer vertical velocity instead, and rename the variable to player vertical velocity. If you want this decelerate to always go down, then make sure you swap the minus sign to be on the force instead, as otherwise a negative velocity will become positive, which means it will make the player go up. Because I named it decelerate, this is what I'll have it do. This of course means that if our player was going down, decelerating it vertically will make it fall slower and slower over time. With that done, go back to the player jumping state script, and inside of the if statement, call in decelerate vertically. Of course, we need a value for the deceleration force, so open up the player jump data script. In here, type in field, serialize field range from 0f to 10f, public float deceleration force, and give it a private set. I'll default it to 1.5f. Back into the player jumping state script, in the enter method, set the state machine .reusable data.movement deceleration force to be equal to jump data.deceleration force. And that's all we need to make it less floaty, so save it all up and go into Unity. If we enter play mode, we shall now be getting to the top a bit faster. If you wanted the player to get there faster, you will simply make the force stronger. Although if you make it too strong,
it will reduce the jump height. We are almost done with our jumping state, but there is one more situation to solve. If we take a look at Genshin, if we jump when we were sprinting, we will keep sprinting after landing. However, this only happens if we have held the sprint key long enough. If we didn't, then we'll go back to the running or walking state depending on the walk toggle value. We also do not keep sprinting with other states like gliding or hard landing or rolling. Of course, we still don't have this in our system, but we'll make it so that it only works for the jumping state. We'll be doing this by creating a reusable data property that defines whether we should keep sprinting or not. Then in our onMove method, if this property is true, we'll simply transition to the sprinting state. The property will only become true when we are sprinting and decide to jump. So, to do that, start by opening up the player state reusable data script. In here, duplicate the shouldWalk property and name it shouldSprint. When that's done, open up the player grounded state script. In the reusable methods region, go to the onMove method. In here, above everything else, type in if statemachine.reusabledata.shouldSprint. If that's the case, then we can transition to the sprinting state by typing in statemachine.changeState and pass in statemachine.sprintingstate. At the end, we return as to not call the remaining statements. When you are done doing that, open up the player sprinting state script. In the input methods region, in our onSprintStarted method, type in statemachine.reusabledata.shouldSprint equals to true. The reason why we are having this here instead of in the onJumpStarted method is because we only want to keep sprinting if the sprint key was held enough time, which we won't know if that's the case in the onJumpStarted method. You could do it in the onJumpStarted method by checking the keep sprinting variable value if you prefer it to be that way. Above, in our variables, we'll create a new variable by typing in private bool shouldResetSprintState. Then, when we enter the sprinting state, we'll set the shouldResetSprintState variable to true. When we exit the sprinting state, we'll check if shouldResetSprintState. If we should reset it, then we set our keep sprinting to false and our statemachine.reusabledata.shouldSprint to false as well. In case we shouldn't reset it, we want to keep these variables as they were, which makes it so we start sprinting once we land. Of course, we need to set this variable to false somewhere, and we'll be doing that when we jump. So in our input methods region, override the onJumpStarted method. Then, before our base method call, we type in shouldResetSprintState equals false. The reason why we are doing this before our base method call is because on the base onJumpStarted method we are transitioning to the jumping state. This means that our sprinting state exit method will be called before we set the shouldResetSprintState variable value to what we want. Now, while everything seems okay so far, let's say we enter the jumping state with the shouldSprint property set to true. Whenever we come back to a grounded state, we'll enter the sprinting state due to the onMove method. However, let's say that while in the jumping state, we were to start gliding whenever we add gliding to our system. In Genshin, this makes it so that we no longer go to the sprinting state whenever we land. But because we are not resetting it anywhere in our jumping or airborne states, right now we'll always come back to sprinting. To fix this, open up the player airborne state script. In the reusable methods region, create a new method by typing in protected virtual void reset sprint state. Inside, we'll call in statemachine.reusabledata.shouldSprint equals to false.
Then call this method in the enter method, which we need to override. I'll also add the enter method to an iteration named iStateMethods. This makes it so that every time we enter an airborne state, the showSprint property gets reset to false. Of course, we don't want that to be the case on the jumping state, so open up the player jumping state script and create an iteration named reusable methods. In here, override the reset sprint state method and leave it empty. Now every airborne state besides the jumping state will reset the showSprint property. However, we still have another problem. While we'll indeed keep sprinting after jumping and landing, this currently stays true even if we stop pressing the movement keys. In Genshin, we'll only keep sprinting if we never let go of the movement keys, or more specifically, if a movement key was pressed when we landed. If we do land with no movement key pressed, then when we move again, we'll go back to the normal running or walking states. To fix this, open up the player grounded state script. In here, override the enter method. Inside, we'll call in a new method named update showSprint state. Inside of this method, we'll check if not statemachine.reusabledata.showSprint and return if that's the case. We'll also check if statemachine.reusabledata.movementInput is different than vector2.0 and return if that's the case as well. If none of these are true, then we'll reset the showSprint property by typing in statemachine.reusabledata.showSprint equals false. This makes it so that every time we enter a grounded state, if our showSprint property is set to true and there is no movement key pressed, we set the showSprint property to false, which means we won't transition to the sprinting state. I'll also add this method to the main method's region. That's all we need to do for our jump. Of course, we can't really test this out until we add animations, but it should be working fine. Our player is now able to jump well, but if we enter play mode and fall down from one of the ramps, pressing space while in the air will make our player jump. This is because right now, when we leave the ground, our player keeps being in a grounded state. We'll solve this problem by adding a new state, falling. While I didn't intend to add falling until I introduced the gliding system, due to a few reasons I've decided to add it to the first part of the series. Because it wasn't intended to be added now, we haven't yet downloaded any falling animation. To do that, open up mixamu.com. In here, after logging in, make sure you select your game character model and then in the Animations tab, search for Falling Idle. We'll download it as is with the FBX for Unity selected and rename it to ibot@fall. In Unity, open up the Airborne Animations folder and drag the downloaded animation into this folder. Then open up the asset and select the animation clip and press Alt-D. We now have our animation clip, so feel free to remove the asset we have dragged in. Select the animation clip and check the loop time option to loop the animation. With that done, let's now take a look at how falling works. We have our ground check collider that we already use in our jumping state. This simply allows us to go back to the idling state when we touch the ground again. To do that, we use the onTriggerEnter method. In the following case, it will be quite the opposite. If, when we are in a grounded state, our trigger collider exits the ground, then we should start falling. When falling, the moment we enter in contact with the ground again, we'll go back to the idling state only until we don't have our landing states. We'll have to care about a few things regarding our falling state, but we'll understand them later whenever we finish the base of our falling. We'll start by creating the falling state script, so head over to the airborne states folder. In here, create a new C# script named player falling state. Open it up and remove the default methods. Then swap the inheritance to inherit from player airborne state instead. Generate the necessary constructor. We'll need to cache this state, so open up the player movement state machine script. Duplicate the jumping property and rename it to falling instead. Don't forget to initialize it as well. Because we need the onTriggerExit method, we'll need to add it to our states, so open up the iState script. In here, duplicate the onTriggerEnter method and rename it to be onTriggerExit instead. When that's done, open up the player movement state script. Implement the necessary interface method and place it under our onTriggerEnter method in the iState methods region. Once you are done doing that, open up the state machine script. In here, duplicate the onTriggerEnter method and rename the enters to exit. Then open up the player script. Under the monoBehavior onTriggerEnter, call in the monoBehavior onTriggerExit method. I rename the parameter to collider. Inside, call in movement_state_machine.onTriggerExit and pass in collider. We now need to check if our collider exited the ground, so go back to the player movement state script. In the onTriggerExit method, we'll start by checking if we exited the ground by typing in if statemachine.player.layerData.isGroundLayer and pass in collider.GameObject.layer. If it is a ground layer, we then call in a new method named onContactWithGroundExited, with collider as an argument. Make sure you return right after as well. I'll make this method protected virtual and add it under our onContactWithGround method in the reusable methods region. You can name it onGroundExit or something else if you'd prefer. I've just named it like this to be something close to the onContactWithGround method. We'll now transition to the falling state with this method, but we'll do it in our player grounded state, as we can only exit the ground when we are grounded, so open it up. In here, in the reusable methods region, start by overriding the onContactWithGroundExited method. Inside, call in statemachine.changeState and pass in statemachine.fallingState. We'll extract this line into its own method, to which I'll name onFall. I'll make it a protected virtual method as well. This is just because we'll need to do something with it later on. Now, while this seems fine at first glance, we are currently starting to fall the moment we leave the ground. This means that we'll fall even if we have ground underneath not too far from the player feet. We don't really want that and don't mind it being considered a grounded state in this case, as the distance is small, so it won't really look weird. The floating capsule also helps it looking better as we'll somewhat teleport down. We'll check for ground underneath using a raycast. So, start by typing in vector3 Capsule Collider Center in World Space equals to state machine dot player dot collider utility dot capsule collider data dot collider dot bounds dot center. Then we'll create our ray by typing in ray downwards ray from capsule bottom, as we'll cast a ray from the bottom of our capsule and not the center, and assign it to be equal to new ray with capsule collider center in world space and vector3.down. For us to get our capsule collider bottom, we'll get its center and then add to it half of its height. Of course, we need to somehow get it. We'll cache this half height into a property. So, go to the script where the capsule collider data property is set by control clicking it. Then control click the capsule collider data class. If you can't do this, just go to the capsule collider data script. In here, right after our local center property, type in public vector3 collider vertical extents and give it a private set. We've named it extents because the collider has a bounds.extents variable which returns half of the collider size, and because we only need half of the height. So in our update collider data method, now type in collider vertical extents equals to new vector3 and pass in 0f collider.bounds.extents.y and 0f. We are now caching this every time our capsule collider is changed through the inspector. With that done, back to our player grounded state script. In our array, we now subtract to the collider center state machine dot player dot collider utility dot capsule collider data dot collider vertical extents. We need to subtract because we want the capsule collider bottom and not the top. For our raycast, we type in if not physics.raycast, which means we found no ground. We pass in downwards ray from capsule bottom for the first parameter and out underscore for the second one. This is known as discards. The raycast method requires a raycast it here, but we won't really need it. So instead we are telling C# to use a placeholder and say there is no value for this variable, which might even make it so storage isn't allocated. We now need a distance from our bottom to the ground, so open up the player grounded data script. In here, duplicate our base speed and rename it to ground to fall ray distance. We'll also update the range to be from 0f to 5f and default it to 1. Back to our player grounded state script, we now pass in movement data .ground to fall ray distance to the raycast. For our layer mask, we pass in state machine .player .layer data .ground layer, and then query trigger interaction .ignore, as we don't want to consider ground trigger colliders. Make sure you move the onFall method call inside of the if statement. This looks like it's over, but we'll actually need to do yet another check. Let's take a look at those two red obstacles we have created. We can see that there is a small gap in between them. Now, when we exit this obstacle, we'll enter the falling state as the ground is still a bit far. The problem here is that small gap. There are a few possible outcomes from this, but the main cause is entering the falling state because our raycast saw no ground in the ray it casted, as it's a really thin ray. Problems like getting stuck in the obstacle or between the obstacles are possible because even though our capsule collider is big enough to pass this gap without falling, our raycast didn't realize that there was ground a bit further. So we started falling and got stuck instead. What we'll do to fix this is cast not only our ray but also a box. This makes it so if there is ground really close to each other, or the player is going to fall a really small distance, we'll keep being on the grounded state. The box can have any size you want, but the best will be around the same size as the Capsule Collider or a bit smaller. We'll go with the size of our Ground Check Trigger Collider for this. Of course, we don't yet have a reference to our Trigger Collider, so we'll need to create a script to hold it. So, in Unity, head over to the Player Scripts data folder. In here, create a new folder named Colliders. Inside, create a new C# script named Player Trigger Collider Data. Open it up and remove the default methods and inheritance. Make the class serializable as well. We'll create a property to hold the Ground Check Trigger Collider reference, so type in field, serialize field, public, box collider, Ground Check Collider, and give it a private set. We'll need to add this to our Capsule Collider utility script, but it currently is a reusable class, while this new class is for the player only. Because of that, we'll create another class to hold it together with the Collider utility. So, back into Unity, go to the Player Utilities folder and create a new folder named Colliders. Inside, create a new C# script named Player Capsule Collider Utility. Open it up and remove the default methods. Swap the inheritance from MonoBehavior to Capsule Collider Utility. Make the class serializable as well. Then add in a new property by typing in field, serialize field, public, player trigger collider data, trigger collider data. I'll give it a private set. When that's done, go to the player script and swap our Capsule Collider utility type with Player Capsule Collider utility instead. This basically allows us to add more things into the utility that are specific to the player, without needing to change anything anywhere. You could, and likely should, go for composition instead, which is simply adding the Capsule Collider utility as a property instead of it being inheritance. But for simplicity, I'll go with inheritance, as again, that makes it so we don't really need to change anything else. If you prefer the composition way, add it as a property and make sure you update all usages to get there correctly. With that done, save everything and go to Unity. In the Player Game object, open up the Trigger Collider data area and assign to it the Ground Check Game object. When that's done, open up the Player Grounded State script. In the same method above our if statement, we'll type in if is there ground underneath and generate the method. Inside of the if statement, we will return, as that means we shouldn't fall. I'll add this method to the main method's region. In here, we'll check for a box using the overlap box method. There are other methods to check for a box, but at least the checkbox method seems to count the transform we cast it from as well, even with a layer mask. So we'll use the overlap box instead. This method requires a center in world space from us, which is where the box will be positioned. We'll use our ground check box center for this. So start by typing in vector3 ground collider center in world space equals to state machine dot player dot collider utility dot trigger collider data dot ground check collider dot bounds dot center. Then we'll create a collider array named overlapped ground colliders and assign it to be equal to physics.overlapBox. For our center, we'll pass in ground collider center in world space. Next we have the size, but it actually requires half of it. So pass in stateMachine.playerUtility.triggerColliderData.groundCheckCollider.bounce.extends. We are repeating this quite a bit, so above our vector, create another variable of type boxCollider named groundCheckCollider and assign to it the groundCheckCollider. Then swap it with where we use our groundCheckCollider. For the third argument, we need the box rotation, so pass in groundCheckCollider.transform.rotation. For our layer mask, we want the ground layer, so type in stateMachine.player.layerData.groundLayer. Pass in queryTriggerInteraction.ignore for the last argument. Now we can return overlapped ground colliders.length greater than 0, as that means we have found ground underneath our player. That shall get our falling working whenever we exit the ground, but we still have a few things to do. The first one is to not allow hair movement while falling, which we can do by setting the speed modifier to 0. So open up the player falling state script. In here, override the enter method. Inside, type in stateMachine.reusableData.movementSpeedModifier equals to 0f. I'll add this method to an heuristic named iStateMethods. The second thing is to make sure we limit our falling velocity. This is because when falling, gravity will keep on increasing the velocity. When using ground colliders like mesh colliders or colliders that don't really have a lot of depth, because our velocity can be quite high, our collider will go through the ground at a speed that the collision won't be detected, even with our rigid body collisions set to continuous and all that. This means that we will simply keep on the falling state even though we have already hit the ground. To fix that problem, we simply limit our vertical velocity, which Genshin seems to do as well. We can do that by adding a vertical force to it in a way that it doesn't go over a certain limit. So override the physics update method and call in a new method named limit_vertical_velocity. I'll add this method to an heuristic named mainMethods. We'll need to know what's our velocity limit, which means we need a data class for falling. So, back in Unity, in the airborne data folder, create a new C# script named playerFallData. Open it up and remove the default methods and inheritance. We'll make it serializable. In here, create a new field, serialize field, field range from 1f to 15f, public float, fall speed limit, and give it a private set. I'll default it to 15f. Higher values than these might not work, so beware when setting it higher. Then open up the player airborne data script and duplicate the jump data property and swap jump with fall instead. When that's done, go back to the player falling state script. In our variables, create a new variable by typing in private player falldata. Then in the constructor, type in falldata equals to airborne data dot fall data. Then back to our limit vertical velocity method, we'll check if we have reached the speed limit by typing in if statemachine.player.reachedBody.velocity.y greater than or equals to minus fall data dot fall speed limit. If that's the case, we return. Note that our speed limit is turned to negative here, so minus 14 will be greater than minus 15. Minus 16, for example, will be an higher speed fall than minus 15, but because it's a negative number, it means that it's lower than minus 15. Otherwise, if we have passed the limit, we'll set the current y velocity to be our max fall speed. To do that, type in vector3 limited velocity equals to new vector3 0f minus fall data dot fall speed limit minus statemachine.player.reachedBody.velocity.y and 0f. We are simply getting the difference between both here. If we are falling at minus 16 and the max is minus 15, then we'll add 1 to make sure we go to minus 15. Because we only enter this statement when the player velocity is stronger than the fall speed limit, doing the subtraction this way ensures we always receive a positive value, not needing to use absolutes. We are also getting our velocity twice now, so above everything, type in vector3 player vertical velocity equals to get player vertical velocity. Then swap the velocity.y lines with player vertical velocity.y instead. With that done, we simply need to add a force, so at the bottom type in statemachine.player.reachedBody.addForce and pass in limited velocity and force mode.velocity change. We pass in velocity change as we don't want it to be over time nor to depend on the player mass. That solves one bug, so we only have two things left to do or solve. The first one is to transition from jumping to falling. This is because when we jump right now, we'll never start falling as there is nothing telling us to change states. Now we could have this happen in two possible ways. The first one is by setting an animation transition event on the frame that the jump animation gets to the top. However, while this may seem fine at first glance, there is a problem. Let's say we jump and there is an obstacle right above our player head. When we hit this obstacle, we'll start moving down due to physics. But because our jump animation still hasn't reached the top frame, we'll be falling while in the jumping state. The second way of doing it is the way we'll be fixing this problem. Simply transition to the falling state whenever our velocity becomes negative, as that means we are falling. So start by opening up the player jumping state script. In here, in the iState methods region, override the update method. Inside, we'll check if getPlayerVerticalVelocity.y greater than 0 and return if that's the case. Otherwise, we can transition to the falling state by typing in statemachine.changeState and pass in statemachine.fallingState. This is basically what is normally needed to transition from the jumping state to the falling state. But we need to keep in mind that we are using the floating capsule technique. This technique tries to keep the capsule collider afloat by adding a force to it. This is needed because the capsule collider would otherwise fall due to gravity. This means that our velocity will always become negative until the next add force method is called. Because of that, if we leave things as they are right now, it will enter the falling state right after we jump. Thankfully, it's quite simple to solve that. In our variables, create a new variable by typing in private bool can start falling. Then in our update method, we'll check if not can start falling, and is moving up. We'll also pass in 0f to the is moving up method to make sure we check for the actual moment it starts going up. If that's the case, we'll set the can starting falling to true. Then in our state change if statement, we'll add in not can start falling or. The transition will now only happen if we can start falling and the player velocity is under 0 or negative. Of course, because we are caching in our states, we need to make sure we reset this variable to false when exiting. So in our exit method, simply type in can start falling equals to false. With that, we should have our transition to the falling state working correctly. However, I had a problem when falling off ramps that we will sometimes just randomly jump. I don't really remember the cause, but I remember that to fix it, I had to reset our vertical velocity when we enter the falling state. We don't reset our horizontal velocity because we still want to keep our horizontal momentum. So open up the player falling state script. Then in our enter method, type in reset vertical velocity. Of course, we don't still have this method, so open up the player movement state script. Go to our reusable methods region to our reset velocity method. Under it, create a new method by typing in protected void reset vertical velocity. Inside, we'll make it so that our vertical velocity becomes 0. So start by typing in vector3 player horizontal velocity equals to get player horizontal velocity. Then set a state machine .player.rigidBody .velocity to be equal to player horizontal velocity. The getPlayerHorizontalVelocity method returns a vector with y value as 0, which makes it so we are resetting the vertical velocity while keeping the rest being the same. If we now go to the player falling state script, the method shall no longer be throwing an error. This should be enough, so now there is only one thing left to do, which is to override the reset sprint state method and leave it empty. I'll add this method to an region named reusable methods. This override is required because now our jumping state only happens until we are at the top, so we need to make sure we keep sprinting after we fall as well. Of course, because we can jump and go to the idling state, in certain situations where we jump to an higher leveled ground, we can keep the jumping state override as well. However, we need to remember that we can also go from a grounded state to the falling state. This means that in our sprinting state, we also need to set the should reset sprint state variable to false when we start falling, much like what we did for when we jumped. Thankfully, we have previously created a virtual method named onFall that will make it easy for us to do that. So open up the player sprinting state script. In here, in the reusable methods region, override the onFall method. Before we call the base method, we simply type in should reset sprint state equals to false. This means that if our should sprint becomes true, it will now not be reset when we fall. Note that the should sprint should only become true if the sprint key was held long enough, which is how it works in Genshin and is how it's working for us as well. That should be all that's needed for falling, so save it up and go to Unity. Entering play mode, we shall now be able to fall correctly. With our falling state done, we can now add in our last states, which are the landing states.
Originally, the light landing state was the only landing state that we would add in the first part of the series, but with the addition of the falling state, I think it's fair if we add the other two landing states as well. Of course, for the same reason as our falling state, we haven't yet downloaded the two extra landing state animations, so we'll need to do it now. Start by opening up mixamu.com. Make sure you are logged in and your character model is selected. Then in the Animations tab, search for Art Landing. Download it with the FBX for Unity option selected. I'll rename it to not contain the white space it comes with. And also search for Sprinting Forward Roll. Download it with the In Place option enabled. I'll rename it to YBot@Roll. Of course, YBot here will be your selected character model name. When that's done, in Unity, go to the Landing Grounded Animations folder. Then drag the two downloaded animations to this folder. Open both by clicking on the arrow key and control-click both animation clips. Then press Alt-D to duplicate them. Once that's done, remove the imported assets as we no longer need them. Regarding our landing states, we now know that we have three possible states. Light landing, which happens when we fall from a small height, like after jumping or when touching the ground from gliding. Hard landing, which happens when we fall from a higher height, and rolling, which also happens when we fall from a higher height, but only if we have a movement key being pressed. With that in mind, let's start by creating their scripts. To do that, go to the Player Grounded States Scripts folder. In here, create a new folder named Landing. Inside, we'll create 4 new C# scripts. Player Landing State, Player Light Landing State, Player Rolling State, and Player Hard Landing State. Start by opening up the Player Landing State script. Remove the default methods and swap the inheritance from MonoBehavior to Player Grounded State. Generate the necessary constructor. When that's done, go to all of the other landing states and remove their default methods and swap their inheritance with Player Landing State instead, generating the necessary constructor for each one of them. When that's all done, we'll cache our states, so open up the Player Movement State Machine script. In here, we'll create 3 new properties, one for each of the landing states. To do that, type in public player light landing state, I'll omit the set. Then duplicate this property twice and swap the light landing state with player rolling state and Player Hard Landing State. Don't forget to initialize them as well. When you are done, go back to the Player Landing State script.
we will transition to a landing state from an airborne state, which means we can enter the landing state with a movement key pressed. That means that if we let the key go, our onMovement cancelled method callback will be called, and will transition to the idling state. Of course, we only want to transition to the idling state at the end of their animations. So, to remove the current behavior, override the onMovement cancelled method and leave it empty. I'll also add it to an Euretia named input methods. The next thing we'll do is to update the current idling state transitions that were supposed to be to the light landing state. We only need to do it in the jumping and falling states. Thankfully, we have added that transition in our airborne state, so open it up. In here, in the onContact with ground method, swap the idling state with light landing state instead. Of course, we don't really do anything in our light landing state yet. The first thing we'll do is make sure we can't move while in this state, so open it up. In here, override the enter method. Then set the stateMachine.reusableData.movementSpeed modifier to be equal to 0f. I'll add this method to an Euretia named iStateMethods. The reason why we are not doing this in the landing state is because rolling will have an actual speed, as we'll be able to move while rolling. I'll also reset the velocity when we enter this state, as we want to make sure we stand still and don't keep any previous velocity. So, call in reset velocity. And that's all we really need regarding the light landing state logic. So all that's left to do here is to set the transitions from this state. If we take a look at our movement system states, we can transition from the light landing state to idling, all moving states, dashing, and jumping. When the light landing state reaches its last frame, it will transition to the idling state. Whenever a movement key is pressed while in the light landing state, it will transition to the respective moving state, including the sprinting state. At any given moment of the light landing state, we can dash or jump. With that in mind, let's transition to the idling state by overriding the onAnimation transition event method. Inside, type in stateMachine.changeState and pass in stateMachine.idlingState. Make sure you remove the base method call. For our moving states, we'll have to follow the update method approach, as we'll be getting here through an airborne state like jumping. So, above, override the update method. Inside, check if stateMachine.reusableData.movementInput equals to vector2.0 and return if that's the case. Otherwise, we call in onMove. For our dashing and jumping transitions, because a landing state is a grounded state, they are already set up. That's all for our light landing state, so we can now do our hard landing state. In Genshin, if we fall from a high enough height and land, if there is no movement input key being pressed, we'll enter the hard landing state. In this state, much like our light landing state, we don't nor can move while in it. Let's start by doing that by opening up the player hard landing state script. In here, override the enter method. Inside, we'll set the stateMachine.reusableData.movementSpeed modifier to be equal to 0f. We'll also call in reset velocity to reset any velocity we had before landing, making sure we don't accidentally move horizontally due to physics. I'll add this method to an Euretia named input methods. That's most of the necessary logic for our hard landing state, and the only remaining logic is regarding the transitions to other states. Because only the falling state will transition to the hard landing state, we'll do that transition after we also add the rolling state. Regarding transitions to other states, if we take a look at our movement system states, we'll be able to transition to idling, running, and dashing. Whenever the hard landing state reaches its final frame, the player will transition to the idling state. Regarding the running state, the way the hard landing state handles moving to a moving state is somewhat different. Whenever we first land, we'll actually not be able to move or press a movement input key. However, at a certain frame of its animation, we'll be able to start moving by pressing a movement input key. This simply means that we'll have to disable the input for a few frames. One thing to note as well is that we cannot transition to the walking state and only the running state. And last but not least, we can dash at any given moment of the hard landing state. Regarding jumping, we cannot jump again while we are on the hard landing state. With that in mind, we'll start with the idling state transition by overriding the onAnimation transition event method. Inside, we'll remove the base method call and type in stateMachine.changeState and pass in stateMachine.idlingState. For our moving states transition, we'll start by overriding the onMove method. I'll add this method to an iteration named reusable methods. Then we'll remove the base method call and then check if stateMachine.reusabledata.showedWalk, and if that's the case, we return. Otherwise, we'll call in stateMachine.changeState and pass in stateMachine.runningState. To call the onMove method, we'll use the movement_started callback. Now, we can do this here even though we can come from the following state, because we'll be disabling and enabling the movement input, which means the started action will be called when enabling again if a key is being pressed. So, above our onMove method, override the add and remove input actions callbacks methods. Then add a new callback by typing in statemachine.player.input.playerActions.movement.started plus equals onMovementStarted. Don't forget to remove it as well. I'll add this method to an iteration named inputMethods. I'll also rename the parameter to context. Inside, we simply type in onMove. Regarding our dashing state transition, it's already coded in the grounded state. Right now we are able to jump because of our onJumpStarted method in the grounded state. So, in our input methods region, override the onJumpStarted method. Then, simply leave it empty, meaning we won't transition to the jumping state. Regarding our movement input, we'll disable it when we enter this state, and then enable it both when exiting the state and at a certain frame of its animation. We need to make sure we also enable it when exiting, because it's possible that we never reach the defined animation frame, in case we decide to do something like dash, which we can at any given frame. So, to do that, in the enter method, type in statemachine.player.input.playerActions.movement.disable. Then override the exit method and type in statemachine.player.input.playerActions.movement.enable. Copy this line and now override the onAnimation exit event method. We'll use this one to enable the input at a certain frame of the animation. So remove the base method call and paste the line we have copied inside. And that's all that's needed for our hard landing state. So next, we'll do our rolling state. Of course, let's first understand what this rolling state is. In Genshin, if we fall from a high enough height and land, if there is any movement input key being pressed, we'll roll instead of hard landing. In this rolling state, we can also move around while rolling. With that in mind, we know we'll need two things: a movement speed and a rotation data. Thankfully, it uses the same rotation as our normal movement, so we don't really need to do anything extra regarding it. We will, however, still need our movement speed modifier, so we'll need to create its data class. To do that, go back into Unity. In here, in the player grounded data folder, create yet another folder named landing. Inside, we'll create a new C# script to which I'll name player roll data. Open it up and remove the default methods and inheritance. We'll make the class serializable as well. Then type in field serialize field range from 0f to 3f public float speed modifier with a private set. I'll default it to 1f. We'll then open up the player grounded data script. Duplicate the stop property and swap stop with roll instead. With that done, we can now open up the player rolling state script. In here, create a new variable by typing in private player roll data. Then in the constructor, type in roll data equals to movement data dot roll data. We can now set our speed modifier, so start by overriding the enter method. Inside, type in state machine dot reusable data dot movement speed modifier equals to roll data dot speed modifier. I'll add this method to an heuristic named iStateMethods. Now our rolling state will keep rolling until its last frame, even if we stop pressing any movement key. This of course means that if we fast press a key, our player will stop rotating, as the move method isn't being called anymore. Because of that, we'll need to add an automatic rotation to it. Thankfully, that's quite simple to do here, so start by overriding the physics update method. Inside, we simply call in rotate towards target rotation. That should take care of it, but let's also add an if statemachine.reusabledata.movementInput different than vector2.0 and return inside. This ensures we only rotate when we are not calling the move method, as our previous implementation will call the rotate towards target rotation method twice while moving. Right now, because we are able to move in the rolling state, and also because we can only enter here if we were pressing a movement input key, our grounded state shows printf statement will never enter due to its condition. However, in Genshin, we do not keep sprinting after rolling. To fix this, we'll just go to our enter method and type in statemachine.reusabledata.showSprint equals to false. This should take care of the problem and we shall no longer keep sprinting once we enter the rolling state. We'll now take a look at the transitions from the rolling state. Regarding transitions to the rolling state, much like the hard landing state, we can only come here from the falling state. So we'll add that transition when we are finished doing the rolling state. Regarding transitions from this state, if we take a look at our movement system states, we can transition to walking, running, dashing, and medium stopping. Whenever the rolling state reaches its last frame, if there is no movement input key being pressed, it will transition to the medium stopping state. If it reached its last frame but we had a movement input key being pressed, then we will transition either to the walking or the running state, depending on the walk toggle value. In Genshin, it seems that you transition to the walking state a bit earlier, but I didn't like the way it looks, so I decided to transition at the last frame. If you do want to completely replicate it, then you could override another animation event like the enter or exit method and do that transition there. I say enter or exit because we'll already be using the transition event to transition at the last frame. So unless you kept a variable that will check if we reach the last frame already, it will possibly transition to the other states earlier as well. Feel free to do it as you prefer. We can also dash at any given moment of the rolling animation. Much like our R landing state, we cannot jump in the rolling state. With that in mind, let's start by setting our animation transition event by overriding the onAnimation transition event method. Inside, remove the base method call and start by checking if statemachine.reusabledata.movementInput equals to vector2.0. If that's true, we can then transition to the medium stopping state by typing in statemachine.changeState and pass in statemachine.mediumStoppingState. Of course, return right after to not call the rest of the code. Otherwise, if we are moving, then we'll just call in on move. Because we are setting the showSprint property to false above, the onMove here will never transition to the sprinting state, so we don't need to override it. Because we are only adding this transition at the last frame, you could also very likely simply transition to the medium stopping state and let it take care of the transitions to the moving states. However, I'll leave them here as they are right now. The dashing state is of course already done in our grounded state. For our jump, let's override the onJumpStarted method and then leave it empty, as we don't want to be able to jump. I'll also add this method to a new region named inputMethods. With that done, all that's left is to add a transition from the falling state to the landing states. To do that, open up the player falling state script. The way the transitions from the falling state to the landing states work is as follows. If we fall from a small height, we'll transition to the light landing state. If we fall from a bigger height, we'll transition to the hard landing state or the rolling state depending on whether we are pressing a movement input key or not. This means that we need to do two things. Get the distance that the player fell and override the onContactWithGround method, as right now it's only transitioning to the light landing state. Knowing that, in reusable methods region, start by overriding the onContactWithGround method and remove the base method call. We now need to know our distance. The way we'll be knowing it is by saving the position of the player when it entered the falling state and then the position of the player when it collided with the ground. Knowing both, we can then subtract the y value of one with the y value of the other, which guesses the vertical distance between both positions. Of course, we should also always make this value positive. This is because the jumping state transitions to the falling state when it reaches its stop point, which means we can fall into a ground that was above our previous ground, which gets us a negative distance. So, knowing that, in our variables area, create a new variable by typing in private vector3 player position on enter. Then in our enter method, we type in player position on enter equals to statemachine.player.transform.position. When that's done, go back to our onContactWithGround method. In here, we'll get the distance by typing in float fall distance equals to matf.abs for absolute, which makes it become positive when the subtraction returns negative, and pass in player position on enter.y minus statemachine.player.transform _position.y. This gets us the difference between the player position on enter and its current position. When that's done, we now need to know what's the distance to be considered a small or big fall. So, to know that, open up the player fall data script. In here, duplicate the existing property and name it minimum distance to be considered hard fall. I'll also make the range be from 0f to 100f and then default its value to 3f. When that's done, go back to the player falling state script. In our onContact with ground method, now check if fall distance is lesser than fall data dot minimum distance to be considered hard fall. If that's the case, we'll call in stateMachine.changeState and pass in stateMachine.lightLandingState. We could instead call the base method here as it is the same as its transition line. But we won't because the base method can be changed at any moment to contain something else. We of course need to return right after to not call the remaining code. Under this, if we hit the minimum distance, we'll either transition to the hard landing state or the rolling state. We'll start with the hard landing state by typing in if stateMachine.reusableData.movementInput equals to vector2.0. Inside, we call in stateMachine.changeState and pass in stateMachine.hardLandingState. We return right after as well. Otherwise, if we have movement, we'll transition to the rolling state by typing in stateMachine.changeState and pass in stateMachine.rollingState. And that's all we need for our transitions. With this, our landing states should now be working. As a tip, if you wanted to add fall damage to your player, this will likely be the place for you to do it. Now, regarding our transition to the landing states, in Genshin if we have the walk toggle on, we'll not be able to transition to the rolling state. However, that's only true if we are not sprinting. If we are, then we'll be able to transition to the rolling state. So, in our landing state transition if statement, add in stateMachine.reusableData.showWalk and not stateMachine.reusableData.showSprint order. This makes it so that if we have the walk toggle on and are not sprinting, we'll transition to the hard landing state. One last thing to do is to set the jump force to the stationary force when we light land, so open up the player light landing state script. In here, in the enter method, we type in stateMachine.reusableData.currentJumpForce equals to airborne_data.jumpData.stationaryForce. Saving and going back to Unity, entering play mode should allow us to fall and land well. Of course, until we add animations, we won't be able to fully test our landing system. There's now one last feature we need to take care of, which we have left to do later when we added our player camera. If you don't remember it by now, I've previously said that we will be enabling the virtual camera horizontal recentering option, which was the option that the FreeLook camera didn't offer us. Now, what exactly is this horizontal recentering option and why do we really need it? Let's take a look at Genshin Impact. Currently, we are facing forwards while in the idling state. Let's say that we start moving to one of the sides, right or left. The moment we do so, we can notice that our player slowly rotates and moves in a circular motion. We can further notice this if we look down on the player at around a 90 degrees angle and start moving. What happens is that our player will rotate extremely fast. This happens even if we move backwards while we are looking down. This is achievable through the horizontal recentering option. Simply put, it automatically recenters our camera at a certain speed, also allowing us to set a time it should wait before it starts recentering. The speed of the recenter is called recentering time, which is how long it takes to recenter the camera. The time it should wait before it starts recentering our camera is called wait time. Of course, our player only rotates and moves in a circular motion because its movement is dependent on the camera horizontal axis. So by recentering the camera horizontally or in the horizontal axis, our player will start rotating itself and move with that rotation in mind. The higher the recentering time, the longer it takes to recenter the camera, which means the slower the player rotates. Of course, as we have seen before, different angles can have different settings or even enable or disable the recentering option. For example, moving backwards while looking forwards disables the option, while moving backwards while looking up or down enables it. To do this, we'll need to know the direction we are moving, which we can know through the movement input variable, and also the settings we want for each angle in each direction. To know those settings, we'll actually not use animation curves and use our own class this time, in which we can simply have a list of angle ranges and their recentering values. This is because I haven't found a way to have two different values in one animation curve, which will require us to have two animation curves, one for each value, which I found somewhat unnecessary as values are updated for the same ranges. You are free to do it using two animation curves if you prefer to. With that in mind, we'll start by creating the class that will hold this data. To do that, go to the player data folder. In here, create a new folder named cameras. Inside, create a new C# script to which I'll name player camera recentering data. When that's done, open it up. Remove the default methods and the monobehavior inheritance and make this class serializable. We'll create the angle ranges by typing in field, serialize field, field, range from 0f to 360f, public, float, minimum angle. I'll give it a private set. Then duplicate this property and name it maximum angle instead. Next we'll need one property for each of our recentering values, so duplicate the last property. I'll make the range be from -1 to 20f and rename it to wait time. Then duplicate this new property and rename it to recentering time instead. We made the minimum range value -1 as a way to specify that we want to use the default setting value, which we'll define later. Next, we need to create a method that tells us if we are within the angle range. So type in public bool is within range and pass in float angle. Inside, we simply return angle greater than or equals than minimum angle and angle lesser than or equals than maximum angle. When that's done, open up the player grounded data script. We'll be creating two lists of our class, one for recentering settings when moving sideways, and another one for settings when moving backwards or downwards. So, to do that, type in field, serialize field, public list of player camera recentering data named sideways camera recentering data. I'll give it a private set. Make sure you import the necessary namespace. Then duplicate the property and swap sideways with backwards, or downwards if you prefer. When that's done, save everything and go back to Unity.
open up the second Inspector tab. In our sideways recentering data, we need 2 ranges, so add 2 elements to the list. The first one will be from 0 to 80, to which we'll pass in -1 for both settings. This of course means they'll use the default values we'll define later. The second one will be from 80 to 90, to which we'll pass in 0 for the wait time and 0.3 for the recentering time. That's it for our sideways data, so for our backwards data we'll be having one range, so add in one element to the list. The range will be from 80 to 90 degrees, to which we'll pass in 0 for the wait time and 0.5 for the recentering time. The horizontal recentering is disabled for any other angle range when moving backwards. Also note that while we are setting the horizontal recentering, these angle ranges are for the camera vertical angles. With that done, we'll set the player camera settings to their default values. So select the player camera game object in the hierarchy and open up the aim area. Don't forget to go to the first Inspector tab. In here, set the default horizontal recentering settings to 0 and 4. These are not really necessary as we'll be overriding them later, but it's always nice to have them set to the default values right away. We'll be defining these default values somewhere else as well, which will be in an utility script we'll be creating. This utility script will allow us to enable or disable our horizontal recentering option whenever we want to. To do that, open up the Player Utilities Scripts folder. In here, create a new folder named Cameras. Inside, we'll create a new C# script which I'll name Player Camera Utility. Open it up when you are done. Remove the default methods and inheritance and make it serializable. To get a reference to our horizontal recenter option, we'll need a reference to our camera POV aim. To get that, type in private SceneMachine POV, SceneMachine POV. Make sure you import the SceneMachine namespace. Above, we'll get a reference to our camera by typing in field, serialize field, public, SceneMachine virtual camera, virtual camera. I'll give it a private set. We'll also have a property for our default values, so type in field, serialize field, public float, default horizontal wait time, with a private set and a default value of 0f. Then duplicate this property and swap wait with recentering instead, and default it to 4f. To get our POV reference, we'll create an initialization method, so type in public void initialize. Inside, type in SceneMachine POV equals to virtual camera.getSceneMachine component of type SceneMachine POV. All that's left now is to create a method for enabling and disabling our recentering option. So start by typing in public void enable recentering. Pass in float wait time defaulted to -1f as the first parameter, and float recentering time defaulted to -1f as the second parameter. Then, under the enable method, create another one by typing in public void disable recentering. To enable our option, we'll type in SceneMachine POV .m underscore horizontal recentering .m underscore enabled equals to true. We'll then copy this line and paste it in the disable method, swapping true with false instead. That enables and disables our option, but when enabling it, we also need to set our setting values, as we'll need them if that's the case. The first thing we'll do is actually cancel any existing recentering that the camera is doing by typing in SceneMachine POV.m horizontal recentering.cancel recentering. I'm not entirely sure if Genshin does this or not, but I'll leave it as I think it fixed some weird recentering that happened without this. For our values, we'll first need to check if they are -1f, and if they are, we'll set them to their default values. To do that, start by checking if wait time equals to -1f, and if that's the case, we type in wait time equals to default horizontal wait time. When that's done, duplicate this whole if statement and swap the wait parts with recentering instead. To set our horizontal recentering option values, we now type in SceneMachine POV.m horizontal recentering.m wait time equals to wait time. Then duplicate this line and swap wait with recentering instead. And that's all we need to enable or disable our horizontal recentering option. We'll now add this utility as a property of the player script, so open it up. In here, create a new property by typing in field, serialize field, public, player camera utility, and give it a private set. I'll also add in a field header with the text of camera. Then, in the awake method, we need to initialize it by typing in camera utility.initialize. This simply sets our SceneMachine POV component. When that's done, save it all up and go to Unity. In here, select the player game object and select or drag the player camera to the virtual camera field. That's our camera utility done, so we can now start thinking on actually recentering our camera. To do that, open up the player movement state script. We'll create two methods here that will call our enable and disable recentering methods, just so that we do not call in a big line every time, and also because we'll need to do something else later on when enabling it. To do that, go to our reusable methods region and type in protected void enable camera recentering and pass in float wait time defaulted to -1f and float recentering time defaulted to -1f. Inside, call in statemachine.player.cameraUtility.enable recentering and pass in wait time and recentering time. Then under this method, we'll create the disable method by typing in protected void disable camera recentering. Inside, we call in statemachine.player.cameraUtility.disable recentering. That's all that's needed for these two for now, so let's now create a method to update our recentering values. Above, type in protected void update camera recentering state and accept a vector2 named movement input. We'll understand in a bit why we'll be passing in a variable instead of using the movement input property right away. We'll have to disable or enable our horizontal recentering option depending on both the camera angle and our movement input. There is a situation that disabled our recentering option, which is when we stop moving. Instead of doing this here, we'll actually do that in the onMovement cancelled option. However, we only have one in our grounded state and none in our movement state, so we'll have to create another. To do that, head over to the Add Input Actions Callbacks method. Inside, add in a new callback by typing in statemachine.player.input.playerActions.movement.cancelled + movement cancelled. Don't forget to remove it as well. I'll rename the parameter to context and then add this method to the input method's region. Because we leave it as private, it won't conflict with the grounded state method. Inside, call in disable camera recentering. Back into our update camera recentering state method, we'll still return if there is no movement input, so type in if movement input equals to vector2.0 and return if that's the case. Next, we'll need to disable it when moving forwards, as it sometimes seemed to give us a weird recentering even though it's supposed not to recenter in this situation. So type in if movement input equals to vector2.hub and call in disable camera recentering, returning right after as well. Then we'll do it for when moving backwards, so type in if movement input equals to vector2.down. In this case, we'll need to iterate through our backwards list and see if it is within the ranges, disabling in case it isn't. Of course, to do that we need our camera angle, so above, outside of the if statement, type in float camera vertical angle equals to statemachine.player.mainCameraTransform.EulerAngles.x. Note that x is the camera vertical angle. Now we'll need to know if the range is between -90 and 90, as looking up has the same effect as looking down. However, we are only checking for positive angles in our lists, so we'll have to convert the negative values to positive using absolutes. To do that, type in camera vertical angle equals to matf.avs and pass in camera vertical angle. The reason why we are doing this here instead of above is because we'll need to add something else before we do this. Our Euler angles only return positive values. That means that -90 will be returned as 270 and so on. However, we want to make it 90 instead of 270 when making them positive. So we'll simply make it negative again by typing in above our second assignment if camera vertical angle greater than or equals than 270. If that's the case, we subtract 360 degrees to the angle by typing in camera vertical angle minus equals 360f. This shall now get us an angle between -90 and 90 and then make it positive so that we can compare it with our list angle ranges. We can now iterate through our settings list, so inside of the if statement, type in for each player camera recentering data in movement data dot backwards camera recentering data. Inside we'll check if not recentering data dot is within range and pass in camera vertical angle. And continue to the next one if that's the case. Otherwise, we call in enable camera recentering and pass in recentering data dot wait time and recentering data dot recentering time. At the end, we return to exit the loop and method, as we have found the desired angle range already. If we did end up outside of the loop, then it means that we didn't find any setting with this angle, so we call in disable camera recentering and return right after. That's all there is for setting our values. We'll need to do this exact thing with our sideways list. so select the code we have just added except the last return statement and extract it to a new method. If you can't extract it, remove the return of the for each loop for a bit while you extract it. I'll name it setCamera Recentering State. I'll also pass in the list of the backwards recentering data and add it as a parameter. Then I'll rename the parameter to camera recentering data and import the list namespace. When that's done, swap the backwards list usage with the camera recentering data parameter. Don't forget to add the return statement back in our for each loop as well. I'll make this method protected just in case we ever need to reuse it somewhere. All that's left to do now is to add a setting for when we are moving sideways. Because we have tested all other directions, and also because diagonal directions seem to use the same settings as the sideways directions, we can just copy the method call we did for our backwards direction and paste it in right after the if statement without checking for anything. We'll then simply swap backwards with sideways to use our sideways data instead. And that's really all we need to do for our update camera recentering state method. Of course, we still need to call this method somewhere. We'll call it both when our movement input has changed and whenever our mouse has moved, as both of these mean that either our camera angle or our player direction have changed. So in our addInputActions callbacks method, in the reusable methods region, we'll add two new callbacks. StateMachine.player.input.playerActions.look.started plus equals on mouse movement started. And then StateMachine.player.input.playerActions.movement.performed plus equals on movement performed. Make sure you remove both callbacks. I'll rename both parameters to context and then add both methods to the input methods region. Again, the difference between started and performed in our movement is that started will only be called on the first key press, while performed means it will call on every key press, like going from W to WD. Our mouse started will be called quite a few times though, likely because of the way delta or the mouse works. In the onMouseMovementStarted method, we'll call in update camera recentering state and pass in statemachine.reusabledata.movementInput. In our onMovementPerformed method, we'll call in update camera recentering state. This callback here is the reason why we need to add the movement input as a parameter instead of using it right away. We are currently on the callback of the movement action. This means that the movement input we are reading in the update method isn't yet updated to the value that we have in this callback, as this callback is called before setting the value. This of course means that using the movement input property in our recentering methods will update the recentering state using the old movement input value. Thankfully, we can easily get the updated value here from the context variable. To do that, pass in context.readValue of type vector2. With that done, our camera recentering shall now be working. So save it all up, go back to Unity and enter play mode. Moving the camera around in the vertical axis or changing movement directions shall now move and rotate the player according to the settings list.
However, we currently have a few problems in our implementation. The first problem you might have noticed is that our camera recentering rotation speed seems to depend in our current player speed. If we change between walking, running and sprinting, we change how fast our player or camera rotates. We'll fix this by making our recentering time be dependent in our player speed. The way we'll do that is quite simple. Let's say that for the speed of 5, which is our current base speed, we have a recentering time of 4. This means that for the speed of 10, we have x. This is, of course, a simple rule of 3. To get the x, which in this case is pretty easy for us as it should be 8, we multiply 10 with 4 and then divide it all by 5. This gets us exactly what we need, which is 8. However, it seems that we actually want the opposite. The higher our speed, the lower our recentering time should be. In this case, we want the result to be 2. To do that, we simply use the inverse rule of 3. The way we do that is by multiplying 5 by 4 and then divide it all by 10. This gets us the result we want, which is 2. We'll be adding this formula to our camera utility enable recentering method, so open up the player camera utility script. In here, in the enable recentering method, we'll be adding 2 new parameters at the end. Float base movement speed, defaulted to 1f, and float movement speed, defaulted to 1f. Then, before we assign our values to the horizontal recentering fields, we apply the inverse rule of 3 by typing in recentering time equals to recentering time multiplied by base movement speed divided by movement speed. Note that we do not use the multiply equals operator, as that will multiply the recentering time with the division of base movement speed by movement speed, which is not what we want. When that's done, go to where we use our enable recentering method, which shall be in our player movement state script. In here, we'll create a new variable by typing in float movement speed and assign it to be equal to get movement speed. Then we check if movement speed equals to 0f, and if that's the case, we set the movement speed to be equal to movement data dot base speed. This will make it so that we don't divide by 0, which shouldn't be possible, and instead divide by the base speed, which will make it so it returns the normal recentering time, as we are multiplying by base speed and then dividing by base speed again. When that's done, pass into the method call movementData.baseSpeed and movement speed. This shall take care of setting the correct values for different speeds, so save it all up and go back to Unity. Entering play mode, our speed shall no longer make our camera rotation faster, although it might not be a completely perfect solution. This, however, brings us to our second problem. Changing states, like going from running to walking, does not update the recentering values until we change to a new movement input key. So moving to one side and pressing the Alt toggle keeps the recentering time the exact same, which means we still have our problem. The way we'll be fixing this is quite simple. Every time we enter a grounded state, we'll update our camera recentering state. To do that, open up the player grounded state script. In here, in our enter method, at the bottom, call in update camera recentering state and pass in statemachine.reusabledata.movementInput. This seems like it will be enough, but we need to remember that this uses our speed modifier now. The problem with that is that we are currently only setting our speed modifiers after we call the base method, which means we won't have them updated by the time we call in the update camera recentering state method. To fix this, we'll go to every grounded state, starting with the idling state, and in the enter method, we'll place a speed modifier line to be above our base method call. Repeat this process for every grounded state that sets a speed modifier. With this done, we shall no longer have the problem we had. However, we also need to remember something else. We can enter and exit slopes, which update our speed modifier. This simply means that the moment the ground angle changes, we shall make sure we update recentering values to our new player speed. To do that is quite simple, as we have a method that returns us the new slope speed modifier. So, start by opening up the player grounded state script. In here, go to the set slope speed modifier on angle method in the main method's region. Inside, add in a new if statement by typing in if statemachine.reusabledata.movement on slope speed modifier is different than slope speed modifier. Make sure you place our current assignment in here. Then we'll also call in update camera recentering state and pass in statemachine.reusabledata.movement input. This makes sure our values are updated if our slope speed modifier is changed. If we save and go back to Unity, entering play mode shall now update the recentering values correctly. We do have two other problems to solve though. The first one is that our rotation stops when we cancel input, even if we currently are in the jumping state. So moving, jumping, and then unpressing the movement key will disable our camera recentering. In Genshin, this is not what happens when we are in the middle of the jump and should instead keep it enabled and rotating. To fix this problem, we'll simply need to override our onMovementCancel method and leave it empty. Of course, we currently have a private method in our movement state and a protected method in our grounded state, which means that we can't currently override it in our jump state. Thankfully, in the grounded state 1, we no longer need to change to the idling state, as no state does that when cancelling input anymore. So we'll simply remove it and make our movement state method protected virtual instead. To do that, open up the player grounded state script. In here, in the input methods region, remove the onMovementCancelled method. Make sure you also remove it from the add and remove input actions callbacks methods as well. When that's done, open up the player movement state script. In the input methods region, make our onMovementCancel method a protected virtual method. We now need to make sure that our currently overridden methods need to call the base method, or be removed if they were left empty to not transition to the idling state. So open up every grounded state script and do that. for the states that transition to other states in this method, we need to make sure we call the base method after we change states. This is because when changing states, we now call in the update camera recentering state method in the enter method, so it will enable it back after disabling it. When the grounded states are all updated, open up the player jumping state script. In here, add in a new region at the bottom named input methods. Inside, we'll override the onMovement cancel method and leave it empty. This should be enough, so save and go back to Unity. Enter in play mode. Moving, jumping, and releasing the movement key shall no longer disable our horizontal recentering. There's now only one problem left, which is that in Genshin, the walking state seems to have the default recentering time when we are looking down and move backwards. The idling state seems to also have a wait time when we are looking down and move backwards. For the sideways cases, both seem to still rotate fast and without waiting before recentering. The way we'll be doing this is quite simple. We'll simply create a reusable property that allows us to set the current backwards and sideways lists. To do that, open up the player grounded data script. In here, copy the backwards list property. Then open up the player walk data script. In here, paste the copied property under our base speed property and import the necessary namespace. We only need to override our backwards data, so we don't need to create a property for the sideways data. For our idling case, we'll need a new data class, so go back to Unity. In here, open up the player grounded data folder and create a new C# script which I'll name player idle data. Open it up and remove the default methods and inheritance. We'll make the class serializable as well. Then paste the copied property here. When that's done, go back to the player grounded data folder and duplicate the walk property. Swap the walk parts with idle instead. When that's done, open up the player state reusable data script. We'll be creating a property to all these rotation values, so under our speeds and forces properties, paste the backwards property we have copied before twice. Then swap the second one to be sideways instead of backwards. This is just in case we ever need to override the sideways data as well. Remove the serialized field attribute and give them a public set. When that's done, go to the player movement state script. In the constructor, after setting our other variables, we'll type in statemachine.reusabledata.backwards camera recentering data equals to movement data.backwards camera recentering data. Then duplicate this line and swap backwards with sideways. I'll extract both lines to a new method which I'll name setBase camera recentering data. I'll make this method protected and add it to the reusable methods region. When that's done, open up the player idling state script. In here, we'll create a new variable by typing in private player idle data. In the constructor, we then set the idle data to be equal to movementData.idleData. Then in the enter method, before we call the base method, we type in stateMachine.reusableData.backwards camera recentering data equals to idle data.backwards camera recentering data. Note that we need to make sure we set this before we call the base method, as otherwise our enter method update camera recentering state call will update with our old data list. We now need to reset this data whenever we leave the idling state by using our setBaseRotationData method. However, we can't really do that when we exit the idling state. This is because if we do that, then the moment we move, we'll set the values back to normal, meaning that our wait time will be set to 0 again, so we'll start rotating fast instantaneously. If we take a look at Genshin, if we wait until we are idle and start moving backwards while looking down, then we'll wait for a while before our recentering happens. However, if we start moving backwards while we are on a stopping state, it will be instantaneous and we won't wait for the recentering to start happening. This means that we can simply reset the values when we enter our stopping states. To do that, open up the player stopping state script. In the enter method, before we call in the base method, call in setBaseCameraRecenteringData. All that's left is our walking state, so start by copying the line in our enter method and then open up the player walking state script. In here, in the enter method, paste the line we have just copied before the base method call. Then swap the idle data with walk data instead. Make sure you create the walk data variable and set it in the constructor. When that's done, override the exit method. We'll need to reset the data back to its default values, which we can do by calling in setBaseCameraRecenteringData. That should set all the data lists correctly, but we of course can't forget to actually use the reusable properties in our methods. To do that, add back to the player movement state script. In our update camera recentering state method, in the reusable methods region, swap our movement data usages with stateMachine.reusableData instead. This should be enough to get it working, so save it all up and go back to Unity. In our second inspector tab, for our idle data, we'll only have one range, which will be from 80 to 90. For the wait time, set it to 0.25 and for the recentering time, set it to 0.5. For our walk data, we'll also only have one range, which will be from 80 to 90 with a wait time and recentering time of -1. If we now enter play mode, we should finally have our recentering working fine. We are now almost ready to start adding animations, but before we go ahead and do that, we'll first fix a few existing bugs. The first bug we have is due to gravity. This bug happens when we are near an edge and our capsule collider starts falling due to its spherical bottom. This basically makes our player fall and also adds a bit of velocity due to physics. This is a problem because this can happen in the states where we are standing still, like the idling state or the landing states, as it makes our player slide while we were supposed to not be moving, due to the velocity it added when falling off the edge. The fix for this bug is quite simple. If the player is moving in one of these states, we reset its velocity. Thankfully for us, we already have two methods that allow us to do just that. We only need to fix this problem in three states, which are the idling state and the light and hard landing states. Knowing that, start by opening up the player idling state script. In here, override the physics update method. Then type in if not is moving horizontally, and if that's the case, we return. In the case that it is moving though, we simply call in reset velocity. And that's all we need to do. So now copy this whole physics update method and go over to the player light landing state script. In here, paste the physics update we have just copied into the iState method's region. Then do the same for our player hard landing state. We won't be doing this in our player landing state because our rolling state doesn't need it. That solves one bug, but we still have a few more to fix. The next one is regarding our dashing state. I thought I had fixed it, but turns out that there's still one bug, which happens when we move, dash and then unpress the movement key. It doesn't always happen, but when it does, we simply dash at a low speed. I'm not entirely sure why, but it's likely because we are using the movement speed in this dash, and we just changed to a low speed modifier state. I've changed the code a bit, and hopefully it is enough to fix it. But in short, we'll simply always add an initial force when dashing. To do that, open up the player dashing state script. In here, rename our add force method to dash instead. Because we'll be adding a force in case we have a movement input as well, place the current code that guesses the direction above our if statement and remove the return statement. Inside of our if statement, we'll now call in update target rotation and pass in get movement input direction. This will simply update our target rotation to be relative to our movement input and camera, which will allow us to add a force towards that direction. Then we'll set the character rotation direction to be equal to get target rotation direction and pass in state machine .reusabledata.current target rotation.y, which will get us the direction of our input relative to the camera, as we have just updated it. Of course, our character rotation direction variable name no longer makes sense, so I'll rename it to dash direction instead. From what I've tried, it seemed to work without this whole if statement, but I'll leave it as is, as it makes more sense and to make sure it doesn't cause any rotation bug. With this, we are now always adding a force to our dash towards a certain direction, which depends on whether our movement input is being pressed or not. This should be enough to fix it. However, we also need to take into account the movement speed on slopes, as right now we'll be dashing slower when we are on a slope. So, go to the get movement speed method in the player movement state script. In here, add a new parameter by typing in bool should consider slopes defaulted to true. Then create a new variable by typing in float movement speed and assign to it the first multiplication. Then we'll check if should consider slopes, and if that's true, we type in movement speed multiplied by state machine .reusabledata.movement on slopes speed modifier. At the end, we update the whole return statement to return this movement speed variable instead. When that's done, go back to the player dashing state script and pass in false to the get movement speed method. And that's another bug fixed, so for the next one, I've previously added a matf.abs when falling in case we fell into a ground that was above our current ground. However, that's of course not valid, as if we ever fall in such a situation, we don't want the player to go to the hard landing state or the rolling state, but only to the light landing state as the ground is above the player. To fix that, open up the player falling state script. In here, in our onContact with ground method, where we transition to the landing states, remove the matf.abs from the fall distance variable. We'll now always transition to the light landing state in the cases we have just mentioned. That's all we need for this one. So for the next one, I've also previously said that we didn't need to update the target rotation when we jumped and add input. But with the addition of our landing states into our system, that's no longer the case. This is because our light landing state does not allow movement, which means that our target rotation will never be updated. This makes it so that if we start jumping to one side and we press the opposite side key in the middle of the jump, and then jump while in the light landing state, we will keep jumping towards the old direction. To fix that, open up the player jumping state script. In the jump method, inside of the first if statement, before assigning our jump direction a new value, type in update target rotation and pass in get movement input direction. This updates our target rotation to be relative to our input and the camera, so replicating the situation we have mentioned before should now work correctly. That should be enough, but we now have one final bug to fix. This bug has to do with our falling state. You might have noticed sometimes that when we fall from a ramp, we don't enter the falling state. The problem lies in that we are using the bounce.accents variable to set the size of our overlap box. Apparently, Unity changes this variable, which means its values can become something we don't want. I'm not entirely sure why, but according to this post, it's because the bounds are cubes in Unity, and therefore when we rotate, it will change the extents. Our Capsule Collider vertical extents property is fine, because we are using a cached extents. So even if it changes at runtime, we are not getting that one but the initial extents. For our overlap box bounce.extents though, we'll have to cache it. Thankfully, we already have a reference to our box collider, so we can easily do that. To do it, open up the player trigger collider data script. In here, add in a new property by typing in public vector3 ground check collider extents and give it a private set. Then create an initialization method by typing in public void initialize. And inside type in ground check collider extents equals to ground check collider .bounce.extents. Of course, we need a way to call this method, so open up the Capsule Collider utility script. We could override the initialize method, but we return here if the collider is already initialized, so we'll create another method instead, which we'll call here. So, under our initialize method, create a new method by typing in protected virtual void onInitialize and leave it empty. Then call it at the end of our initialize method. Back to our player Capsule Collider utility script. Now override the onInitialize method and call in trigger collider data.initialize. If you use composition, then you will simply create an initialize method here and call both properties initialize methods inside. We now need to use this new extents property, so open up the player grounded state script. In here, go to the main methods region to our isThereGroundUnderneath method. Inside, swap our ground check collider.bounce.extends with statemachine.player.collider.utility.trigger_collider.data.ground_check_collider_extends. Our bounce.center is alright because we want the center at the time we check for the ground. This should be enough to fix our bugs, so saving it all up and going back to Unity, all of our bugs should be solved. Of course, some of them were only visible with animations due to the animation transition events. Talking about animations, it's finally time for us to add them into our system. Not only will they make our system look better, they will also make it possible for us to transition to the states that required animation events. We have already downloaded our animations before, so we are basically ready to use them. In case you haven't, make sure you do it first. In Unity, to control our animations, we need to create an animator controller and also add an animator component to an object. The animator controller allows us to add transitions between multiple animations as well as set the conditions for those transitions. The animator component allows us to set the necessary data for those conditions through code, or even play or stop a specific animation. In other words, it allows us to control the animator controller through code, among other things. It's also the component that allows us to specify what's the animator controller of a specific game object. We'll be adding our animator component to our character model, so select it in our player game object. In here, simply click on Add Component and search for Animator. When that's done, simply add it by double-clicking on it or pressing Enter. I'll set the animator culling mode to Cull Update Transforms. Simply put, culling mode translates to what should animations do when they are not on camera. With our option, it will stop playing the animation when the object exits the camera, but still calculate where it should be so that the next time it enters the camera, it will start playing the animation at the right frame as if it never left in the first place. With that done, we now need an animator controller, so go to the Player Animations folder and create a new folder named Controllers. Inside, we'll create a new animator controller by right-clicking in the project window and going to Create Animator Controller at around the middle area. I'll name it Player Animator Controller. When that's done, select our character model and drag our Player Animator Controller to the Animator Component Controller field. Double-clicking our controller asset should open the Animator window. I'll leave it docked right next to our Input Actions window. Now, if this is your first time using an animator controller, this window is likely quite strange to you. While we won't be going through every available option or feature, we'll at least go through what we need to know. The graph in the middle represents the area where our animations and transitions will stay. You can move it around by using the mouse middle button. Go ahead and open up the Player Grounded Clips Animations folder. Then, drag the idle animation to this middle area in the Animator window. Unity automatically creates a rectangle for us. This rectangle is called a state. If we click on it on the right side, we shall see our idle animation assigned to the motion field. Unity also named our state the same as our dragged animation. With that, we know that in the animator controller we can have states that may have an animation attached to them. We can create a state without dragging an animation by right-clicking on the graph area and going to Create State and Empty. We can rename it using the top field, and we can attach a motion or animation if we want. So, states can represent animations if a motion field is attached, and it is through them that we'll add transitions to other states. A state with no motion attached to it can be used as a transition intermediary, such as enter this state without animating, and then check which state we should transition to next. To add a transition to another state, simply right-click on the state we want to transition from and choose Make Transition. Then left-click on the state we want to transition to. This will create a transition from one state to another. We can see all of the transitions from the selected state to other states on the transition field, or we can click a specific transition line. In this transition, there are a few options that will be important for us to know, some which are within the settings foldout. The first one is the S-Exit Time option. Simply put, this means that the transition will only happen once the animation of the state we are transitioning from is finished. This leads us to the Exit Time option, which controls what percentage of the animation needs to be finished for the transition to happen if we have the S-Exit Time option enabled. In this case, we aren't waiting for the whole animation to finish, but instead 75% of it. We'll be disabling the S-Exit Time option for all of our animations, so this won't really matter too much for us. The next important option for our use cases is the Transition Duration option. This is simply how long does it take for this transition to happen. The default 0.25 value means that it will take 0.25 seconds to transition from one state to the other. A value of 0 will make it an instantaneous transition. Something to note here is that Unity seems to blend both state animations when there is a transition duration. This is cool because it makes our transitions look smoother. Of course, a big duration will also mean it will take a long time to animate a player with a second state animation. A value of 0 would also make it so there is no blending whatsoever and would make it a snappy animation transition. Later on, we'll need to be careful when using animation events and setting up an animation duration, but we'll understand why whenever we get there. The last important option for us is the Conditions field. Much like the name entitles, this specifies the condition that we need to fulfill for this transition to happen. This is what we'll be using to know if we should transition from a state to another. Now, we do need something to condition with. That something being a value, like a boolean value or a float value, which will allow us to add conditions such as transition if we are walking or transition if the speed is over 5 units. This is what the parameters tab at the left side of the window is for. To add a parameter, we click on the plus icon and choose the type of value that we desire. Throughout all of this series, we'll have one of our values be a trigger, while the rest of them will all be booleans. For our movement system part, we'll only be needing booleans. Let's add one. In our conditions, if we now add a new condition, our new boolean parameter should show there with a dropdown to choose if the parameter should be true or false for this transition to happen. That's mostly all of the basics we'll need to know about the animator controller. However, right now, if we were to drag all of our animations into this area and make the necessary transitions, it will very likely end up being an horrendous mess, which people often call the animator web. We'll be learning one of the two things that can help us organize things better, which are substate machines. We won't be taking a look at blend trees, but we'll at least learn how to make our sub-state machines reusable. Of course, while this will reduce the amount of webs one area has, in a big game with a lot of animations, this will likely still cause an animator web. There are probably a few assets out there, both free and paid, that can swap this animator system from Unity with a cleaner solution, but we won't be using any. In case you are wondering what blend trees are, they are a nice way to blend between animations often used in things such as movement, where you have a different movement animation per direction. If your project is one of those, it will likely be worth it for you to go learn a bit more about them. Now, regarding about what are reusable substate machines, they are simply normal substate machines made in a way that we can copy them into other animator controllers without caring about what transitions to that specific substate machine exist, nor what transitions that substate machine has to the outside. It will likely become a bit more clear what this means when we start doing them. To create a substate machine, we simply right-click in the main area and select Create Substate Machine. I'll name this one we have just created Grounded. Feel free to remove the other states we have added. To go inside of this substate machine, we simply double-click on it. To go back, we either double-click on the Up substate machine, or we click once at the top in the Base Layer tab. You might also have noticed that substate machines are represented by a diamond-like rectangle shape compared to the rounded rectangles that represent normal states. Inside of this substate machine, we can create other states or even other substate machines. We are going to be doing both, as our animations will be organized much like our folders are. So, start by creating 3 other substate machines. Moving, stopping, and landing. For our normal states, we'll drag our idle and dash animations to this window area. Let's start by updating our moving substate machine. To do that, enter on it by double-clicking it. Then open up our grounded moving animation folder and drag all of the animations here. I'll organize them from the left to the right, following walk, run, and sprint. I'll also go ahead and organize the default states and substate machines from top to the bottom, where the up state and the entry node will be on top, and the any state and exit nodes will be on the bottom. Because dragging our animations automatically sets the states with all the data we need, all that's left to do is to set their transitions. When we have dragged our animations in, Unity already set up a default transition to one of them, which is marked by a yellow arrow. A default transition means that when we enter the substate machine and no other conditions from the entry node are valid or true, it will always enter the default transition. This is why if we select that yellow transition, there is no conditions field, or any field at all. If we wanted to change this default transition to some other state, we would right-click on the entry node and select Set State Machine Default State, and choose a state we want to transition to by default. We'll set it to our run state, so if yours isn't, make sure it is. Now, from our previous transition code, we know that walking can transition to running, and running can transition to walking, but none of them can transition to sprinting, as only dashing transitions to sprinting. We also know that while sprinting can go to both running and walking, in Genshin it transitions to running, and then the running state takes care of transitioning to the walking state. Knowing that, create a new transition from the walk to the run state. Then create one from the run to the walk state. Finally, create another one from the sprint to the run state. We now need to set our conditions for each of these transitions. So we need to create parameters. In the Parameters tab, create 3 new parameters: is walking, is running, and is sprinting. If you haven't deleted the previous parameter we created, feel free to do it now. When that's done, add these to the corresponding transitions. So, walk to run will have is running is true, run to walk will have is walking is true, and finally, sprint to run will have is running is true. That's it for our transitions between the 3 states. But why exactly did we create our isSprinting parameter if we are not using it? The reason why is because states outside of this substate machine might want to transition to a state that's inside of this substate machine. Such is the case of the dash state, which can transition to the sprint state. Whenever a transition happens from the outside of this substate machine to its inside, it will first arrive at the entry node, which then takes care of transitioning to the correct states. So, add a transition from the entry node to the walk state, and another one to the sprint state. Then add a condition of walking is true, and the condition of is sprinting is true, accordingly. If none of these conditions is valid, then our substate machine will transition to our run state, as it has the default transition set to it. Note that this also means that we only need the isRunning parameter because we need it in the transitions conditions between the 3 states themselves, as the default transition doesn't require it. There's now only one transition left, which is a transition from our states to the outside states. Now, normally people will likely go ahead and add transitions from these states directly to the outside states. This can be done by creating a transition to the up node. This should bring up a menu that shows every existing state and substate machines that are outside of this substate machine. While this works fine, this is basically setting up a dependency, which makes it so that the substate machine is no longer reusable. The reason being that we are directly transitioning to a state or substate machine from the outside of the substate machine. So if we copy the substate machine elsewhere, we would also copy those dependent transitions. This isn't what we want. What we want is to know that we indeed can transition to a state from the outside, but we want to decide what that state is outside of this substate machine. When we copy a substate machine that defined its transitions outside, those transitions won't be copied with it. However, we do need a way to tell our substate machine states that they can transition to the outside, without directly telling them what states they can transition to. The way we do that is by using the exit node. When a transition goes to the exit node, it will exit the substate machine and stays in the up substate machine, checking for whatever conditions it has. This makes it so that we can add our transitions outside of the substate machine, which means that if we want to add a new transition, we don't need to update the insides of a substate machine and can simply add a transition outside. Knowing that, create 3 new transitions, one from each state to the exit node. For our condition, we'll create a new parameter of type bool and name it moving. I'll move this parameter up. Then add it to every condition of our new transitions and set it to be moving is false. Note that we need to add it one by one, as selecting all of them doesn't really edit them all. Now, this moving parameter is also how we are going to be transitioning to this substate machine, without caring about what states are inside. If from the outside we create a transition from a state to the substate machine and make its condition be moving is true, we can easily add or remove states from the inside of the moving substate machine without breaking existing outside transitions, as those outside transitions do not care at all what states we have inside, but simply that they need to transition to the substate machine when we start moving. That's it for our moving transitions, but we should of course set each transition setting correctly. So, one by one, disable the sExit time option, which renders the exit time field useless, and leave the transition duration as 0.25. You might have noticed that some of our transitions are grayed out and don't allow us to set any settings. This happens when our transition is an entry transition. The settings of these transitions are set through our exit transitions. This simply means that when we enter a substate machine through a transition from the outside, its entry node transition settings were defined by that outside transition. So, for example, our moving substate machine exit transitions define the settings of our future stopping substate machine entry transitions. This makes sense because our exit transitions are the states we are transitioning from. For example, we'll be transitioning from the walk state to an outside state, and the walk state defines that there should be no exit time when we are transitioning from it. Of course, this also means that the entry transitions are the states we are transitioning to, so they shouldn't be the ones deciding the transition settings. That's it for our moving substate machine, so in the up substate machine, let's add transitions from the other states to this one. Before we do that though, I'll organize them a bit. I'll add the landing to the top left, the moving to the bottom left, the stopping to the top right, the dash to the bottom right, and the idle to the middle up. I'll also make sure that the idle state is the default state. The states or substate machines that can transition to the moving substate machine are landing, stopping, idle, and dash. The condition for all of these four transitions will be moving is true. Now you might have noticed that only our states have a white transition. This is because in normal states there are no exit transitions as there is no exit node, so our created transition can be considered their own exit transition. This means that we need to define their transition settings here. Because of that, in both the idle and dash transitions, we'll be disabling the sExit time option. Make sure the transition duration is always set to 0.25, which shall be the default value. As a test, if we were to duplicate our moving substate machine, it will come without the transitions, which basically makes it so that we can copy it to other animator controllers. As a side note, if you are wondering about the AnyState node in the substate machine, it means any state in the whole animator controller, and not for that specific substate machine. As far as I know, there is no built-in node for the latter. That's basically all we need to know regarding our animator controller. So all we need to do now is to add the remaining animations and their transitions. Let's start with our stopping substate machine, so double click on it to open it up. Then open the stopping clips animations folder and drag the animations into the substate machine. I'll order them as medium, light, and hard stop, as I like to keep the default transition in the middle, which will be our light stop state. I'll also organize them before we keep going. When that's done, I'll add a transition from the entry node to the other two states, as all the states in this substate machine can be transitioned into from outside states. Then add a transition from all states to the exit node. We'll not add any transition between the three states, as they can transition between each other. In every white colored transition, disable the exit time option. We'll only need 3 new parameters here, so add in stopping, is medium stopping, and is hard stopping. From the entry node to the states, add the condition of is medium stopping is true for one, and is hard stopping is true for the other. From the states to the exit node, add the condition of stopping is false. We don't need a parameter for our light landing state, because it uses the default transition, which doesn't require a condition, and also because no other state inside of this substate machine transitions to it. That's all we need here, so go up to the up substate machine. The states that will be able to transition to this substate machine are moving, and dash. Make sure you are transitioning to the substate machine and not a specific state. The transition conditions are, of course, stopping is true. Again, select the white transitions and disable their exit time option. For our last grounded substate machine, we have the landing substate machine, so open it up. Open up the landing folder and drag the existing landing animations here. I'll organize the area here as well. We'll make the light landing the default animation. Because it is the default one, we don't need a condition nor a parameter, so simply transition it to the exit node. Disable the exit time option from the transition, and then create a new parameter named landing. Add a condition of landing is false to the transition. Add the transition from the entry node to the other two landing animations. Create 2 new parameters, is rolling and is hard falling. Add them in their respective conditions in the entry transitions. Then add another transition from the other two landing states to the exit node, and add the condition of landing is false to both transitions. And tick the exit time option in both of them as well. That's really it, so go to the up substate machine. The following states can transition to this substate machine: jumping and falling. Of course, we don't yet have our jump and falling states here, but that doesn't really matter, as all that we need to do is to add a transition from the entry node to the landing substate machine, with the condition of landing is true. This is the good thing about reusable substate machines. We don't need to care what states from the outside transition to it. One thing you might have noticed is that inside of our substate machines, our up substate machine might transition to the entry node. These are the transitions of the outside states or substate machines to this one, but we don't need to worry about them, as if we duplicate a substate machine, they won't be present in the new one. All that's left now for our grounded states are our idle and dash states. Because these aren't substate machines, we don't really need to do anything else besides adding their transitions. Knowing that, we'll be able to transition to the idle state from landing and stopping. The other two will go to the stopping state and not to the idle state. We need to create a parameter for this state, so add a new boolean and name it isIdling. I'll drag the parameter to the top. Then add the condition of isIdling is true for both transitions. Because no states directly transition to this one, none of them are white-colored transitions, meaning that their settings were set from the respective substate machine transitions to the exit node. For our dash state, we can transition from landing, stopping, moving, and idle. Create a new parameter of type bool named isDashing. I'll move it under the isIdling parameter. Then add the condition of isDashing is true to every transition. For the transition between the idle state and the dash state, we'll also need to disable the sExitTime option. That's it for our grounded substate machine, so we now need to do our airborne substate machine. Of course, every grounded state can enter the airborne state, known as jumping state and also the falling state. This means that we need a transition to the exit node from every state to be able to transition to them. So go ahead and add a transition from every state to the exit node. For the condition, add a new bool parameter named grounded above all others. And set the condition for each transition to be grounded is false. For the white transitions, make sure you also disable the sExitTime option. Back into our base layer, add a new substate machine. I'll name it Airborne. I'll organize them a bit. All nodes can be above the entry node as we won't use them. I'll also place the Airborne substate machine a bit to the left, as later on in the series we'll add a swimming one to the right. We'll need to transition from and to the grounded substate machine, so add a transition from both sides. Then create a new bool parameter named Airborne. For the transition from the grounded substate machine to the airborne substate machine, we'll add a condition of airborne is true. For the opposite transition, we'll set the condition of grounded is true. In my original system, I also added the current state is false condition due to a bug that I don't really remember. But I couldn't seem to get any bug with the way we have things right now, so I'll leave it as is. If you do end up finding any bug regarding animations between different substate machines, then you might want to try and add that extra condition. Unless my brain isn't thinking correctly though, there shall be no problems, and it's possible that the bug was fixed through finishing the system. Opening the airborne substate machine, we need to drag our jump and fall animations here, so make sure you go to the right folder and drag them in. I'll organize them a bit. We'll make our jump animation the default animation. We'll be able to transition from the jump state to the fall state, so add in a new transition to it. Then create a new parameter named isFalling, and add it as a condition to the transition we have just created. Of course, it transitions when it is true. Make sure to untick the sExitTime option as well. Then add another transition from the entry node to the fall state with the condition of isFalling is true. When that's done, add a transition from both animations towards the exit node with the condition of airborne is false in both of them. Again, make sure they have the sExitTime option unticked. With that done, our animation controller is finished, and all we need to do now is to set the parameters to either true or false through code, and also set up our animation events. Let's start by setting our parameters first. We'll be doing that using the animator.setBool method. This method accepts a string, which is the name of the parameter, or an int, which is the ID of the parameter. The ID here is an hash that we can get from the string-to-hash method. If we pass in a string to the setBool method, it will call this string-to-hash method to transform it into the hash integer. That means that any setBool call with a string as the argument will need to do that conversion. Because of that, it will be way faster for us if we instead pass in that hash right away. Of course, we ourselves don't know that hash, but the fix for that is quite simple. We simply need to cache that hash once by using the string-to-hash method and then pass it in into the setBool method. This ensures that the string-to-hash method is only called once per parameter, instead of being called once on every setBool call, which should lead to a better performance. Of course, this all assumes that the string-to-hash method doesn't cache the data into an hash set. If it does, then there shouldn't really be much or any performance difference. However, regardless of it caching it or not, it's still a great idea to cache it in, as that makes it possible to change its name through the inspector whenever we want, and the changes will be seen across all usages. To do this, in Unity, open up the Player Data Scripts folder and create a new folder named Animations. Inside, create a new C# script named Player Animation Data. Open it up and remove the default methods and inheritance, and make the class serializable. We'll need two things for each parameter: its name, which is the same as the one we have set in our animator controller, and a property to store our hash. Let's start with our names. I'll create an header with a text of state group parameter names. And then type in serialize field, private, string, grounded parameter name, and default it to grounded. Then duplicate this line 4 more times and swap grounded with moving, stopping, landing, and airborne. make sure the actual strings have the exact same name as the animator controller parameters, even the uppercased letters. I'll now create another header with the text of grounded parameter names. Copy one of the lines above and paste them here. I'll paste it in a total of 10 times. When that's done, we'll swap the variable names and default values with idle and is idling, dash and is dashing, walk and is walking, run and is running, sprint and is sprinting, medium stop and is medium stopping, hard stop and is hard stopping, roll and is rolling, hard land and hard landing, and fall and is falling. Remember that some of our states don't have a parameter as they use default transitions, so we don't need to add them here. If you ever intend to add parameters for them in the future, then you can also create a variable for them if you want to. But I think you need to make sure they also exist in the animator controller. That's it for our grounded strings, so we now need to create our airborne strings. To do that, copy the first 2 lines including the header. Then paste them in and swap grounded with airborne, and set the variable name to be fall parameter name and its value to be is falling. With that done, we now need to create properties for our hashes. To do that, create a new public property by typing in public int grounded parameter hash and give it a private set. We don't need the field serialized field here, as we don't need to set these through the inspector, as they are generated by the string to hash method. Duplicate this line for each variable we have above and rename them accordingly. That's done, so we now need to initialize them. To do that, create a new method by typing in public void initialize and inside type in grounded parameter hash equals to animator dot string to hash and pass in grounded parameter name. The animator here is the animator class itself, and the string to hash is simply a static method. Do the same thing for every single parameter. When that's done, make sure the default names are correct and save. If you saved and they weren't correct, make sure that you update them correctly in the inspector as well, when we add it to the player script. To add it, open up the player script. In here, create a new field, serialize field, public, player animation data, and give it a private set. I'll also add in a field, header, with the text of animations. Now in the awake method, call in animationData.initialize. We now have a reference to our parameters, hashes. Of course, we'll need to use the animator setBool method, which means we need a reference to our animator. To do that, create a new property by typing in public animator with a private set. Then, in the awake method, type in animator equals to getComponent in children of type animator. Note that getComponent in children first searches in the parent and only then in its children, which doesn't really make sense given the name. If you wanted it to search only in the children, then you will probably iterate through its children with the getChild method or through its transform, if that works. Because we really only call it once, and because we are searching for the animator of the player, which there should likely only be one, I'll leave it as is. With that, we'll need to start setting our animator parameters. To do that, first open up the player movement state script. We'll create a method here to not need to call the setBool method every time. So in our reusable methods region, create a new method by typing in protected void start animation and pass in int animation hash as a parameter. Inside, call in statemachine.player.animator.setBool and pass in animation hash and true. We'll also need one to set it to false, so duplicate this method and swap the start with stop and the true with false. With that done, we simply need to call these methods in each state enter and exit methods, both to start and stop respectively. So start by opening up the player grounded state script. In the enter method, type in start animation and pass in statemachine.player.animationdata.grounded parameter hash. When that's done, copy this line. Then override the exit method and paste the line we have just copied. In here, simply swap start animation with stop animation instead. That's all we need to set a parameter value. So all that's left is to do the exact same thing for the rest of the states. So open up every state and call both methods for the states that have a parameter. That's all we need to do, so when you are done doing that, save everything and go back to Unity. If we enter play mode, our animations should now be playing whenever a state changes. However, you might be noticing a problem when doing something like running and then jumping. This seems to happen because there is a prioritization order for the transitions, likely because you can have two conditions being true at the same time, so Unity needs to prioritize one of them. In this case, if it happens to you, it's likely that you are prioritizing a transition to something like a stopping state or idle state, instead of prioritizing to the jump state, or in this case the exit node. To fix that, exit play mode and go to the animator controller. Clicking any state, we should see the transitions it has. We can drag them and set their order by holding the two small bars icon. I'll be changing their order to be exit, moving, dash, stopping, landing, and idle in that order. Do it for every grounded state. For the airborne states, we'll focus on the exit one and then on the fall. This should now make it work more correctly. Of course, we still need to take care of our animation events. To do that, exit play mode if you entered it, and select the character model. Then, in the Project Window tab, right-click to add a new tab and select Animation in case you don't have one open. This tab shows the animations that are in the animator controller of our currently selected game object. This is where we can add our animation events. If we move to any frame that we desire and click on the last small icon with the tooltip of Add Event, we'll add an event to the selected frame, which should show in the frame column. Clicking on it shows us the animation event window where we can select a public method to call. We however have two problems here. The first problem is that we have no way of calling our state events, as only methods that are part of a script in the same game object as the animator component show in this drop-down list. Because our model is separate from our player, this means that we can't access our player script code. Furthermore, none of our states are mono behaviors, so it isn't possible for us to add them as components, which means that we have no way of directly calling their methods. The second problem is regarding our animation events and the transition duration, but we'll take a look at it after we fix the first problem. To fix it, we can create a public method in our player script that calls a state machine animation events methods. However, our animator currently sits on a child game object of the player game object, which again means that we have no access to our player script methods. To fix that, we'll have to create a new class that references the player and calls its public methods. We can then attach that script as a component of the character model, which allows us to use it in our animation events. So start by removing the animation event we have just added by right-clicking it and pressing delete. Then open up the player script. In here, we'll need to create one method for each of the animation events methods, so type in at the bottom public void onMovement state animation enter event, and inside call in movement state machine dot onAnimation enter event. Duplicate this method twice and swap enter with exit for the first one, and then enter with transition for the second one. When that's done, save it up and go back to Unity. In here, navigate to the Player Utilities Scripts folder and create a new folder named Animations. Inside, we'll create a new C# script named player animation event trigger. Open it up and remove the default methods. Because we'll add this as a component, we need to keep the monobehavior inheritance. In here, create a private variable of type player named player. Then, in the awake method, get it by typing in player equals to transform.parent.getComponent of type player. There's also the getComponent in parent method, but that one also calls the getComponent in the GameObject we call it in, much like the getComponent in children method, so we'll use our current solution. When that's done, we'll create a new method to call the events by typing in public void trigger on movement state animation enter event. And inside, call in player.onMovementState animation event. Duplicate this method twice and swap enter with exit for the first one and enter with transition for the second one. When that's done, save it up and go back into Unity. Then in our character model GameObject, add the player animation event trigger as a new component. Back to our animation tab, we can now add in our animation events. Click on the drop-down on the left and select Dash. We'll need to transition to our sprinting state here, and we'll do it around halfway into the animation. So select a frame around the middle, to which I'll choose the 0:11 mark, and add a new animation event. Then select the transition event method in the animation event window. Note that you can add multiple animation events to the same frame if you wish to. When that's done, open up the drop-down again and select Light Stop. The stopping states will simply transition to the idling state at the end of their animation. So around the last frame or around the 1 second mark, as the animation is somewhat coming to a stop here, we'll add a new animation event. Call in the transition event method. Do the same in our medium stop animation. In our hard stop animation, we'll add it a bit earlier around the 0:20 mark. Then in our light landing animation, we'll have an animation event transitioning to the idling state at the last frame. Next, in our rolling animation, add a new animation event around the last frame. I'll place it at the 1:02 mark, transitioning to the medium stopping or moving states. I added it at around the 1:02 mark as that looked a bit better for me. If the transitions don't look too good, you can always add them earlier or later as you desire. Next, for our hard landing animation, we'll need two events. One will be for enabling our movement input, while the other one will be to go to the idling state. I'll add the first one at around the 1:11 mark, which shall be around when we are getting up, and call in the exit event method. Then I'll add the second one at around the 1:25 mark, and call in the transition event method. And that shall be it for our animation events. However, we still need to talk about our problem regarding animation events and transition durations. Let's enter play mode to see what the actual problem is. In here, let's dash, wait a bit and dash again. We can see that our player just stopped dashing right after our second dash. The reason why is because animation events can still be called when we are in the middle of a transition. This is possible because while we are transitioning, our previous animation is still happening or running until we fully transition to the other. An even bigger problem with this is that we'll already be in our new state, so the event that will be called will be the one of that new state. In our case, we entered the dashing state and then the hard stopping state, and then dashed near the animation event of the hard stop animation. Because in code we have already swapped to the dashing state, the animation event ended up calling the dashing state event instead, and entered the hard stopping state again, as that's what we do in the dashing state transition event method. Thankfully, we can easily fix this by not calling an animation event if we are in the middle of a transition. To do that, open up our player animation event trigger script. Then, create a new private method that returns bool named isInAnimationTransition. We'll add a parameter of type int named layerIndex and default it to 0f. While we won't be using layers here, the method we'll call requires it, so it's always nice to have the possibility of passing it in. To be honest, I don't really know much about layers, but this index is the index of the layer our animations are in the animator controller, which should be the first and only one, so it's the index of 0. Inside of this method, simply type in return player.animator.isInTransition and pass in layer index. Then, in all of the other methods, before we call our player animation events, check if isInAnimationTransition and return if that's the case. Copy the if statement to the other two methods as well. When that's done, save it up and go back to Unity. Entering play mode, we shall no longer have this problem, and our animations and transitions should all be working fine. If you did want to call the previous state animation event, you could do that by adding a new variable to our state machine that held the previous state and simply call the previous state animation event method instead. Of course, you will need a new method in our player script to do that. Also note that if our transition duration was 0 seconds, this problem wouldn't happen as the transition will be instantaneous. Someone also wondered if we were gonna add the double animation that Genshin offers, but I have decided when I started trying to replicate this system that I will not do it. In case you are wondering what do I mean by double animation, it's simply that Genshin seems to have two animations in certain states, like jumping or stopping. If we take a look at it, we can see the arms and legs that go to the front can be different. I'm not sure if they do this using IK or simply have two animations, but the leg and arm that go to the front seem to depend on the foot that was at the front as well. For example, if you jump when your right foot is ahead, you seem to jump with the left knee forward. It does seem to only happen after the feet has touched the ground, as if you jump before that you'll jump with the same side knee forward. According to a forum post, if you are using a generic model, which we are for no particular reason besides me not really understanding very well how models and animations work, we can know which foot is at the front by using animation events. You will simply go to each step in the moving stakes animations, for example, and whenever the foot touches the ground in the animation, call in an event that sets a variable that tells you what foot is currently at front. If you end up using a humanoid model, which is probably what we should have been using, you can know it using the animator pivot weight variable. Although it seems that this doesn't work for some if they have the root animation option enabled, and they had to use something else like the animator get bone transfer method. For the animations itself, it's possible that they do it with IK by setting where the knee shall go, or you could flip the animation and add both animations to an array or simply two variables, which you will then choose an animation depending on which foot is currently at the front. Of course, we won't be doing it ourselves, as that's what I've decided myself before. Regardless, our animations shall now be working fine, and we shall now be able to transition to every existing player state. With all that done, the first part of our Genshin Impact movement system is finalized. This took quite a lot longer than I expected it would, but I hope you were able to understand most of it without too much trouble. Of course, we still have two systems left to do, which are the gliding and the swimming systems. Thankfully, both use the movement system as their base, so they are not really very hard to create. However, I'll be placing this series into an halt for a while. Both systems do still need some fixing, as I've left them unfixed to be able to start the first part, but that's not really the reason why. The simple reasons for why it's coming to an halt are money and motivation. A little over a year ago, I got laid off from work and decided to try and get into game dev, and keep going if I was able to earn a somewhat good enough income within around a year. Unfortunately, the amount of money I'm making right now is €0, which is the currency my country uses. For those who are interested, it roughly translates to $0. This is of course not sustainable, which means I can't really keep things the way they are, as otherwise I'll have to stop making videos, as I'll have to go find work and, well, work. Unfortunately, I can't really record audio after work hours, so doing both isn't very plausible, which means I will likely not do any more videos for a few years. Before that happens though, I'd like to try and earn some money through game dev, so I'm thinking on trying to make a few small games in hopes that it gets me some income. I do plan on finishing the series if everything goes well, but if things don't go well, then that will depend on how bad it went, but hopefully I'll be able to finish it up before I leave to work. I did think about a Patreon, but I know I won't get enough income with it to keep going, so I will still have to leave, which will make me feel like I was kind of scamming people, which I don't really enjoy the feeling, so I removed that consideration. Games are also what I'm mostly interested on, and that's what I wanted to focus myself on when I got into game dev. But in this a little over a year, I've mostly focused on tutorials, and not on making games. Which brings me to the second point of motivation. To be completely honest with you, I've been feeling quite unmotivated to edit videos, and I think I felt that in the last videos where I kinda just threw things around without caring too much, even if there were errors on the videos. I also started slacking quite a lot, and haven't slept very well for a while now, so I haven't really been enjoying these days. I will try to rest for a week or so and then likely try and make some small games to get my motivation up and hopefully get some income with it so that I can keep doing this. Because of that though, I won't be continuing with this series for a while, so our gliding and swimming systems won't be coming so soon. As a tip though, the main feature of the gliding is simply limiting the velocity much like we did for our falling state, but with a lower value. While swimming is mostly freezing your vertical position when you enter the water. I also added a GitHub repository where you can check the code we have done so far for our movement system. Of course, it does not contain the gliding and swimming systems code, as they aren't really fixed yet. I do apologize for this outcome, and I do hope that you can understand it. Regardless, I hope you have enjoyed this series so far and learned something new with it. The full video with the first part should also be coming somewhat soon. It's quite a long video to render, so it will very likely come with a lot of audio artifacts. So I apologize for that right now, and hope that it doesn't come with any video artifact whatsoever. Until then though, see you in the next one.